All right. Can you hear me well now? Okay.
Yes. So this first day of the summer school is dedicated to an in-depth series of lectures on various theoretical aspects of reinforcement learning. And in the last decade, we have witnessed an increase in the popularity of reinforcement learning. So it's by looking at the various statistics across the main machine learning conferences that we can clearly see that reinforcement learning is one of the hottest fields in the machine learning community currently. So this rise of popularity was mainly due to a series of success stories that saw reinforcement learning agents surpassing human level performance across different challenging domains. Unfortunately, there are still many theoretical aspects that remain unclear, and our speakers of today, Niao and Bodai, are going to walk us through some of their recent contributions in reinforcement learning, which are fundamental results in the field, as they bring the community some steps ahead in closing this theory-practice gap. It is therefore my great pleasure to introduce Niao He, who is currently assistant professor in the Department of Computer Science at ETHZ Zurich, where she leads the optimization and data intelligence group. Before joining ETH, she received her PhD from Georgia Tech in 2015 under the supervision of Nemirovsky, and then from 2016 to 2020, she had been assistant professor at the University of Illinois at Urbana-Champaign. Her research lies in the interface of operations research and machine learning, with a primary focus on the algorithmic and theoretical foundations of data-driven decision-making problems. We'd like to thank again Professor Niao for joining the summer school, and we are really excited to have her as a main speaker. She is going to tell us all about all the new in tabular reinforcement learning and reinforcement learning with the nonlinear function approximator. Professor He, the floor is yours. Many thanks.
All right. Thank you so much for the very kind introduction. And again, thank you very much. Also, I want to take the opportunity to thank all the organizers for putting together this very wonderful summer school on data-driven control, which is obviously a very timing topic. And unfortunately, Bob will not be able to join us this morning because it's midnight in California, but he will be joining and giving the two sessions in the afternoon. So today we're going to dive a bit deep into reinforcement learning and review some of the recent advances in reconciling three key aspects of reinforcement learning, namely optimization, generalization, and exploration. And I try to make this lecture as self-contained as possible, just in case some of the students do not have the background in reinforcement learning. But if you have any questions at any moment, feel free to interact, or feel free to send your question in the chat, or either raise your hand and we'll try to answer those questions. Okay, so let's get started then. Yeah. So I think arguably RL is one of the most important and hottest topic nowadays that lies at the intersection of machine learning and control. And I think there are also many other close terminologies of reinforcement learning that's used in many other communities, like in operations research, we also say this is neural dynamic programming, or we say this is multi-stage stochastic programming, or decision-making under uncertainty. Whereas in control, people may just refer this as stochastic control or adaptive control. But for this talk, I just stick to the conventions in reinforcement learning and use all of the notations there just to be consistent. So what is reinforcement learning? Just to summarize it in one sentence, it basically describes a learning task where an agent tries to learn to act by interacting with the environment. And by interacting with the environment, I'm really saying that the environment will be providing some reward signals and feedback of the state after the agent plays certain actions. And by learning to act, I'm really referring to that the agent tries to learn to take the best actions in order to achieve a certain goal or make a good sequential decisions along the way. Or simply said, he just want to control the system to achieve the goal he has in mind. So in this particular example with this Super Mario game, you can see that the reward are basically the points that he will get, and the state or the environment gives the feedback about kind of the screen shot of what are the status looks like. And there essentially 4 key actions here that he would like to play. And the agent could also be, let's say, a self-driving car, where this the goal here would be just to achieve or to arrive at the destination as fast and as safely as possible, right? And an agent could also potentially be just a human. Say, for instance, in this scenario where we wanted to give treatments to patients, a doctor tries to dynamically decide what are the best treatments for patients, given on the patient's own health status, and in the long run tries to improve his well-being. So just to summarize, I think that for reinforcement learning, this particular framework or setting is fundamentally different from many other classical settings in control or in other machine learning scenarios like supervised learning. So for instance, first of all, we're dealing with unknown environment, which is unlike control. Oftentimes we assume that we know the underlying system dynamics. Right. Unlike supervised learning here, we do collect the data on the fly. So the data oftentimes comes from different policies and hence they're non-stationary, unlike the IID settings we often talk about in machine learning. And another very key distinguishing feature about reinforcement learning is that we often receive delayed feedback, in the sense that when an agent plays an action, that action does not only affect the intermediate reward he will receive, but will also affect all of the subsequent rewards, right? So this is called the delayed feedbacks. And in certain cases, you will only be able to receive the reward at the very end of the stage of your game or your problem. And that's often called a sparse reward. And this makes reinforcement learning fundamentally much more challenging than the supervised learning problems. Lastly, it's also obvious that for reinforcement learning, oftentimes it requires this sequential trial and error, that you keep trying, the agent keeps trying, connect feedback, and then keeps improving, right? So this is also different from other learning scenarios. And I would say that reinforcement learning is obviously not a new topic. It actually is a very old topic that has over 60 years of history. And interestingly, there are actually many recent, I would say, empirical breakthroughs in the real world that brings RL into the spotlight. And this kind of the very well-known story starts from like playing the Atari game from DeepMind, where they are able to achieve superhuman level performance for many Atari games within very short period. And followed by that is the AlphaGo agent or AlphaZero that was able to beat human players within only less than 70 hours of training from scratch. And there are also lots of interesting, exciting stories on beating world champions in all kinds of video games. And recently there was also some, I think in 2019, there are also some other interesting stories about learning how to play this Rubik cube, and that's much more challenging problem. So other than playing games or robot arms, there are actually a lot of other applications of RL in practice. Say, for instance, in robotics, of course, this is where reinforcement learning is used the most widely. And there are also other applications. People use this for dynamic treatment in healthcare, for online advertisement and the personalized recommendation in e-commerce, and also using this for energy control, say, for instance, to improving the energy, building energy efficiency, and also data center cooling or control. So there are many interesting and exciting applications in the real world, not just to play in the video games. So there are several fundamental, as I said, grand challenges of the modern reinforcement learning comparing to the classical reinforcement learning that people dealt many years ago. And one of the outstanding issue is that in practice, oftentimes we have to deal with very large state space. So if you think about the chess game or the Go games, the number of states can be extremely large. And that means it's and a lot of the algorithms, like classical reinforcement learning algorithms, often requires to compute and store values for each state, and that immediately becomes intractable, both in terms of memory cost and also in terms of computation cost. And they're also, for problems, there are also like very large action spaces and large search space, as you can see here on the right. This is kind of the game trees of Go, and that contains like very large amount scenarios of alternative strategies. So besides large state space, there is also another key challenge with reinforcement learning is the data insufficiency. And by data insufficiency, I meant for two aspects. First of all, oftentimes to train such a large scale problems, we need lots of data, but for reinforcement learning problems, unlike in the real world, we don't have unlimited amount of data like in a simulated environment or in some of the control problems. We only have access to very, I would say, limited amounts of data. And particularly if you want to deploy your policies, this can be very expensive and costly, right? So the second aspect of data insufficiency is really that oftentimes the data we receive comes from past experiences or some behavior policies, which are not aligned with your ongoing policy or your targeted policy. So there is also a lack of causal insufficiency there in order to learn those problems well. So those are the two fundamental challenges that brings a lot of new kind of difficulties in three aspects of reinforcement learning. One is how you can optimize it to learn the optimal policy, and also how does it actually generalize to this potentially infinite number of states, and how could we actually explore efficiently in order to learn to solve the problem well. So those are the three fundamental pillars of reinforcement learning that we will touch base in this talk throughout. And I should say that a lot of empirical successes in reinforcement learning actually relies heavily on trying to address these three problems: optimization, generalization, and exploration. And there are lots of the recent successful stories in reinforcement learning hinges on like very new algorithmic advances, or sometimes people call these algorithmic tricks or algorithmic magics. So this includes, of course, first and foremost, the use of extremely deep neural networks and very complicated neural network architectures to represent your state space or your policies. This also includes, say, for instance, the use of experience replay to memorize and reuse your past experiences in order to make your sample, in order to be more sample efficient. And also the use of, say, for instance, target networks to reduce the overestimation bias, and using entropy regularization to facilitate online exploration, and also the use of offline data to train your models. So all of those are combined in many of the very advanced reinforcement learning algorithms together in order to achieve good performance. And in this lecture, we're going to try to unveil some of these mysteries underlying and try to answer from a theoretical point of view, why does some of these tricks work and when doesn't work, and how we can leverage them to build more efficient and robust reinforcement learning algorithms. So that being said, I would say on the theory side, we really have very little understanding so far, and that leaves a very wide gap of the practice and theory. And this figure may be a little bit exaggerating the gap here, but that's how it looks like, I would say. In practice, as we see that oftentimes we have to deal with very large and infinite state space problems. But in RL theory, at least in the classical theories, oftentimes we're only able to deal with finite state space and oftentimes very small state space. And in practice, we oftentimes use very deep neural networks for the function approximation or for representing your value functions or policies. But in most of the existing RL theories, people were only dealing about linear function approximation at best. And in practice, we see that there are so many different tricks, variations, modifications of the RL algorithms. Whereas in theory, I would say most of the theories really focus on more simpler settings, and all of the analyses are less adaptive to these new variations. And of course, in practice, all of those algorithms does not really have any theoretical guarantee, although they perform quite well in the real world, but we don't really know that theoretically speaking, will they actually converge even at a basic understanding. And this basically kind of motivates a very recent active line of work that tries to bridge these two gaps and tries to bring the theory a bit closer to practice by considering all of these different aspects. And so in the goal of this lecture here, sorry, my mouse is getting too fast. So the goal of this lecture series is really trying to provide or establish some theoretical understanding about these algorithmic underpinnings of RL. And particularly we'll be focusing on some interesting new theories that comes from either a control theoretical perspective or some optimization or game theoretic perspectives, and we'll shed light on some interesting results on both the asymptotics and non-asymptotics of different RL algorithms. And the second component of this lecture series, we really focus on trying to understand the more practical RL algorithms from a theoretical viewpoint and try to understand, say, for instance, convergence, the sample complexity of RL algorithms with nonlinear function approximations, with online exploration. And in the end, hopefully also give you some idea of how we can possibly derive new algorithms with both provable guarantees and also sample efficiency. So that is kind of the goal that we would like to achieve in this lecture, and hopefully you will be able to benefit something from it. And as we go along, so the talk will be consisting of 4 different parts. So the first part, I will mainly focus on the asymptotics of reinforcement learning just to set up the stage so that everybody is on the same page. We will go through some of the basic terminologies, some of the old classical results, and also some of the new findings using those control theoretic tools. And in the second part, we're going to dive deep into reinforcement learning with nonlinear function approximation and try to understand what are their convergence behaviors and try to see how different ways of designing algorithms that can leverage nonlinear function approximation in a principled manner. And in the third part of this talk, we will be focusing on how we can actually leverage locked data or offline data to train the RL algorithms. And this will also build on this either the frameworks that we discussed from this part 2. And in the last part, we will be looking more into reinforcement learning with online exploration and also more on the policy-based methods. So that is the outline of the talk today. And maybe I'll just pause here and to see if there is any questions so far at this point. Okay, I think we're good. So there was one question here. Let me just try to see it. So at the training times reported for the examples at the beginning of the talk, slide 6, I believe real training time, do they refer to sped up simulations? So let's go back to page 6. Okay, here. So those are, I would say for instance, for AlphaGo, there are many different improvements of the reinforcement learning algorithms. I think the latest one is AlphaZero. So the reported time, say for instance, the agent can achieve a superhuman level performance within 70 hours is indeed the reported time for the training time, actually, yes. What would approximately be the resulting training time if the training were carried out in a real time? So I don't quite follow the question though. So all of the training are done offline. So they're not necessarily like real-time training together with the agent, if I understand that question correctly. So, but I guess the point here is really that I think a lot of these, the efficiency of the training really benefits a lot on the fundamental design of the reinforcement learning algorithms and also the neural network structures. And of course, on top of it, there is also the improvement of the computing infrastructures that helps to advance it. But I would say most of that is because of leveraging more sample efficient reinforcement learning to speed up the computation. I hope that answers the question, but we can talk more maybe later on about this point. But as I said, this talk will focus more on kind of the theoretical aspects and the mathematical foundations of reinforcement learning algorithms and try to understand the behaviors of them. Okay, thanks for the question. So maybe let's just move on to the part one of the talk. So just to make sure everyone's on the same page, maybe I'll just go through some of the very basics of reinforcement learning. So mathematically speaking, reinforcement learning is often described through Markov decision processes. And here throughout this talk, I'm going to focus purely on discounted infinite horizon setting. And many of these theories can be generalized to the finite horizon settings as well. So we're talking about a Markov decision processes that consist of, I'd say, 6 key components. First of all, the state space. Here for some of this talk, we will be just looking at finite state set. In some part of the talk, we'll be looking at infinite set as well. And the actions space A, the probability transition matrix, which is a probability for the state, say for instance, the probability when you're giving a state and action, how it will transit to the next state. We're going to denote this as P. And this probability transition matrix is oftentimes unknown in the reinforcement learning setting. And we're going to denote the reward as R and using mu to denote the initial distribution. And we're going to consider the discounted infinite horizon setting. So we will be using this discount factor gamma that is going to be in between 0 and 1. Okay, sorry, the pen doesn't work. So, and we define the policy pi to be a mapping from the state S to a to the action space, and this policy could either be deterministic policy or a stochastic policy. Just say, for instance, in this particular humanoid example, right, let's just to see that you start with some initial state S0, and you take some action A0, and this action, in this case, could be like the forces you applying to your fees and loins. And the agent will then immediately receive some reward R0 based on the state and the action he has. And this will also lead to another new state S. And if you take another action, this will gives you another immediate reward R1 and it will lead you to another state. right? So the state here basically encodes, say for instance, the vertical speed, the positions of joints of the agents, or the velocity, right, of those. And the eventual goal here is really for the agent to try to walk as fast and as steady as possible. And the agent is basically rewarded if he can achieve those goals. So that is kind of the very fundamental setting of Markov decision processes. And I'm sorry for the kind of the delay on this. Somehow my computer got stuck and there was quite some delay on my side as well. Let's see if this will work out. So there are two fundamental tasks that are associated with Markov decision processes. First of all, the two tasks are the first one is policy evaluation. So basically for a given policy pi, we want to evaluate what is the non-term reward you will be able to receive for any given state, starting with any given state S. So that is normally what we denote as wheel of pi. And there is also, we can also, and this is normally what we call the value function. We can also define the values, the state action value function, which we denote as Q of pi. And that is basically the non-term reward you will be receiving if you start with the state S and take action A. So another task in reinforcement learning is the so-called policy optimization. Basically, you want to find the optimal policy. And we're going to denote V star as the optimal value function. That is the maximum, that basically takes the maximum over all of the feasible policies pi. And we're going to denote Q star as the optimal state action value function. So one kind of fundamental result in reinforcement learning is that both of these two tasks can be equivalent to solving Bellman equations, particularly if you look at the state value function. This is satisfies the so-called Bellman expectation equation. So can everyone still hear me okay? Because I don't know what's going on, but my computer is not working well, and there was a serious delay on my side. So you can see my mouse pointer, or is there a delay on your side?
We can hear you and see your mouse pointer correctly, actually.
Okay, good.
Yes.
All right, thank you. Yeah. So we can show that the value function actually satisfying the so-called Bellman expectation equation, and this can be immediately derived based on the Markov chains, and particularly, so this basically says that your value at a given state S, your non-term value at a given state S is essentially the immediate reward you will get plus the expected reward you will get starting from the next state S prime, right? So this is easy to see. And for the optimal value functions, one can also show a similar result, that they are essentially solutions to this Bellman optimality equation. And in the Bellman optimality equation, instead of taking the expectations or the average of your reward, here we're taking the maximal value, or taking the maximum over all possible actions here. So that is kind of the main difference here. And I should say that many of the classical reinforcement learning algorithms, like temporal difference, Q-learning algorithms that we were going to introduce, are essentially based on solving these Bellman equations. And particularly, maybe let's just dive a bit deep into this Bellman optimality equation, and we're going to define this Bellman optimality operator T that we'll be also using later in this talk, which is defined basically as the reward R plus gamma times this max operator taking expectation, conditional expectation here. And as you can see that basically what we shown earlier is trying to say that if Q star is the optimal value function, then it is indeed a fixed point of this Bellman optimality operator. And in fact, this is also true vice versa. This is a if and only if condition here. And this is actually a very fundamental result, but maybe we can but it can be actually proved very easily. So maybe we just see kind of why this is indeed a sufficient condition. So suppose we have I think I missed a very important point in the previous slide. So the reason why we oftentimes use these state action value functions instead of the value functions itself is really because that you can directly derive what is optimal policy pi star based on this state action value function Q star by just taking the greedy policy according to it. And here basically let's say that if Q star is indeed a fixed point to the Bellman optimality operator, then that implies Q star is indeed the optimal value function. So to see this, let's just look at the difference between Q star and any given policy, for the value function for any given policy pi, right? So if we look at the difference between Q star and Q pi, so based on the Bellman expectation equality equations, we know that Q pi satisfies this Bellman equation here. And this basically implies that Q pi is going to be the inverse of this matrix times your reward vector R, right? This matrix is indeed invertible because it actually, you can show that this is a full rank matrix. And you can also use the Bellman optimality equation to show this relationship of Q star and your reward R. And you can also do the same thing by replacing this R. Basically, this R is going to be, let me try to use my. Pen, is that okay?
Is everything okay?
Yeah, would you mind if I maybe just log out and sign in?
Sure.
My screen is completely frozen on my side. I don't know what's going on. Maybe
Sure, we wait for you 5 minutes, don't worry.
Yeah, I'm very sorry about this. So maybe just very quickly, maybe 2 minutes. I'll just sign out and log back in again. Okay.
Sure.
Sorry about that.
No problem. So just a small comment. We have while we wait for Niao, we have the Slack channel link. So we are passing it on the chat, since the link that we sent on the email was not working. So we have a new link. If you want to join, just feel free. Just that from my side. And probably I've seen that there were 2 questions, but if you want to do them again to Niao, that would be very great, because she might go out and come back and she will not see them. Just that.
Okay, it's
Okay, sorry about that.
don't worry, not at all. It seems to
me-
work now. Do you have any more freezing issues or?
Yeah, it's just an issue with my computer. I think I
Don't
was
worry.
having the issue with my Zoom meeting all the time with the Surface Book. So yeah, somehow yeah, it just got stuck, and everything I wrote there just didn't show up. So, but now I think maybe I just re-logged in, and maybe this is better now. Yeah, at least yeah, this is smoother now.
Awesome.
So okay, sorry about that. Yeah.
No worries.
So I do want to make sure that everyone can see my handwriting, but
No, we cannot see the handwriting for now.
still no.
No.
Okay, maybe I just yeah, maybe I just forget about it. Okay, sorry. So yeah, so yeah, maybe so you can easily show this from this just by plugging the definition of Q star and Q pi here, and you will be able to see that the difference of Q star and Q pi is going to be this inverse of this matrix here times the difference between the transition matrices P and P at pi star and pi. And the first term is non-negative indeed, and which you can easily show. And because of this P are indeed non-negative everywhere, and this gamma is between 0 and 1. And second term, you can also this is also non-negative because the definition of how you choose pi star, which is a greedy policy corresponding to Q star. So P times Q star is indeed the maximum value function, maximum over Q star, right? So that is larger than just taking any other arbitrary policy pi. So with this, you can basically show that, okay, Q star is indeed the optimal value function. And the other side of this result can be easily derived also by just plugging the definition of Q star, which I will not show here. And for the interest of time, so let me just maybe speed up a bit. So we can also define, we can also show that this Bellman optimality operator is indeed a contraction mapping. And that is also something you can see immediately by plugging this definition of T of Q here. And indeed, it is a contraction in terms of L infinity norm. And based on this result, as you can see that you have a, we're trying to find a fixed point of this Bellman operator. And a natural way of solving this Bellman equation would be just to apply the fixed point iteration, right? Particularly if we know what is underlying dynamics, we know the MDP, and this is a then we can exactly compute what is the Bellman operator, and we can do this iteratively by applying the Bellman operator to a value function Qt, and this is called the value iteration, right? And as you can see, this is nothing but just a fixed point iteration. So based on the contraction property of this Bellman operator, you can immediately show that this value iteration actually converges linearly. So another different way of solving the Bellman equation is to do this fixed point iteration on the policy instead of on the value functions. So the idea is basically you can try to compute, improve your policy at every iteration by computing this greedy policy with respect to your current Q functions. So this, I wrote it in one line here, but this indeed requires two steps, right? The first step is, first of all, for a given policy pi, you want to evaluate what is the state action value function Q. And then the second step is that you can try to improve it from the current policy to a new policy pi t plus 1 by just taking the maximum actions. And in fact, you can show that this also converges linearly. So both value iteration and policy iteration, if you can compute the Bellman operator, they converge linearly. And there is a difference, of course, in terms of the per iteration complexity, because policy iteration requires both evaluation step and this policy improvement step. And in practice, this is oftentimes much faster than the value iteration. But coming back to our reinforcement learning problem, we know that oftentimes we do not really know the underlying dynamics. We don't know this matrix P. Instead, what we have is just a sequence of samples that either coming from some target policy pi, which we call, or from some behavior policy. And we cannot really just compute those Bellman optimality operators because the state and cannot really compute to store or in memory all of those value functions at every state and action, because the state and action space can be very large, right? So as a remedy, I think in order to deal with unknown transition probabilities, oftentimes people have to resort to this bootstrapping or so-called or stochastic approximation schemes, and this include many typical examples like TD learning, standard Q-learning. And to deal with large state and action spaces, we have to resort to some function approximation techniques to represent your value functions instead. And this could be linear function approximation or using deep neural networks. So for instance, for a given state, we can just represent our value function as a linear function in terms of a number of basis feature vectors phi. Or we can also just use a neural networks to represent our value functions instead. And in the end, instead of learning these value functions for every state, we're only going to just learn the parameter theta. And this parameter theta is often in a much lower dimensional space, where this D here is much less than the state space. So now I'm going to just quickly discuss several fundamental algorithms that we can use for this policy evaluation or to find optimal policy. So the first one is temporal difference learning. That is one of the most widely used approach for policy evaluation. So for a given policy pi, you want to estimate what is the value function. So the idea is that at every iteration, you're going to just use your next state to estimate the target value of your value function. And then you're going to consider or take this combination or convex combination between your target estimate here sorry that this is not transitioning well. So we're going to, so the way how this TD learning works is basically you try to first compute this target update, and then you take the difference between your target update and your current value function at sk, and this is also called temporal difference. And then you do this iteratively. So this is in the tabular setting. In the linear function approximation setting, you basically just update your parameters theta accordingly. So this, again, this orange part is the temporal difference. And this phi here is the feature vector. So you can also extend this to more general nonlinear function approximation. Say, for instance, here we consider this particular two-layer neural network, where you have this only one hidden layer, and you have this weight matrix W. Like for any given state, you feed it into this first input layer, which is going to be just those the feature vectors you have, and then you'll get this kind of two-layer neural network representation, and you can also come up with this TD learning algorithm. So here, instead of here, you can see that have this temporal difference term times the gradient of your value function at W. Here I'm just fixing B, so B is not a parameter here. So maybe I'll just pause here and see if there is any question.
Exactly, sorry to interrupt. There are a few questions. So if the students, if they feel comfortable, please unmute, it's okay. You can ask the speaker directly. If you don't feel comfortable, we can do it for you. But please, if you want to ask a question, go ahead.
Yeah, I feel comfortable, but I think there are some people before me.
That's okay, you can go ahead. And then
all right. Yeah, thank you for the presentation. And I wanted to ask you if we can make any convexity assumptions. Since we are computing some maximization operators, how can we actually compute them? Is the thing that we're optimizing actually convex?
So that's a good question. So first of all, the max operator is taking over, if we were talking about the Bellman optimality operator, then say normally, say for instance, the max is taking over the action space, right? So if your action space is finite, then you can actually easily compute it, right? If it's finite state or finite action space, then that does not really involve solving any nonlinear optimization at all. Because you were just say for instance, if the action space only has 4 actions, right? You were just basically trying to compute which ones gives you the largest value. And that basically can be done in linear time, all of linear time, right? So that by itself is not an optimization problem, but we will come back more on how that will, and well, of course, like if you have a infinite action space, then of course that will become a actual optimization problem, or at least a nonlinear optimization problem. And then you need to consider about convexity or non-convexity there. But so far, I think here we will be mostly focusing on finite action space, where you can evaluate what is the maximum over then.
That was very clear. Thanks a lot.
Thanks.
So there were a few other questions.
Yeah.
Go ahead, please. Go ahead.
Yeah, shall I go ahead?
Absolutely.
Yes, please. Yeah.
Yeah. So you mentioned that the matrix I minus, like identity minus gamma times P is invertible, right? Is that due to the fact that the P matrix is stochastic matrix and the rows add up to 1?
Yes, so it's due to, first of all, the gamma, the discount factor is between 0 and 1, and then P is the stochastic matrix. And then you can show that for any like non-zero vector, if you like multiply this matrix by this vector,
right,
then it won't always be, it will never be 0, right? If you take the norm of, like, I cannot really write here, but
right.
Yeah, but this, yes, as you said, this depends on this gamma being 0 and 1 and P being the stochastic matrix. Yes.
Okay, thank you so much.
I have a small question about the derivative that you have at the bottom of slide 19, if that's okay.
Yes, sure.
Forgive if this is a bit of a naive question, but so at the bottom of slide 19, yes, you have a gradient there. I'm just wondering, what is the configuration space over which this derivative is computed? So this gradient in particular. So so right outside these square brackets here.
Right. Yes. there is this gradient at W, right? And
Yes.
this, for this particular, let's say, neural net work, you can actually compute this gradient here, right? With respect to W, right? The gradient is basically going to be, so this sigma is the activation function. Say, for instance, this could be the sigmoid, or this could be the rectified linear unit.
Ah, okay. Okay.
So you can actually say, for instance, you can actually compute this, right? So this will be, say, for instance, for rectified linear unit, or for just any activation function, this is just going to be the gradient of this times phi, yeah. So this is something you can actually compute, yeah.
Thank you.
All right, so if you guys don't mind, maybe we can take a very short 5 minutes break. I'll have to reboot my computer, and hopefully this will be a much better presentation.
Sure.
Like
Just
right now.
do you want to try it again? Because I think we can't see your annotations. So right now you have do a line. There's
yeah, but
a line
it's not
under...
coming up. I actually wrote equations here, but it's
okay.
it's not working. Yeah. So let's just take 5 minutes break, and sorry for that. And I am going to just reboot my computer and make sure everything is normal. Yeah.
Sure.
Okay. Thank you very much. See you soon. Yeah.
Okay. So we can see your slides now. Maybe we can do some trial with the handwriting.
Okay. Sorry, yeah. My computer is not at its best mode this morning. It's like, I feel like it will explode in any minute. It's like super, super hot. And now just my PowerPoint just disappeared. Okay. Yeah, sorry. So sorry, Matilda, my computer is frozen. Let me just change it to my another computer.
Sure.
And yeah. I will still be here if you have any questions. Just feel free to ask.
Sure, we will handle the question. Don't worry.
So for the ones who for the ones who still have questions, feel free to go ahead. So I believe we had one question about the accountability of the action spaces, one about still thinking about the discount factor, and then about the initial condition of the policy. So feel free to ask.
You know what? I think yes. I just see a question. Do we have access to the slide? I think that would be very beneficial for you guys to have the slide indeed. So let me just maybe share it in the slide so that just share it in the chat, right? So everyone have the slide, and would that be okay?
Sure. Yes, actually, there are many people requesting the slides, so probably would be really awesome to give them access to the slides if possible.
Okay, I think I'm back again. Can you
Yes.
see my slide now?
Yes, we can see
Okay,
the slides.
like, yeah, now it's better.
Yes.
Yeah.
Maybe if you want to try out the handwriting before starting again, or...
Okay, now it's better, right?
Yes,
okay,
yes, definitely.
Great, yeah.
Great, thanks.
Sorry about all of that. Okay.
No worries.
Yeah.
So I guess
I'll share the slide like I think maybe in the other break, because I was just trying to save it. Yeah.
We can restart actually. So yes.
Okay. Thank you so much for your patience, and my apologies. This is not how I expect this will be happening. Yeah. So we just talked about the TD learning, and this is for policy evaluation. And now we're going to look at how we can actually find the optimal policy. And this Q-learning algorithms is obviously one of the most well understood algorithm and widely used reinforcement learning algorithm. And we're going to start with this standard Q-learning algorithm. And this is very similar to TD learning algorithm, except here because we're considering this Bellman optimality operator, right? So here we are going to have this max over all this action in the when computing the temporal difference. So this is the update for the standard Q-learning. And if you have a linear function approximation, right? If your Q is represented by a basis vector times your parameter theta, you can update theta similarly as before, right? There is your temporal difference term here times the feature basis vector phi there in front of it. And the only difference here is that we're replacing this value functions by this state action value functions, and we're using this max operator at every iteration to find the best action corresponding to the current Q functions. And there are indeed also many other Q learning variants, like the deep Q learning is where you use instead linear functional approximation, use deep neural networks. And there's also double Q learning, which uses idea of target networks, and we will discuss in a bit. And then there are also a lot of accelerations of Q learning algorithms using momentum type of ideas, like the speedy Q learning and zap Q learning. So particularly this double Q learning is kind of one of the building blocks of modern deep reinforcement learning. And the main idea of this double Q learning and the motivation, I should really say that, as some of you also pointed out about this max operator. So the presence of the max operator actually causes the so-called overestimation bias or maximization bias. The idea is as follows, right? If you look at this estimator here, this is oftentimes a noisy estimator of your true value functions. Hence, you are really using the maximum of a bunch of estimators to estimate the expectation of the actual maximum value. So this will cause a positive bias in terms of estimation. And think about the case where your true value function is actually 0, your reward is 0. This estimator oftentimes can be very noisy, so it could be both positive and negative. And when you take the maximum, it will always kind of in favors of those actions that gives you positive and a noisy estimate. So in order to deal with this maximization bias, the idea of double Q learning is really to introduce another set of estimator for Q. So it keeps track of 2 estimators of these Q value functions. One estimator used to select what is the best action. And then you use a second Q estimator to evaluate what is the value function at this best action, right? So you see that here this best action is selected based on this estimator at this WA. And then it is evaluated based on another network or another Q estimate, QB here. So this is kind of the double Q learning algorithm. Particularly at every iteration, you will just flip a coin and randomly update either the first estimator or the second estimator. So the computation cost is the same as Q learning algorithm, but the memory cost is twice large as the standard Q learning algorithm. So to give you a better idea of this maximization bias, you can look at this like Sutton and Bartels example. And in this example, say for instance, there are only 4 states. And if you look at the state A, there are 2 actions, right? Either you move to the right or you move to the left. If you move to the right, you will end up in a termination state and you will get a 0 reward. If you move to the left, you also get an immediate reward, which is 0. But you might, in expectation, it will goes to other states with expected negative reward. So as you can see in this case, actually the optimal action at state A is going to be to turn to the right instead of the left, because in the left, you always expect some negative reward in expectation. However, when you run Q learning algorithms, because of this maximization bias, it will often appear that making a left will have a positive value, right? Because this is a random reward, the random reward could be positive. So initially, when you run Q learning algorithms, it will actually it will strongly favors the left action, which is not optimal, right? On the right figure, you can see that at the very beginning, actually, there is a very high probability that you will actually choose the left action. And if you apply double Q learning, it actually fixes this issue, and it will be less in favor of this left action, right? So this is the so-called maximization bias. So another issue with Q-learning other than the maximization bias is that oftentimes if you were to use functional approximation, and if your data are connected from some behavior policies, then in fact, this could lead to divergence, right? So this, again, there are actually many examples that was provided in different textbooks. This is an example that was given by Bert. And this is a particular example where you have, say, 7 states and only 2 actions. And here we're using 8 parameters to estimate your value function. So as you can see, the number of parameters is much larger than the number of states you have. So this could actually fully represent your true value function. If you apply this TD learning algorithm, for instance, here, based on some data that are connected from a behavior policy, so this is the so there are only 2 actions here in this example. So the solid line is 1 action and the dashed line is another action, right? So in this example, actually, you can easily show that off-policy TD learning algorithm actually will diverge. So those W's, which are the parameters you try to learn, will diverge. And this is not only true for TD learning, but also true for Q learning as well. And this was essentially the so-called deadly triad that was a concept coined by Richard Sutton in 2018, which says that if you try to combine both functional approximation, even just linear function approximation, with bootstrapping, with off-policy data, it will not guarantee convergence of your algorithm, right? But in practice, we know that you have to use functional approximation for large state space, and you have to use bootstrapping for efficiency. And you do only have observations from off-policy data, then what can we do, right? This feels like a bottleneck here. And for this part of actually the first part, which I'm significantly delayed, that we're trying to really to understand what are the asymptotics and non-symptotics behaviors of these reinforcement learning algorithms. And can we say anything about if we are to using function approximation, how large or how flexible our function approximation should be in order to guarantee convergence, and how we can actually derive what are the sample complexity you need for them to converge. And there are indeed many proofs and analyses for these classical reinforcement learning algorithms. And I think a common recipe here is either to resort to stochastic approximation or the continuous time dynamic systems of the underlying ODEs. So here I'm just, and you can use all of these to derive the asymptotic convergence or finite time convergence, or even derive very tight error bounds on the convergence. So here I just listed a couple of references. They are by no means exhaustive, right? There are many also recent theoretical developments and many different variations of Q learning algorithms and TD learning algorithms. And here, the orange ones basically highlights those use this continuous time dynamic system perspective, and the black, the blue references are those that use these stochastic approximation arguments. And later in this talk, I'm going to give you some examples, actually very recent result that that uses either of these approach, and so that you can have a better flavor. What are the technicality of different proof techniques? So I wanted to start by saying that using this continuous time dynamic system has both advantages and disadvantages. The apparent advantages are, first of all, I think because they're first of all, it offers a very systematic and also oftentimes unified analysis for different reinforcement learning algorithms, and as you will see later on also. And there are lots of very rich control theory and tools that we can leverage directly, and so you don't really need to have a lot of new analysis. And also another, I think, a key importance of this is that you don't really need to have a clear objective or gradient to work with, right? You just directly work with dynamics, and you'll be able to get a full characterization of how it should behave. The challenge, though, is that oftentimes we have to deal with nonlinear systems, for instance, especially even for just a tabular Q-learning setting, because of this max operator. The underlying system is indeed nonlinear, and there are not that many theory about convergence of nonlinear systems, unfortunately, and then it's also very hard to extend to nonlinear function approximation in many cases. And now let's just see how we can actually leverage a unified ODE analysis and to derive the convergence analysis for a wide spectrum of reinforcement learning algorithms based on existing control theory. So the ODE method is initially introduced by Bokar and mine in this very seminal work. And although it has more than 20 years of history, still these days I find it quite enlightening. And it's in fact also one of the 20 most read articles in SAM Journal of Control and Optimization. And many of you probably is familiar with the main idea of this ODE approach or ODE method. So the basically what it says here is that we can analyze the convergence of any stochastic approximation algorithms by simply tracking the associated ODE in the steady state, right? If the underlying ODE is asymptotically stable, then it actually guarantees the convergence of this stochastic approximation algorithm. And by asymptotic stability, we're really saying that the solution or the ODE converges to some equilibrium point for any arbitrary initial condition. So this is kind of the key idea here of the ODE approach. As you can see that let me just give you a simple example. Say, for instance, if h is just a gradient of some function, then your ODE is essentially going to be the gradient flow, right? But here for reinforcement learning, as you can see, most of the algorithms, those H you have in those updates are not necessarily the gradient of some objective. So the analysis is slightly different from gradient descent. So the ODE method so to be more specific, there is this Bokar and Mine theorem that says the following, right? Suppose you're under some regularity condition, say so there was a typo here, which I did not correct. So this should be actually H. So if your operator H, or this mapping H here is globally Lipschitz continuous, and if your step size satisfies is this Robbins-Monroe step size that is square summable but non-summable. Say, for instance, you can choose alpha k to be just of order 1 over k, right? And if your noise epsilon here is bounded, that satisfies this condition listed here in this part C here, then you can, and then on top of that, if we can show that this original ODE is asymptotically stable, and the limiting version of this ODE is also asymptotically stable, then this will be enough to guarantee that there exists a unique globally asymptotic stable. Then this will be enough to show that this discrete time stochastic approximation algorithm will actually converge to the equilibrium point X star. Right? As you can see, this algorithm is super handy in the sense that if you are able to show the asymptotic stability, then you are able to establish convergence. And I'm going to give you some examples like where you can actually easily establish asymptotic stability. Hence, you will get convergence of reinforcement learning algorithms. So the first example is, for instance, for linear systems. We know that for linear systems, there exists a unique stable equilibrium point if and only if this matrix A is Hurwitz. And by Hurwitz matrix, we mean that all the eigenvalues have strictly negative real parts. And particularly if you think about the TD learning algorithms, those are indeed can be casted into a linear system. And this stability argument has been widely used and explored in various different TD learning algorithms. Say, for instance, if we look at the TD learning with linear function approximation, and you can immediately see that if you look at the associated ODE of this stochastic approximation, this is going to be given by some matrix A, right? This matrix A is the feature matrix phi times D. D is the diagonal matrix of your station distribution of your so this D is basically the diagonal matrix of your initial or your station distribution mu. And then you have this matrix as we see before, gamma times P minus I times phi. And you can actually easily show that this matrix A is actually Hurwitz, because you can see that this actually, you can show that this intermediate, this middle matrix here, gamma times P minus I is in fact negative definite. So this part is indeed negative definite. And if this matrix phi, your feature matrix phi is also full rank, then this will mean this A will be also negative definite. Okay. So that's kind of the original results that people tries to use to establish the convergence of TD learning. So you can also generalize this analysis to other TD learning algorithms. Say, for instance, if we consider the double TD learning algorithms that we proposed a few years back. So the idea is similar to the double Q learning, where we maintain two different sets of estimators for your value functions, right? You have this estimator, two different parameters, theta B and theta A, and you're updating them symmetrically. And you're using one of those estimators to evaluate your target update, and the other one to just keep an online estimate of your value function. Then you can also write down what is associated ODE, and that will have a slightly different matrix A here. But this matrix A is actually closely related to what you see in the case above. And you can also easily show that this matrix A is actually Hurwitz, and if this feature matrix phi is full rank. And then this immediately implies the convergence of double TD learning algorithm. Okay. Of course, linear systems are very kind of optimistic, right? That's not really capture a lot of the real dynamics. So we also have many rich theory about stability of general nonlinear systems. So if this H is just arbitrary, or let's say if it is Lipschitz continuous functions, then there was also lots of existing theory that tries to establish sufficient conditions to ensure global asymptotic stability of this nonlinear system. Here I just list one example of it. And you can see that if you are able to find some Niao function V that satisfies these certain conditions, then indeed this implies asymptotic stability. As you can see, that differs from the linear case. This is just a sufficient condition, not a necessary condition. And although this result is very general, it can be very hard to construct these Niao functions. And oftentimes it's also very hard to check whether these conditions actually are satisfied. Not only is still there are some work that shows that indeed for Q-learning algorithms, you can come up with such Niao functions and use that to establish convergence. And we can see that for general nonlinear systems, this is not really very useful in some sense, that because this difficulty with constructing the Niao function. But in fact, we can show that for some special nonlinear system with particular structures, the story is much nicer than this. And of particular interest is a class of linear switching systems, which is a very special class of nonlinear system. And that has some similarity with linear systems. So the difference from linear systems is that for linear switching systems, here your matrix A is no longer fixed, right? This matrix A will be switched among a subset of matrices based on some switching signal sigma. And this switching signal can be arbitrary, right? It could be just arbitrary policy, or it could be dependent or controlled by your state. So if it is dependent on your state xt, then we call this state feedback switching signal. And there exist actually a lot of interesting results about the stability of linear switching systems. And particularly here is one nice result that says that that says that the linear system is globally asymptotically stable if and only if you can find some full rank matrix L and a family of negative row dominant matrices A1, AM, such that this following condition is satisfied, okay, for any given matrix from A1 to AM, right? So notice that here, this is indeed a both necessary and sufficient condition to characterize the global asymptotic stability of switching systems. And this result is actually closely related to robust stability of uncertain linear time variant systems. I'm sure many of you know control theory much better than me here. And this is indeed a very useful condition. And now I'm going to show you that indeed for Q-learning algorithms, and actually for a very large family of Q-learning algorithms, they are naturally can be characterized as linear switching systems. So for instance, recall that this is how Q-learning algorithm looks like, right? At every iteration, we're going to update our Q functions based on this temporal difference. And with some simple algebraic simplification, you can easily obtain the following ODE model for this Q-learning algorithm. And that is particularly given by this matrix here, times some other vector, okay? And here I should say that this pi qt is denoted as a greedy policy with respect to the current value function qt. This D again is just the diagonal matrix that corresponds to the state action distribution in the steady state. And this P is the transition probability matrix as before, right? And as this may not be immediate to you, but if you rewrite this, like using the notations I just introduced, right? If you denote xt as just the difference between qt minus q star, and if you denote this matrix here as just this matrix A, as you can see this switching signal here, sigma, actually depends on your current state qt, right? So this is indeed a state feedback switching policy here. So as you can see that by nature, right, Q-learning algorithm is in fact just a linear switching system. It's not linear system, it's not the general nonlinear system, but it's actually controlled by some switching signal. And different from what we have seen before, that we do have this additional affine term. So it's not completely switching linear system. This actually has this affine term that makes it a little bit more complicated. And you cannot really just use the existing theories that I just discussed to prove the convergence here, or to prove the asymptotic stability here. So what we've shown is that actually this affine term can be easily avoided if you consider if you relate this system to two much simpler systems, particularly if you just ignore this affine term. Actually, if you just throw away this bilinear term, this will give you this linear switching system, right? Which we know how to prove the asymptotic stability. And for this linear switching system, in fact, you can show that this bilinear term here, this affine term here is indeed always, I think it's always non-negative, right? It's less than or equal to 0. I'm not able to remove it. But you can show that this is actually always less than equal to 0. Sorry that it's not showing up, but yeah, the reason for that is because this pi star is actually the greedy policy response to Q star, right? So any action you take by any policy pi qt, this will give you a smaller value function. Hence, this term is actually negative than smaller or equal to 0. That basically implies that this linear switching system you come up with is indeed strictly an upper bound of this affine switching system. Okay, so that's why we call it an upper comparison system. You can also show that if you just replace or throw out this affine term, just to replace this policy pi or the switching signal here by just the fixed policy, which is kind of the optimal policy pi star here, then you can show that this will be a linear system right now, right? Because this matrix here is just fixed. And you can easily show that this is indeed gives you a lower bound on the original affine switching system. And that's why we call it a lower comparison system. And all of these can be easily derived in just one line of proof based on the definition of the greedy policy. And as we see earlier, that for linear systems, we know that if you're able to prove that this matrix here is Hurwitz, then this implies asymptotic stability, which is indeed what we already shown for TD learning, because this is almost the same as TD learning. If you look at the upper comparison system, since it's linear switching system, if you're able to show that sufficient and necessary condition holds true, then this is also asymptotically stable. Instead, we can show that this matrix A sigma here. In fact, we can show that this matrix here is indeed by itself a negative row dominant matrix. Hence, you can just construct the 4-rank matrix as identity, and this will immediately give you that sufficient condition you need for asymptotic stability. Right. So this then brings to the following kind of immediate result, which says, like, for the linear system, we know that is asymptotically stable. For the upper system, we know that it's also asymptotically stable. Now, if we look at this this original system, and we can immediately just apply this so-called vector comparison principle that says, if it is if those functions are if this system is upper bounded and lower bounded by this system from the initial point, then there will be the whole trajectory will be upper and lower bounded by these two comparison systems. Hence, as t goes to infinity, this original system will also converge to 0, or also give you the converge to the equilibrium point, right? So this is kind of a very immediate result you can see. And basically, so far, what we have established is the asymptotic stability of this associated ODE, and by invoking this ODE analysis, this Volcker and Mines theorem, this implies that if you just use any Robbins-Monroe step size, and you apply this Q-learning algorithm, this Q-learning algorithm will be guaranteed to converge almost surely as k goes to infinity, right? I should mention that there indeed are also many other proofs for Q-learning algorithms. This is by no means the first asymptotic result on Q-learning algorithms. In fact, so there are stochastic approximation-based algorithm, approach analysis for this Q-learning algorithm. There are also finite time analysis for Q-learning algorithms that has been recently developed. All of these other proofs are much more complicated than what I have just shown to you. And in fact, the step size here we choose are very general. As long as satisfying this Robbins-Monroe condition, it will guarantee convergence. Whereas many of these other proofs, they do need to have very special step size choices. And this analysis can be easily extended to many other Q-learning variants, as you can imagine, right? Because really, it really boils down to just figuring out what is associated ODE and checking, do some sanity check to see if the underlying system will be asymptotically stable. So particularly, I'm going to give you this example on, let's say, some target-based Q-learning algorithms. And by target-based Q-learning algorithms, I'm just basically saying that we're going to use, as before, just to keep track of two different estimates of your target values. And then we can update your target values either like as the double Q-learning algorithms, like symmetrically, or we can also update your target values like in a kind of in a periodic fashion, right? Every 50 iterations, you are going to update your target values, or you can update it in a Polyarc averaging fashion, right? We call this averaging Q-learning or average TD learning algorithms, or periodic TD learning algorithms, right? You can easily come up with all of these different strategies to update your target values. Particularly, let's say if you look at this averaging Q-learning algorithm, where here we're going to use a second estimator QB to estimate or to keep track of these target values, right? And we're going to update this QB based on a Polyarc averaging step, which is basically taking the combination of QA and QB at every iteration, right? That's a very simple algorithm. Instead of double Q-learning, so in double Q-learning, basically you're updating QA and QB in a more symmetric fashion. Here we're just taking the average to update the other estimator. And you can show that this actually is also naturally a switching system, and you can easily also show that this is asymptotic, underlying OD is asymptotically stable, and you can come up with the convergence easily, okay? I will not go to the details, but I think you can easily see why that is the case. And similarly, we can also extend this to Q-learning with linear function approximation. And for linear function approximation, the ODE is slightly more complicated than before, but still it's a switching system. So what's different here is that it's no longer easy to directly verify the asymptotic, those sufficient conditions for stability. The reason for that is because that we know that even for Q-learning with linear function approximation, as we shown earlier, that this does not always converge, right? If your target, if the data that you connect from the off-policy data is far away from the target policy of the optimal policy, then it actually does not always guarantee convergence. So here we show that if you actually use this OD analysis, and if you look at the upper comparison system, lower comparison systems, you can actually easily, from that theorem will provide for switching systems, you can easily cook up some sufficient and necessary condition for guaranteeing the asymptotic stability. And in fact, this is a condition we have, which looks maybe a little bit abstract here, because it's essentially just coming from the asymptotic stability. And we show that if this sufficient condition holds true, then this will guarantee convergence of Q-learning with linear function approximation. And this condition basically essentially also says that your behavior policy or the data you use should be close enough to the optimal policy. And we should mention that there are also similar conditions that has been established in the literature, like the well-known one is a Mellows condition, and that one is much and that one is based on this nonlinear system, come up with some Lyapunov functions and construct sufficient conditions for it. So it's much more conservative than our condition, because our condition is really based on this not only sufficient condition, but also necessary condition from the switching systems. So in fact, you can also show that you can also very easily verify that the analysis based on some numerical experiments. And here's just one toy example that you can visualize how the upper system, lower system looks like, and what does the original OD system looks like. And you can see that those systems are indeed very close to each other. So this basically summarizes kind of the roadmap that how you can actually establish convergence of reinforcement learning algorithms, right? You start with some algorithm, let's say Q-learning algorithms, and you write down what is the underlying ODE system for it in the steady state. And you try to understand what are the asymptotic stability behavior of this underlying ODE system. And if this asymptotic stable, then that gives you the convergence, asymptotic convergence, right? So this is kind of a simple recipe that does not only apply to Q-learning, but potentially many other stochastic approximation algorithms. So maybe I think this is a good time to pause a bit here and see if there are any questions. I do see there are lots of messages in the chat, and I'm sorry that I didn't monitor it yet.
So no worries about the chat. We tried to help you there. But if there are any students with questions, please go ahead.
Hi, Niao. Could you please go through that portion where you discussed that capital pi symbol? I couldn't understand that.
Okay, so the capital pi one is just for easy notation. Okay, so it's essentially just to choose the. So it's just a I think we're getting there soon. Here. Right, so this is just for easy notation. Actually, you can also, I think you can also write this as so basically P of pi qt. So that is essentially to say that I'm going to just use the greedy policy, to pick the corresponding action, right? So this is just a matrix notation to just make it in a more compact form.
Okay, thank you.
Mm-hmm. Any other questions? Please feel free to unmute yourself, and I do wish that we can keep this as interactive as possible. Okay.
Yeah, I have a question, if I might.
Sure, yeah, please.
So it is not really clear to me how we can go from a discrete time update to a continuous time update, because if you prove stability in for a continuous time dynamical system, it is not guaranteed that the sampling, if it is a sampling of that dynamical system, is also stable. So I don't understand how we make this passage.
So there, as I said, there are kind of so showing the asymptotic stability of the OD is not is of course not the only sufficient thing you need to check, right? And there is definitely a gap between the discrete system and also the continuous system. And so basically, as we see that in this ODE method, there were conditions you need to satisfy. Say, for instance, these errors, this noise term at every step has to be bounded, right? And this step size has to be satisfying this Robbins-Monroe condition here, right? So that basically says if your step size is small enough, right? If your error, the noise is controlled at every iteration, then indeed this ODE, this continuous time system, is very much close to the discrete time system. So that implies a convergence.
I understand. Thanks a lot.
So basically, yeah, I think there are really those requirements on the step size and requirement on that the errors cannot increase too fast, right? So that's a very good point.
Yeah, so I have a question. So first of all, thank you very much for this. This is actually a very interesting idea. So you show that the iteration, so the learning process can be categorized as an affine system so that you can achieve some convergence. So my question is that, so still here, we prove that the iteration process converge, but does it solve the problem of reaching the global optimality? Or it just showed that it converged to something, but maybe it converged to the local optima point, for example. So I just want to make sure.
Good point. So if you look at what I wrote down here, right? So this is indeed the difference between your estimate and the true value function, Q star. So Q star is the optimal value function. right? So if by convergence, I mean this Qt minus Q star will converge to 0 for this problem here. Right, 0 will be the global, will be the equilibrium point here. So basically, if it converges, then it will converge to 0, meaning that Qt will converge to Q star. So it will converge to the optimal value function.
So it means the global optima, right?
Yes, the global optimal value function, yes.
Okay, interesting. Okay, thank you.
And you should pay attention to here. So far, I'm only looking at tabular settings, right? This is not like nonlinear function approximation yet. So this only applies to tabular setting and also linear function approximation as of now. Okay. And for those cases, we know that normally Q-learning actually converges to the true optimal function. And later on in the next session, I will talk about if you have nonlinear function approximation, under what conditions you can show also convergence to the global optimal value function.
Okay, thank you. Thank you very much.
Thank you. Thanks for the question. Okay. So maybe I'll just come to the remark really quick because I do want to be mindful of the time. I think we're supposed to have the break very soon. So I think this, hopefully this gives you some interesting connections between Q-learning and switching system, and this has not been identified in the literature. So there was, and also I can see that the analysis here is quite intuitive, right? You just basically look at how the system should look like and understand the asymptotic stability of it, and this gives you the convergence instead of some like just some upper bounds or playing with the stochastic approximation directly. And in fact, there was nice things about using this ODE analysis in the sense that you can, as I said, exactly characterize the behavior so that you can get much tighter conditions, much tighter bounds, and much weaker assumptions you need. So there are, of course, many open questions, right? First of all of this only shows asymptotic convergence. And we know Q-learning asymptotic converges and also double Q-learning asymptotic convergence. But which one is better? This does not say anything about like their finite time behavior or which one is faster than the other one, which one is stable than the other one, right? How do we compare different algorithms based on the asymptotics, which I will discuss also very soon. So there is also, as Emilio pointed out, there was a difference between the discrete time dynamics and the continuous time dynamics. Those are not exactly equivalent to each other, right? How do we characterize their differences? And so far we have talked about asymptotics, but this does not really give you a finite time guarantees. Establishing the finite time convergence will then need to resort to the discrete time dynamics, right? And we do have some interesting recent ongoing work that's shown that in fact you can also get much tighter bounds by directly looking at discrete time switching systems instead of the continuous time. And ideally, hopefully, this will inspire the potential to design new algorithms based on this control perspective and how we can leverage some of the robust control theories to design something much more efficient and reliable. So lastly, as I said, in the next, I will also talk about how can this be generalized to not this approach, but how, like if we have nonlinear function approximation, essentially we will have some non-convexity there. When does this guarantee global convergence to the globally optimal value functions? And that I will discuss in the next section. And I'll maybe just pause here and give you guys some time for break, and hopefully we'll see you back in 20 minutes or so. Yeah. Meanwhile, if you have any other questions, feel free to let's just ask. I will also try to read some of the chat and try to answer the questions here during the break.
I just suddenly have an idea regarding the results. So here, actually, you use some results regarding the stability of continuous time linear switch system to reason about the convergence of the training process. So I believe, I'm not sure, but I believe there is some similar results also for discrete time switch linear system. And would it be possible to use that those theory to reason about the convergence, because the question before me, so he just asked, so this is a theory regarding the stability of continuous time switch, a linear switch system. So it also depends on what is the sampling frequency. So when you discretize it, why don't could we directly use those theory from the regarding the discrete time system?
Right, that's a very good question. That's a natural thinking here, right? So ideally, if you wanted to characterize the finite convergence, you will have to use those analyses for discrete time dynamics. So I think the difference here is, first of all, the underlying like the Q-learning algorithms or this original algorithm is stochastic by nature. Right, so in principle, those are stochastic discrete time switching systems. And my understanding is there is not much work in terms of understanding the stochastic dynamic systems, unlike the deterministic dynamic systems. Right, I think that's one issue. And for sure,
I was just saying the stability of deterministic discrete time switching system. Yeah. So I think there should be some results. I'm not sure, but I think there should be some result regarding stability of deterministic discrete time.
Exactly, yes. And as said, that would not be sufficient here, right? Because you do have this stochastic noise at every iteration.
Okay, so, I see, yeah.
So that's why we kind of use this OD analysis by resorting to the continuous time dynamics and use this OD analysis says if the noise is controlled well enough, the step size is chosen well enough, then this will be close to each other. But I think that's definitely also a viable approach to just directly look at the discrete time dynamics instead of resorting to the OD.
Yeah, then we don't need to think about what should I, so because that's the continuous time stuff and you're reasoning about something which is discrete time and then you still have a gap for it. But now I see the point. Thank you.
Correct. Yeah, that's a very good question. Yeah, thank you.
Actually, second. Okay, we can start now, actually. Yes.
All right. Yes. Let's do that. All right, so let's continue the discussion. And as we mentioned earlier, that all of the results are for asymptotics. And how can we compare different algorithms based on their asymptotics, right? So particularly, I'm very interested in, let's say, just comparing, say, for example, Q-learning and the double Q-learning algorithm. And the reason for that is, as we showed earlier, that double Q-learning was proven to be helpful with reducing this maximization bias and was extensively used indeed in practice, especially in many of the deep RL algorithms. This is kind of one of the building blocks. So recall that the Q-learning algorithm, if we were to use linear function approximation, basically looks like the following. And if we were to use double Q-learning algorithm with linear function approximation, we're going to keep two separate estimators for the value functions. One is using parameter theta A, the other one uses the parameter theta B. Here in particular, I'm adding this coefficient beta k here, and beta k is just a Bernoulli random variable because we're going to update either of those updates based on flipping a coin, right? So at every iteration, we'll either update A or B. So, and as we mentioned earlier, that the essence here is really to use one estimator for selecting the best action or the greedy policy, and use another estimation to evaluate the value function. So as we shown earlier, that you can show that both algorithms converge asymptotically, but the question is, which one is better then? Like, which one should we use actually, and why does double Q learning actually can potentially lead to faster convergence or better performance. So far we have shown that the asymptotic convergence, which is like almost a sure convergence. But even in the asymptotic regions, we can also talk about distribution convergence, right? And this is actually indeed not only characterize the convergence rate, but also characterize the dependence on the system parameters. So for instance, here we want to, I think a good way to maybe just compare two different algorithms in the asymptotics is based on comparing the asymptotic variances, right? And that basically characterizes how stable each algorithm is. So in order to consider the asymptotic variances, we're going to introduce the notion of asymptotic mean squared error. And this is nothing but just taking the trace of this asymptotic covariance sigma term. Okay, so it's like you take the square norm of your estimator theta k minus the optimal solution theta star. For double Q-learning algorithm, because we have two different estimates for the parameters, so we can define the asymptotic mean squared error for both of those estimator parameters, theta A and theta B, right? And we can also consider the asymptotic mean squared error for the average of them, right? The average of them is also a good estimator for the Q-value functions. So we have this result. Sorry that I did not put a reference here. And also I just look at the chat. Yeah, thank you guys for providing those references in the chat. So this is a work that we had from last NeurIPS 2020 on the comparing the efficiency of double Q-learning and Q-learning. It's actually a very simple result, I say. So the result is basically as follows, right? If you compare these two algorithms and let's consider both of them using the same scale of step size 1/k for both Q-learning and double Q-learning. And we can show that if both algorithms converges asymptotically, because we know that if you use linear function approximation, convergence is not always guaranteed. But suppose there are some certain sufficient conditions like the Mello condition or what we proposed earlier satisfied, then suppose both algorithms converge, then we can show that under very mild conditions of like say basically you need this step size G to be sufficiently large, such that we can show that the asymptotic mean square error of any of your output of your double Q-learning estimator actually is strictly worse than the asymptotic mean square error of standard Q-learning, right? So this C0 is some positive values, G is also the step size, so it's also positive. So this is strictly worse than the asymptotic mean squared error of the standard Q-learning, which actually comes out quite a bit surprise, right? Because if you think about all of this double Q-learning was really trying to reduce overestimation bias to stabilize the learning process, but it actually ends up to have a larger mean squared error. However, we also shown that if you take the average of your two estimators, theta A and theta B, and you look at the asymptotic mean square error, actually it is actually the same as the asymptotic mean square error of the standard Q-learning. There are a couple of things that we need to pay attention to here. First of all, for the way that for us to make a fair comparison here, we're using the step size of double Q-learning that we're using is twice as large as the step size of the standard Q-learning algorithm. And the reason for that is because for double Q-learning algorithms, we're only updating one of those estimates at every iteration. Right, so if you choose the step size to be twice as large as the standard Q-learning, then that is a fair comparison in the sense that this will guarantees like similar convergence, at least the same like transient behavior among those two systems with the same convergence rate. And now then it makes sense to compare their covariances and symptotic mean square error. So as I said, the result here holds true for tabular setting or linear function approximation. We don't have a result for linear function approximation yet. And I will show you kind of how we establish this result is not actually very challenging. But before that, let me just maybe first to show you some kind of numerical studies we had that illustrate what we have proved in the theory. Right, in the theory, we've shown that WQ learning with twice as large as a step size actually has worse asymptotic variance comparing to Q-learning algorithms. And here is again the Baird example that we discussed earlier, which actually is an example where Q-learning could fail when you use a linear function approximation. And to make Q-learning work, right here, we use like a larger discount factor. So in the original counterexample by Baird, they were using like a discount factor, which is like 0.99. Here we just use a moderate discount factor so that both algorithms will actually converge. And if you look at this figure, this red curve is how the Q-learning algorithm behaves. And this blue line is the double Q-learning algorithm if you use the same step size as Q-learning algorithm. As you can see that if you use the same step size as Q-learning algorithm, double Q-learning will converge much slower than Q-learning algorithm, right? The reason is kind of also straightforward because you are only updating one parameter at a time rather than two of them. However, if you use twice as large as a step size as Q-learning, double Q-learning actually converges in the same rate, right? Initially, as you can see, the transit behavior is nearly the same as Q-learning algorithm. However, asymptotically, you see that the double Q-learning with twice step size has much larger variance than Q-learning algorithm. Right, you can see it here. There's larger asymptotic variance. But if you look at the double Q-learning algorithm with the average estimator, the average estimator actually has the same variance as Q-learning algorithms as we predicted in the theory, which is what you actually observe in all of these experiments. Like in all of these three figures, you see that the one with the variance of the variance of the double Q-learning algorithm actually is the same as the Q-learning algorithm. So this basically perfectly matches what we predicted in the theory for this particular example. But what about another example? Okay, so this is another example about the grid world, which is also a tabular setting, but we're using some linear function approximation to estimate the value functions. And in this example, you see something similar, right? You see something similar that if you use the same step size as Q-learning algorithms, and double Q-learning actually performs worse, has slower convergence. So you have to actually really use the twice the same as the step size. If you use a twice as large as the step size, it behaves very similar at the beginning. And again, here you see that the double Q-learning with the average estimator actually has the smallest, actually has a much better asymptotic mean squared error or asymptotic variance. So you might wonder, like, what happened? Like in all of these examples, it's not really clear that like you don't really see this phenomenon of maximum bias, right? So let's just look at that example we discussed earlier by Sutton and Bartle about the maximization bias, right? In this example, we shown earlier that in fact there was this maximization bias of Q-learning algorithms initially, but double Q-learning was able to avoid that. And here is again the figure where we consider that both double Q-learning with twice the step size and double Q-learning with the average estimator, right? Both of them actually converges better than Q-learning algorithm. However, if you use much larger, like, so this is the first left figure is in the tabular setting. If you consider the same example, but if you use much larger, if you use like neural network function approximation instead, which is oftentimes what people use in practice, then you will see that there is no overestimation bias phenomenon anymore. Right, so Q-learning algorithm with neural network function approximation does not really have any overestimation maximization bias at the very beginning. But still, in this case, you can see that double Q-learning performs better, slightly better than Q-learning algorithm, and especially in terms of asymptotic mean square error, is much better than the Q-learning algorithm. So this seems to suggest that maybe like using nonlinear function approximation seems different, right? But I think the bottom line here you can see is that the punchline here you can see that is really that if you were to deploy double Q-learning algorithm, then you should be using like at least twice the same step size as Q-learning algorithm to ensure at least the same convergence rate. And then you should be really outputting your average estimator instead of just either one of those estimator you use to estimate your value function, right? So that's kind of some interesting observations from our theory, and which happens to align very well with the numerical implementations. Any questions at this point before I show you kind of how we establish this result?
So,
please go for it.
So yes, I have a question. So, what about soft Q learning? So, I think that again, what's the comparison of double Q learning with soft Q learning? Where in soft Q learning you try to avoid this maximization bias by using entropy regularization and penalizing deterministic policies at the beginning of the learning process.
Okay, that's a very good question. So first of all, yes, soft Q learning, which kind of smooths out this max operator that also helps with maximization bias, right? So in practice, people use soft Q learning also a lot. Here we did not make any comparison to soft Q learning algorithm. I think that would be very interesting future work to do. And in terms of using entropy regularization and all of these, I think I will also talk about this in the next part. We'll be also discussing more about the role of entropy regularization and softmax learning type of algorithms. Yeah.
Thanks a lot. So by using entropy regularization, so let's say that this is an implicit explanation of why using entropy regularization. There's no rigorous justification. While with double Q learning, we justify rigorously that you deal directly with this maximization bias. Is this correct?
Sorry, I don't hear you very well. Can you repeat your question?
So I'm asking if with double Q learning you justify rigorously that the maximization bias is not anymore an issue. Because with soft Q learning there's no rigorous justification. It is just an intuition behind entropy regularization.
So for double Q learning, the essence here is really that to handle this max operator, you are using a different set of estimates to find, you are separating the selection of best action from the evaluation part. But for soft Q learning algorithm, it's different, right? You're really just using a softmax operator. And then there you don't necessarily encounter this maximization bias that severely, I mean, because the max operator is much more non-smooth than the softmax operator. So the softmax operator kind of will not have such a large maximization bias. right? So the kind of the motivation of those two algorithms are slightly different. Yeah.
Okay, thank you very much.
But that's a very good question. Yeah, I think yeah, it will be interesting to look into the differences between these three algorithms. Yeah.
Thanks.
Okay. All right then. So maybe I will just give you a quick, brief sketch of how we derive this result. Actually, again, as I said, this heavily relies on like existing theory on dynamic systems and control theories, and this is nothing really very new here. So if we consider this general linear stochastic approximation, okay, with this say this 1/k step size, and here for simplicity, I'm going to assume that it will converge to some point that is just a 0, so that we just look at this asymptotic, so that we don't need to bother with this Q star here. And suppose we define this matrix A as the matrix associated with underlying ODE in the steady state, and this other covariance matrix of this affine term B as the following. Then there is a very kind of classical result that says that if you select this step size G properly, such that this matrix 1/2 times identity plus G times A is Hurwitz, then the asymptotic covariance of your stochastic approximation algorithm is indeed the unique solution of the following Lyapunov equation. Okay, so you can basically exactly characterize what is the asymptotic covariance matrix is by just plugging in what are this matrix A and what is this matrix sigma B there, right? So, and we can use this result to establish what are the asymptotic covariance of both Q-learning and the double Q-learning algorithm by writing down what are the corresponding Lyapunov equations. Right, if you write it down here, you will see the only difference here is that the matrix A in the steady state is different, right? So this is already something we see before, right? For this matrix A in the steady state for Q-learning algorithm, assuming that your policies, because in the steady state, your policy is already close enough to the true optimal policy. So here A is just this a matrix that was defined based on this optimal policy pi star here that we see before, which is indeed Hurwitz, right? And we can also write down what is the matrix corresponding matrix A for this double Q-learning algorithm. Again, this is what we have shown before as well, which you can also show this matrix is Hurwitz. And if you select the step size G properly, then you can show that this matrix here is also Hurwitz matrix. And then now it's the basic observation. You can see that because of this kind of symmetric nature of this matrix A of double Q-learning algorithm, you can actually show that this asymptotic covariance term should have this special structure, which is also symmetric. Right, and if you look at the kind of the relationship between these two Lyapunov equations, if you add this, if you take the sum of the rows of this matrix A, you see this recovers the A matrix in Q-learning. And since, as we mentioned from before, that this asymptotic covariance matrix is indeed the unique solution to this Lyapunov equation. And these two seems to have two different, and using this, you can actually easily construct a solution that satisfies this other Lyapunov equation as well. So this essentially implies that if you take the summation of V matrix and C, taking half of it, then this will actually should be exactly the same as the asymptotic covariance due to the uniqueness of this Lyapunov equation. And this immediately then implies that the asymptotic mean square error of the average estimator should be the same as the asymptotic mean square error of the Q-learning algorithm, because they have the same asymptotic covariance terms. And also by similar reasoning, you can show that indeed the asymptotic mean square error of either of those estimators is strictly worse than that of the Q-learning algorithm, because you can show that the trace of this upper part of the matrix is strictly greater than the trace of this of diagonal matrix part. So that basically completes the proof, right? As you can see, that is really nothing magical here, just to try to characterize what does the asymptotic covariance look like, and you will be able to establish this type of relationship between these two algorithms. And you can do this also potentially for many other Q-learning variations and see which one has the smallest asymptotic covariance. And as I said, this also gives you some motivation how you can actually design more principled algorithms, right? By trying to see, based on this Niao function equations, trying to design ways to minimize the asymptotic covariances. So this basically summarizes what I want to discuss. There is a little bit delay, so now this is actually the summary for the part one. That we can see that there are many other rich and useful control theory that can help us to build better understanding of the asymptotics of reinforcement learning algorithms. I only focus on asymptotics for this part. In fact, you can also leverage a lot of these theories to establish finite time convergence of reinforcement learning algorithms as well. And I think the interesting part is really that can we leverage these to really design better algorithms with faster convergence, potentially more robust, better stability, which remains a largely open question here. And in the next, we will be moving on more to the nonlinear function approximations. So that will be kind of the part two of this lecture is what can we say about nonlinear function approximation? As we mentioned earlier, right, there is a huge gap between the theory of RL and the RL used in practice. In practice, almost always we're using deep neural networks for estimating the value functions because of the state space is so large. But in most of the theory we see so far that only applies to linear function approximation. And in fact, even for linear function approximation, sometimes it could diverge when you are combining it with off-policy data, right? So there is a huge gap between what people use in theory and what people can prove in theory and what people use in practice. And as I said, like there is really no way that you can avoid using nonlinear function approximation, because like the state space is so large and you do have to have enough representation power in order to generalize to other states, right? So the fundamental question we want to ask is like, if we're using nonlinear function approximation, will it converge, and under which conditions should it converge? How much over-parametrization do we need in order to guarantee convergence? And how does it generalize to other states and other policies? So in this part, I will focus more on the convergence part. And as we mentioned earlier, that there is this deadly triad issue with reinforcement learning in general, that if you combine function approximation with bootstrapping of policy data, it could lead to divergence, as shown by many examples that we discussed earlier. On the theory side, like people have been using Q-learning with linear neural networks for training, like for like playing like Atari games and many other video games, and showed great success. Like they're able to achieve superhuman level performance, and they're able to learn very good policies. Then what happens here, right? What's going on here? And in fact, in this paper by Wan Hasselt in 2018, they listed a couple of hypotheses. So they were saying, like so they were basically hypothesizing that maybe because of these other techniques we were using, that actually eases the divergence issue. So for instance, because we're using very large function approximations, then it actually helps with it actually is less likely to diverge, or because we're using these targeted networks to cure the overestimation bias, or this double Q-learning type of algorithms to reduce the overestimation bias, then this helps with this also helps to ease the divergence. Or maybe it's because we used multi-step returns instead of just one single, just looking ahead for one step. Like when you compute the temporal, the target update, instead of using just look ahead for one step, you look ahead for multiple steps. This will also help with the divergence, help with avoid divergence. Or because we use experience replay and we're prioritizing the samples and reweighting the samples, and this helps as well. So here was, I think there are a number of hypotheses here, and they were able to, they run many experiments to see like which one actually is helpful. And turns out all of those are somehow helpful, right? If you use target networks versus without target networks, you get much better performance. But they were only able to justify it numerically, and still it remains largely open, like theoretically speaking, like which one of them is the main reason that uses the divergence, right? And in this talk, we're trying to maybe shed some light on the nonlinear function approximation part. Does it mean, is it true that if we use larger and more flexible networks, then it will help with the convergence? Which is in general, intuitively for, this may not necessarily be the case, right? If you think about if you use larger networks, it makes your problem even more non-convex. And then it's more likely that you will be stuck at some stationary points or some saddle points rather than converging to a global optimal solution. So in this next, I will basically just look at more simplified settings, not deep neural networks. We're going to look at just a two-layer neural networks, and we're going to see like whether this will lead to global convergence to the optimal, to the value function, and whether and how many neurons, how large is the network you need in order to guarantee certain convergence. So to start with, I'm going to look at just the TD learning with neural network approximation, right? Again, this is kind of the very basic algorithm for policy evaluation. For given policy pi, you want to evaluate what is the value function V. And for simplicity, I'm going to denote this X as just the feature vectors for a given state S, okay? And this X is going to be a d-dimensional vector, and d is much smaller than the state space. And we're going to consider the following function approximation for your value function V, which I denote as V hat. And V hat is given by 1 over square root of m times the summation of some coefficients ai times this rectified linear unit. And by this plus sign here, this really refers to I'm taking the max between a given vector u and 0, right? That's the kind of the standard rectified linear unit or activation function use. And pay attention to here that we use this particular coefficient 1 over square root of m, which turns to be actually very crucial indeed for the analysis. And you'll see why that's true. And for simplicity here, I'm going to assume this coefficient A are fixed, and those are randomly generated from this Radmacher distribution, like from -1 and 1. Okay, and I'm going to also initialize them in a symmetrical manner, that the first m over 2 coefficients will be the negative of the last m over 2 entries of A. Okay, and I'm going to also initialize those weight matrices W to be just the IID Gaussians also in this symmetric manner. And for now, since A are fixed, so the only parameter are those weight matrices W. right? And for TD learning algorithm, we're going to just update our parameter W. And the TD learning algorithm here, I call it neural TD learning algorithm, which basically performs the following, right? Like what we see before. So at every iteration, you update your weight matrices W by adding this step size alpha times the temporal difference, right, evaluated, and times the gradient at W, right? If you look at the gradient of W here, we'll have a form for that, right, later on. So why is this so one thing you might be wondering, like, why does the TD learning look like this in the functional approximation setting, right? Why do you have this extra gradient term here? So in fact, I think TD learning algorithm was oftentimes compared or can be viewed as solving this minimization of mean square Bellman error, right? Remember that for any value function, it actually satisfies this Bellman equation. And in order to solve this, you can basically just say, let's just minimize the mean squared Bellman error, right? So the optimal solution or the minimizer of this problem will be essentially going to be the value function, right? Because the value function will be driving this objective to be 0. And here we're going to just represent our value function as this parameterized function we had. And if you write down kind of the gradient of this objective, you will see that the gradient looks very similar to the TD learning algorithm that you use, but it's slightly different, right? In fact, the TD learning can be viewed as a stochastic semi-gradient, because like if you write down the gradient here, you will see that it will have this temporal difference term, right? Delta, which is this whole thing here. So my pen is not really working well. But you can also see that if you take the gradient, so you will have this temporal difference term here, and you also have the gradient of this first term, right? We had, and you also take the gradient of this second term, which involves this conditional expectation, right? And this other term. But for TD learning algorithm, we're just showing away the gradient of this second part completely. We just use the gradient of this first part, right? So it's not really the true gradient of this objective. That's why we call it a semi-gradient. Okay. So if you use a neural network approximation, then this objective immediately becomes non-convex. If you use linear function approximation, this is still a convex function, right? Because it's a quadratic function inside of it. It's linear, so it's convex in the linear function approximation, but it's immediately non-convex if you use neural network approximation. And you should also pay attention to that there is an approximation error between the function, the parameterized function we had to use and the true value function, right? The true value function is not necessarily represented by this two-layer neural network. So as you can see, this is very different from like the gradient descent, right? In like, and it's very kind of unintuitive why applying neural TD learning algorithm might lead to global convergence, right? Because first of all, it's not really the gradient. Secondly, this is a heavily non-convex problem. Lastly, there is a certain approximation error, right? So can we show that this neural TD learning converges to the true value function V? And if so, how many number of samples or how many number of iterations do we need in order to converge to an epsilon optimal solution? And how many neurons or how large is the network should be in order to get an epsilon optimal solution, right? That's all the questions we're interested to figure out. So indeed, there are lots of theory in the literature about TD learning algorithm with linear function approximation, right? And they're able to characterize how many number of samples or iterations do we need to convert to the true value function within this linear function class, right? There were some recent results for TD learning with projections, TD learning without projections, IID settings, and those are kind of the recent breakthroughs in the theory side of TD learning algorithm. But here we're dealing with nonlinear function approximation, particularly this two-layer neural network type of function approximation. So there are also a very active line of research in deep learning theory that studies the generalization of gradient descent type of algorithms with this two-layer overparameterized neural network. And these are kind of also in the spotlight of deep learning theory that shows that if the number of neurons, let's say the M, you use the network width is infinity. If this goes to infinity, then you can show that this essentially mimics to a reproducing Hilbert kernel Hilbert space, and then you can actually show global convergence. And this was proven in the Jacot and ETHZ paper. But of course, in practice, nobody uses infinite number of neurons, right? We oftentimes just use finite number of neurons. So there were results shows that if you use like a polynomial, if the number of neurons you use is polynomial in terms of number of samples you have, then you can show that actually it also, if you just apply gradient descent, you will converge to the optimal solution, or oftentimes it gives you zero training loss. But and there were also some results for stochastic gradient descent. Let's say for classification problems, people can show significantly reduced overparameterization complexity. Instead of a polynomial dependence on the sample size, they only get polylogarithmic dependence on the number of training samples you have. So those are kind of the recent advances in deep learning theory. And it'd be interesting to see how this can be generalized to understanding TD learning or the TD learning dynamics, which is significantly different from gradient descent dynamics in several aspects. First of all, right, unlike the gradient descent or supervised learning regression settings, where basically your observations are just you have the labels, and you do have you have the kind of the input, and you have directly given the labels, right, noisy labels. Whereas here in the reinforcement learning setting, we are not directly given what are the estimations of your value functions. We will only be given just rewards, right? So those are very different from the gradient descent or from, say, regression settings. And secondly, in many of these regression classification problems, people were able to show that, in fact, if you initialize your neural network as what we discussed earlier, and if your number of samples M is sufficiently, number of network size is sufficiently large, then you can show that your estimator does not drift too far away from your initial weight W. So this is also so-called the lazy training regime, where basically your parameter is close enough to the initial W0. So more or less your function approximation is like linear function approximation, essentially. So all of these existing result requires that your network size to be polynomial in terms of the number of samples. And in the TD learning setting, this basically implies you need the polynomial dependence on the state space, but the state space is so large, right, in general. And if your overparameterization is larger than the state space, then this is no better than just applying the tabular TD learning algorithm. You don't really, there's no benefit of using function approximation. So the question we are interested in to see is like, is this really necessary, right? Can we have modest overparameterization that is independent of the state space? And can we actually control this drift among of these network parameters? So before that, maybe I will just give you a kind of a quick motivation of what is this so-called neural tangent kernel that was extensively studied in recent years in deep learning theory. So if you look at this value function, which is represented by this two-layer neural network, you can actually use, say, by first order Taylor expansion, right? You can rewrite, let's say, it's approximately equal to, let's say, you just do the Taylor expansion around your initial weight W0, right? So this is your function value at the W0, and then you can compute what is the gradient, right? The gradient of this will be just because this is the maximum between 0 and this linear function. So the gradient will be the indicator function, right? If your W transpose X is positive, then it's 1. If it is less than 0, then it's 0, right? Remember that's the rectified linear unit. How does it look like? And times X, that is the gradient of at W0, and you have this W minus W0 in the first order term. And you can see that because of this definition of this rectified linear unit, actually this term is the same as this term times Wi, right? Because so basically, you can easily see that by definition, that V hat is just your gradient times Wi0, okay? So basically, this simplifies it to just this linear term, okay? So your value function can be approximated by this indicator function evaluated as the initial weight matrix W times this X, your feature vector, times Wi, right? So this is more or less like a linear function approximation. And the idea is that if W0 is close enough to W, then your value function will be approximately linear at every iteration, right? Approximately linear. And if your number of samples, or number of network neurons, M goes to infinity, then this will actually reduces to the so-called neural tangent kernel, right? You can define the neural tangent kernel as just taking this, so this will be, first of all, because W0 are random Gaussian vectors, right? If net M goes to infinity, so these are just random features. If net M goes to infinity, this is then associated with this neural tangent kernel in the infinite width limit regime, where you're just going to take your feature, your random feature vector is going to the indicator times X, right? You take the inner product between them, taking the expectation over W0. W0 is just the IID Gaussian random vector. And this is a neural tangent kernel is well known to be a universal kernel in the sense that actually it can represent, it's actually the corresponding reproducing kernel Hilbert space is indeed dense in any continuous function space, meaning that if you have any continuous function with a compact domain, then you can find, then you can approximate it arbitrarily well using this kernel function here. Okay, so that is kind of more or less the essence here of why we use this type of initialization, and in fact also for neural tangent kernel, this may look a little bit complicated, but you can actually exactly have the closed form kernel computed, which is given by some arc cosine functions. So one of the key assumptions we make here is that we're going to assume your value function V is going to reside in this reproducing kernel Hilbert space generated by this neural tangent kernel. As I said, this is a universal kernel, meaning that basically any continuous function, as long as your value function is continuous, it can be well approximated, right? So V is should be belonging to such reproducing kernel Hilbert space. In particular, on top of that, we're going to assume that the norm, like so this small v is basically the representation of your value function in this kernel space. And we're assuming that your representation with those coefficients are bounded in L2 norm, okay? So which is kind of just a bounded assumption here. You don't want those norms to go to infinity. And this essentially basically characterizes how smooth your value function is, right? If your value function is really smooth, then you would expect that this V bar is smaller, right? So this is corresponding to kind of the RKHS norms in this space. So here comes our main result. Our main result basically says the following. We have two set of regularization here. So the first result says if we're going to enforce a max norm regularization by projecting our weight matrix W into this set, which says that basically we're enforcing the Wi to be close enough to the initial point within some distance that is proportional to the number of neurons you use. Then we can show that the total number of neurons, if you just set it to be of order 1/epsilon square, and you set your step size to be of order epsilon square, then you can show with high probability that your value function that you estimate your output, this is actually the average of the output, is going to converge or is very close to the true value function with this type of error bound. That depends just in the order of 1/square root of t, right? So that being said, you only need a very modest overparameterization in the order of 1/epsilon square, and then you will be able to actually achieve global convergence here for this neural TD learning algorithm. But the kind of the cost you need to pay is that at every iteration you need to perform this projection. But performing this projection is actually relatively easy because this is a max norm regularization, right? So you can do this in parallel. And this max norm regularization is widely used actually in deep learning. Like particularly, this is also closely related to dropout and many other things people used to train neural networks. So the other result we have is that if we don't do any regularization, if we don't enforce your weight matrix to be within the proximity of W0, your initial point, then we show that we can still get global convergence to the true value function as long as you stop early, in the sense that if you just stop your algorithm for a fixed number of iterations t, that's roughly in the order of 1/epsilon square times alpha. If you just run this many number of iterations, not more than this, but just this order of iterations, and with properly choosing step size and the number of networks, neurons you need is of order t. So basically this is kind of saying that you need slightly more neurons than the number of iterations you need, right? So this is also in the so you need to have more overparameterization. So you need to have some overparameterization here, essentially, right? The number of neurons you need has to be more than the number of samples you have seen. And then under these conditions, you can also show this type of convergence. And maybe let me just discuss this a little bit more so that you have a better picture of what's going on before we dive into the kind of the technical details. So the kind of the highlight here is basically says that you need some sort of regularization, right? So either through this max norm regularization or through this early stopping. So early stopping is also widely used regularization technique for training neural networks that people observe in practice, especially like in training games or many adversarial machine learning problems where you have noise in your labels. Then they've shown that using early stopping actually helps you to generalize better, right? This is kind of in our theory, we've shown that this is also true for TD learning or for reinforcement learning. So you need some sort of regularization in order to generalize or in order to convert to the optimal solution. And by adding this regularization, then you only need a very modest overparameterization, okay? And as we said, in the max norm regularization case, we only need the 1/epsilon square number of neurons. And this is much better than the existing result that was provided in this paper here, these two papers. They've shown that if you do L2 regularization instead of max norm regularization, you actually need much more neurons. They've shown that you need 1/epsilon 8 number of neurons if you apply this L2 norm regularization. And know that L2 regularization is much more harder to compute than the max norm regularization, right? Because the number of neurons is so large, and the L2 norm regularization, you cannot really do it in parallel as the max norm regularization. So this is much more kind of computationally efficient than the other one as well. And without the explicit regularization, we've shown that, so basically we needed to have smaller step sizes in order to make sure that your W does not drift too far away from your initial point. Hence, that increases slightly the sample complexity. And in this case, if you just don't use any sort of regularization or projection, the overparameterization complexity we derive is 1/epsilon 6 instead of 1/epsilon 2. So you pay a little bit more price there without doing any projection or regularization. And the sample complexity is also slightly higher, okay, than the case where you apply max norm regularization. But the trade-off is that with max norm regularization, you were kind of you were restricting also the network representation power, right? Because you are restricting the weight matrices to be bounded somehow. So there is a trade-off, right, between the sample complexity, overparameterization complexity versus the representation power of your neural networks. And lastly, I think we should mention that the overparameterization complexity, as you see so far, only depends on sort of this 1/epsilon, the accuracy that your target error, and the this parameter V bar, which kind of measures how smooth your value function is and the bounds of your value function, the true value function, right? This has nothing to do with the size of your state space. So unlike this other work that I should mention that uses the uses neural networks, and they've shown that you need polynomial in size of your so this should be state space S. You need a polynomial in the size of state space, number of neurons, in order to convert to the true optimal solution, which is apparently impractical when your state space is very large. So that kind of is kind of the main message I want to discuss about this neural tangent like the neural TD learning algorithm. And with the remaining time, I want to maybe also discuss very briefly the proof. And the proof, if you look at this result, you think it is so sophisticated, but the proof actually is fairly straightforward. And also this gives you another flavor of kind of how to derive finite time analysis based on this discrete time stochastic approximation scheme. So this is a very different flavor comparing to the ODE analysis we discussed earlier. But this is also kind of the popular approach people try to establish convergence in the literature. So the idea is basically the following. So let's look at this, define this minimal norm solution W bar. And this W bar is basically the weight, the initial point W0, right? Times, times this A, that is the coefficient we used before for initializing your neural network, and the V, which is the representation of your value function in the RKHS. right? So we define this W bar here, then you can immediately show that by definition, if you look at the gradient of V hat times W bar, then this will converge to the true value function as m goes to infinity. Okay, so if you write this down here, so you will basically get just nothing but 1 over m. So this gradient here, you have 1 over square root of m indicator function x transpose, and times these two terms. And this is kind of the reason why we use symmetric initialization, so this gradient times w0 will be just essentially 0, right? So this will give you just nothing but 1 over m, your feature vector times v, and because those wi are IID Gaussian, so as m goes to infinity, this will converge to the neural tangent kernel, and that will converge to v of x, right? By definition. So this basically essentially means your v of x. So this basically means w bar is essentially, you can view this as the optimal solution if the optimal solution if your Vx is just a linear function, right? And if we define this, consider this Niao function, which is just nothing but just a square distance between your estimator W and W bar. And you can show that there is a very nice drift analysis of this Niao function. You can show that if you look at the difference between these two Niao functions at the two consecutive iterates, there is actually a negative drift, which relates to kind of what we wanted to minimize, right? The distance between your value function and the true value function, plus some error terms. And those error terms depends on, say, for instance, how you choose your step size, alpha, and how many neurons you use to estimate your function, right? So this is basically kind of the key result that we base on. And this drift bound only holds true if t is smaller enough, right? If t is smaller than the stopping time, and we define the stopping time as the smallest iterate where your wi will be far away from w0. So basically, as long as your number of iterations does not go to too large, or if your wi does not drift too far away from w0, then you can establish such type of relationship. And then basically by telescoping this equation here, you will be able to show convergence of this term here, right? By just telescoping, taking the sum from 0 to t, and with properly choosing m, right? Then you can actually control this distance here, which is kind of how what is the error you get with your estimator, right? So that is kind of the key idea. And in fact, this is kind of very standard also in the analysis. Say, for instance, let's look again at this WT plus 1. This is basically just the WT plus alpha times GT, and GT is given by your temporal difference, which is delta T, times the gradient, right, of at W. And if you just take look at the Niao function and you just expand it, you will see that oftentimes you have this cross term, which is your semi-gradient GT times the difference of WT minus W bar. And then you have this square term of your semi-gradient, which can often be controlled, right? This is bounded by some constant. So this will basically just of order alpha square. Like if you choose alpha small enough, then you will be able to control this term to be very small. So the important term is, of course, this intermediate, this cross term here. And for this cross term here, if you just plug in the definition, right? Again, this GT is just the temporal difference times the gradient, right? Times this is the inner product here. If you look at the first two terms, right? The gradient at W times W. Actually, this because of we're using the rectified linear unit. In fact, this is exactly just the value function at WT, right? Because this is just the indicator function times W times X. So this is nothing but just the true value function at the WT, okay? And if you look at this W bar times this first term, as we mentioned earlier, if you use W0 instead of WT, then this work essentially converts to the true value function, right? So basically let's just plug in those two terms, right? So this first term is coming from this first term, and we're going to add and subtract the value function, true value function. We're going to add and subtract this gradient, replacing WT by W0, okay? And then this is the second term here in the previous step. So if we decompose it this way, and you then can immediately see like how this will work out, right? The first term here is kind of the standard TD learning analysis. And this is bounded because, and you can show that this temporal difference, because you are using this Bellman operator, this actually expectation corresponds to some contraction, right? That's why you get this 1 minus gamma times the square norm of the V hat and the V. Okay, this kind of follows immediately from there. If you look at the second term here, what is it? Second term is basically measures, as we said earlier, if m goes to infinity, then this is going to converge to Vx, right? So the second term basically characterizes how good your function approximation is to the neural tangent kernel, right? So that is controlled by this 1 over square root of m. And the last term is basically the difference is controlled by the difference between W0 and WT, right? It's like how your parameter deviates from the initial point. And as we said, if we consider our stopping time tau, so before the stopping time, this is always bounded by 1 over square root of m. So you can control all of these terms, and then you get the drift bound we discussed earlier, and then this leads to the final convergence, right? So this is kind of the high level. Actually, this is essentially the whole proof. Oh, this is not exactly the whole proof, right? So you still need to show that, of course, your stopping time tau is bounded, right? In the case, so we wanted to still show that like within the number of iterations t, right? So if you're running this algorithm for t number of iterations, indeed this deviation can be bounded. So that means t cannot be too large, right? In the case if we use maximum regularization, then of course this stopping time tau is just infinity, because every iteration you are enforcing that this bound holds true. But if we don't use any regularization, we want to show that indeed this stopping time tau is larger than the number of iterations you use, right? For a fixed amount of number of iterations, indeed, you can guarantee that your deviation of W is bounded. And this we can easily show by just using some standard results of martingale concentration and using again the drift analysis to try to bound the deviation. And I will not go into the details here. I'm just trying to keep track of the time here. Okay. So this is how we can actually show that the stopping time that everything actually holds with high probability that within this fixed number of iterations, indeed you can control this deviation of your network weight parameters. And that completes the proof here. So as an immediate extension, we can extend, like so far our analysis heavily depends on this IID assumption on the samples. We can easily extend this to Markovian settings using these mixing time arguments. We can, and you see that also here we are using this linear, the rectified linear unit that we use only consider a linear function instead of W transpose X plus B. We're just using W transpose X, right? You can also extend this to the case where you have this addition of affine terms, and this only leads to more extended feature vector, and then a slightly extended like a neural tangent kernel function class, and a slightly different definition of V bar. Everything will follow similarly. And the analysis can be potentially also extended to smooth activation functions instead of just this ReLU activation function. There are a number of interesting open questions. First of all, so all of these analyses are based on this one hidden neural network, right? Just a two-layer neural network structure. Can we generalize this to like multiple layer neural networks or other neural network architectures, right? If you use new layers, does this imply that you can further reduce the overparameterization complexity, right? That's kind of typically what people think is true for deep learning. And also, if you use multiple layers, do we still can we still achieve global convergence, right? It's still a non-convex problem. It's even more non-convex than before. Can we still have any guarantee in the global convergence? And in fact, this can be, and in fact, I think all the analysis like neural tangent kernel can be potentially extended to multiple layer as well. And also another interesting question is this early stopping or this maximal regularization or L2 regularization really necessary here, right? Because in practice, people don't do regularization, right? They just run TD learning or run Q learning with neural function approximation without any projection, or they run the algorithms forever, right? They don't really do any early stopping, right? Is this really necessary? So far, our analysis shows these are quite essential in order to have reduced the overparameterization complexity. And also, does this result extend to deep Q learning algorithms, right? Instead of just the policy evaluation, if you want to find the optimal policy, if you want to apply Q learning algorithms instead, does this generalize to that? And also, like we know that with Q-learning algorithms, if you use function approximation, it may not necessarily converge, right? Even if you are using linear function approximation, not even to mention like if you use neural networks. Then what are the principled ways can we design RL algorithms to integrate it with nonlinear function approximations that guarantees convergence? Right, other than using these Q-learning or value-based methods. So that will come to what I will discuss next is a family of optimization-based RL algorithms that can be easily integrated with nonlinear function approximation, and you can easily get some convergence guarantees, okay? So maybe I'll stop here and to see if there are any questions. It looks like we're all good.
I think it's crystal clear. Okay,
it's good to know because I was worried that so neural network stuff will confuse people. Okay, good to know that. So all right, let's move on then. So in the remaining time, I wanted to talk about other potential algorithms that we can more easily integrate with nonlinear function approximation. As you can see that even here with two-layer neural network, for these value-based algorithms like TD learning, Q learning, the analysis is already very complicated and very kind of hard to analyze. And So it would be interesting to see whether we can go beyond these value-based methods and derive more easier ways to integrate nonlinear function approximation. And this kind of what I would summarize as optimization-based RL algorithms. Many people don't agree with me because they think, okay, RL by itself is an optimization problem, and it's like solving the it's trying to maximize the reward to get optimal policy. But this, you'll see that how this is different from kind of the value-based methods we discussed earlier about Q-learning and TD learning. As I said, those algorithms, while they can be interpreted more or less for solving some optimization problem, but they're not really computing the actual gradient, right? It's some semi-gradient that is not really capturing the true gradient. Here, by optimization-based reinforcement learning algorithms, I'm really referring to problems where you pose an explicit optimization, static optimization problem, and you try to solve it based on gradient methods or first-order methods. So the first category, which I call it Bellman residual minimization methods, that was trying to minimize the Bellman errors. And this include many interesting algorithms like the gradient TD learning algorithms and something that I will discuss later called the speed algorithms that we proposed a few years ago. And then there was the other family of algorithms that are based on the linear programming reformulation of Markov decision processes. And there are lots of interesting algorithms like primal dual algorithms and mirror descent algorithms for solving this to find optimal policies, and those algorithms can be easily integrated with nonlinear function approximation. And there is also a third class of algorithms called policy gradient method that directly tries to maximize your long-term reward by computing the gradient over a class of policies, and you're directly trying to compute the gradient with respect to the policies directly, right? So those are fundamentally different from the value-based approaches we see before. And we'll discuss each of them, at least one example for each of them. And I would say that there are many advantages of considering this type of optimization-based RL algorithms. First of all, because they're also, like control theory, we do have also very rich literature and theory algorithms for gradient-based methods for optimization, both convex optimization or non-convex optimization, which many of you are probably more familiar with. Also, there is much easier for us to exploit off-policy data. Unlike the co-learning and TD learning algorithms, we know that they might potentially diverge with off-policy data, but with these optimization-based approaches, you will see that it's much easier to integrate with off-policy data, and that's what Bo will talk about this afternoon more extensively. And it's much easier to adapt it to function approximation. And lastly, I should also mention, I think they're much more adaptive and extensible, because all of these optimization frameworks can be easily generalized to other settings. Say, for instance, if you have safety considerations, you just add a bunch of constraints to your optimization problem. If you are dealing with multi-agent reinforcement learning, then you just pose this as distributed optimization problem, right? So it's very easy to adjust to different other more complicated scenarios. And similar, unlike before, there is also a common recipe here, right, to derive or to analyze optimization-based reinforcement learning algorithms. Oftentimes, we just treat this as an optimization problem. Either you are minimizing some loss function, or you are solving a min-max, a two-player zero-sum game problem that you want to minimize over X, maximize over Y. And then you can deploy many of the existing first-order methods like gradient descent, stochastic gradient descent, mirror descent, variance-reduced gradient methods, primal dual methods, Frank-Wolf algorithms, like all kinds of first-order algorithms you can potentially be applied to solve those problems. I'm just giving you a couple of examples, right? Say, for instance, people have been using these primal dual algorithms for policy gradient, policy evaluation, and variance reduced methods also for policy evaluation. And also there are lots of first order methods for policy optimization as well. And I would say you can easily come up or show asymptotic convergence of these gradient-based methods based on the existing optimization theory. You can also use a lot of these techniques like acceleration, variance reduction to get better performance and improved bounds, right? So those are kind of also very neat in comparing to the more control theoretical analysis. So first of all, I'm going to give you an example of this residual, Bellman residual minimization approach, right? So if you look at this, again, coming back to this Bellman optimality equation, we want to find the optimal value function V star. So in of the Q-learning algorithms, we're basically iteratively solving this, right? And as we mentioned earlier, there was this difficulty mostly coming from this max operator, because this is highly non-smooth and it often causes instability or maximization bias, especially if you are using function approximations. Okay, and here I'm going to just rewrite our Bellman optimality equation by using this policy pi, right? So instead of taking the maximum over a finite set, I'm going to take the maximum over the simplex set over a distribution, right? So these two are equivalent to each other. And normally when you encounter something like a simplex set or like some distribution, probability distribution, you think about, okay, we should be using entropy, right? Here, let's just add this entropy regularization into the Bellman equation. Okay, so here I'm just considering this coefficient lambda, which is a regularization coefficient, times this entropy h defined over your policy pi. Okay, and I'm going to call this the smooth Bellman optimality equation, or if you rewrite this, if you plug in the definition of pi and compute the max, you'll see this is nothing but just a softmax operator. Okay, so you have this very clean form, a smooth operator, log sum exponential form. Okay, and this lambda here basically controls how close your value function is to the true value function, optimal value function. I'm going to denote this as V lambda as the fixed point to this softmax operator here. Right, you can show that this softmax Bellman operator is also a gamma contraction, like the original Bellman operator. And you can show that the difference between this this new or this approximate value function is not too far away from the true optimal value function. The difference is controlled by this lambda, right? Smaller lambda you use, then the bias is small, but this will be less smooth. And if lambda goes to infinity, then this reduces to the original Bellman optimality equation. And you can also have a even simpler form of this Bellman equation by just considering both value function and the policy pi, right? So you can show that this optimal value function V lambda and the optimal policy, corresponding optimal policy pi lambda satisfies this Bellman equation below, right? The difference from the optimal Bellman optimality equation is that you have this actual logarithmic term here, and you don't have a max operator anymore. Okay, so intuitively, if you want to solve this Bellman equation, the idea would be let's just try to minimize the mean squared Bellman error, right? Just like what we did for TD learning as well. So we try to minimize the mean squared Bellman error over both value function V and pi. So notice that this problem by default is not, it's convex in V, right? Because this is a square loss with linear in V inside, but it's not necessarily convex in pi, okay? And if you solve this directly, you will encounter this so-called double sampling issue. Like if you just want to compute the true gradient, as we mentioned before, if you want to compute the true gradient, you have to compute, you need to compute the gradient of this part, right? And you need to estimate this whole thing here. So you need at least 2 independent samples from S prime in order to construct an unbiased estimator of your gradient. And in practice, oftentimes, you only observe one successor state for any given state action pair, right? You don't really have 2 samples. So you cannot really just apply, say, stochastic gradient descent to solve this type of problem. So what we propose instead is let's just consider a reformulation of this problem by using the functional duality of this square loss function. So if you apply like a functional duality of this square loss function, I can kind of extract this like inside term here outside, right? So this will then gives you rise to this following min-max optimization problem. And the interesting thing with this min-max reformulation is that now you don't have to deal with this conditional expectation anymore. You only need to deal with this joint distribution over state, action, and S prime, those triplet here. And this you can easily sample, right? You can get one sample of this and you will be able to then estimate this objective. And you will be able to apply, say, for instance, stochastic gradient descent directly to solve this min-max formulation. So the caveat here, though, is that this dual variable rho here is not a scalar vector anymore, right? This rho is going to be a function of your state action pair, right? Because if you look at this objective here, for any state and action realization, there will be a corresponding dual variable, right? So hence here, you do have a function of dual variables. And you do need to also incorporate some sort of parameterization to make this problem more tractable, rather than just dealing with a infinite dimensional continuous space here. So that is essentially what we propose, right? We can then basically parameterize your value function using some neural networks. We can parameterize pi using neural networks. We can parameterize this dual function rho with some neural networks. And then this will give you some non-convex minimax optimization. And then you can just directly use stochastic gradient descent to solve it. So the algorithm sketch that we propose is basically to say that, so if you look at this problem here, we're going to just say wrong, like say for any fixed v and pi, we are going to solve this max sub problem here to find the best rho. And then we're going to use that rho to compute what are the gradient for v and pi, and then we're going to update v and pi recursively. So that is the algorithm we propose, and we're calling this the speed algorithm, which refers to the smooth-Bellman error minimization algorithm. And you can, as I said, you can easily incorporate nonlinear function approximation here. You can also easily incorporate many of the other techniques people proposed in deep learning, like deep reinforcement learning, like experience replay, and so on. So that's what, and also you can easily use behavior policies to offline data of policy data to generate samples and to construct gradient estimators. So that's kind of a more comprehensive or slightly more complicated algorithms we propose. And we'll be able to also derive some sort of asymptotic, like convergence guarantees for this algorithm. So particularly, say for instance, so this is some experiments we did a while ago, and we compared the approach to various other state-of-the-art policy optimization algorithms like trust regime policy optimization TRPO, or this DDPG algorithm like deterministic deep policy gradient methods, and we've shown that our algorithm actually has somehow my video is not showing up here. Sorry. Okay, so there was only one video is working, the middle one. Okay, so you can see that actually it initially it actually okay, it's kind of slow here, but you can show that only after within like less than 100 iterations it was able to achieve a relatively good policy there, right? And kind of that is like just one example of this Bellman residual minimization approaches. So another kind of different approach was to using this linear programming reformulations for Markov decision processes. And from even any textbook on reinforcement learning, you will be able to see this type of primal and dual linear programs for MDPs. Particularly, like say, for instance, the primal linear program is given as the following, right? And so you have a linear objective. So mu0 is your initial distribution. And here, these constraints basically corresponds to the Bellman equations, as you can see. You can write down the dual formulation of this LP, or this actually can be also easily derived based on this definition of this state action visitation or occupancy measure rho, and this gives you the dual LP. And the nice thing with the dual LP is that this occupancy measure rho SA actually, if you solve this, if you get the optimal dual solution, you can use it to directly construct what is the optimal policy, right? So in practice, oftentimes people just direct for small Markov decision problems, people just directly just solve this dual LP, and that will give you the optimal policy pi star. For large-scale problems, of course, you cannot directly solve this primal problem or the dual problem, right? So by Lagrangian duality, we can also write down the saddle point formulation of the primal or dual problems, right? So all of these three problems are essentially equivalent. So the nice thing with the saddle point formulation is that you don't have any constraints, right? You just have this objective here, which you can actually easily draw some. You can actually use the samples from the of policies to construct unbiased estimators for this objective or this cost function here. So building on these LP formulations, there are actually many like algorithms people proposed. Say, for instance, you can use these primal dual algorithms to solve this bilinear saddle point problem, or you can use, say, a more general version of gradient descent, like mirror descent, to solve the saddle point problem as well. And in the recent result, so the way how you do with update for, say, the dual variable rho is instead of using the gradient descent, which typically you are going to use a square norm distance here, you are going to replace that by, say, for instance, a KL divergence between rho and the previous iterated rho t, right? So this is called a mirror descent step, or this actually oftentimes gives you multiplicative updates for your vectors rho. So recently, I think there were results showing that if you use this type of KL divergence in your update, or using this mirror descent type of algorithms, you were able to achieve much better complexity in terms of the dependence on state and actions. So you can also solve the dual problems directly, right? If you solve the dual problems directly, you can use, say, for instance, also you can use just mirror descent to solve the dual. This will be then equivalent to using proximal point algorithm or so-called augmented Lagrangian method. All of those are sort of equivalent, and this reduces to some of the existing studied the algorithms in the literature. The idea is also similar, right? You're going to just use some, say for instance, some KO divergence to regularize your objective. So, and the difference between these two approaches here is that here oftentimes we use a fixed regularization, whereas in mirror descent we use a much smaller step size, and where I think those are kind of some of the differences there. And you can also easily combine all of these approaches with linear or nonlinear function approximations, rather than just dealing with the tabular setting, right? There are lots of results that coming out. But the caveat here, though, is that when you integrate with nonlinear function approximation, then you will immediately lose strong duality. So the dual is not necessarily going to be giving you the exact solution for the primal problem. And then because you're using nonlinear function approximation, the landscape of the solutions are much more complicated, right? There will be many more stationary points or saddle points rather than just the global optimal solutions, right? And it's slightly harder to characterize the approximation errors because here you are basically relaxing off the constraints with function approximations rather than, so this is slightly different also with the value-based methods. Nonetheless, I would say there are lots of recent progresses in solving non-convex, non-concave min-max problems. And we now have a slightly better understanding of what are probably convergent algorithms for solving such non-convex problems, and what are the landscape of them. So those new advances in the optimization side could be potentially useful to generate new insights for reinforcement learning. So lastly, I want to also briefly touch base on the third class of optimization-based methods, which are called policy gradient methods. And policy gradient methods consider directly the original objective instead of these intermediate objectives that are derived from Bellman equations. They're just going to just consider maximizing the value functions over a class of policies pi. And assuming those policies pi are a parameterized class of functions. Say, for instance, in the tabular setting, we can use direct parameterization. So basically, for any state action pair, you can use one parameter theta to represent it. So your theta basically is going to be in some high dimensional simplex. Or you can also use this softmax parameterization by just taking this softmax form, right? So the difference between these two is that you see that the number of parameters is the same with the direct parameterization and softmax parameterization. The difference is that for the softmax parameterization, there is no constraint on theta, right? Whereas in the direct parameterization, you do have to constrain theta in some simplex. So if you directly apply this direct parameterization, oftentimes you have to do projection. You have to project on the simplex, which is slightly more expensive. You can also use function approximations. Say, for instance, you can instead of using this, you can also use something similar, softmax parameterization, but now you're going to consider, say, for instance, this linear function approximation. So this is oftentimes called the log linear policy. You can also use neural networks inside your softmax parameterization, and this is oftentimes called a neural policy, right? So the idea is basically once you represent your policies with this parameter theta, and then you just directly run gradient descent over the theta, right? So you compute the gradient with respect to theta, and then you just do gradient ascent here because you try to maximize the value function. Okay, so I have not told you how to compute exactly the policy gradient, right? How you estimate the policy gradient or construct unbiased estimator for it. There are lots of kind of approaches that you can do that. And it's kind of not too hard to see that this problem is fundamentally non-convex. So if you apply this type of policy gradient method, it may or may not converge to the global optimal solution or global optimally policy, right? So one thing that was heavily used in practice, as I mentioned in the very beginning, is the entropy regularization. As you see also in the other two approaches, like the Bellman residual minimization or the linear programming cases, we also use the entropy regularization extensively. Here, for entropy regularized policy gradient, oftentimes we just also directly add this entropy regularization into your objective, right? And then I'm going to call this V lambda pi. This is a slightly different objective, and you can also control the difference between this and the original objective by this regularization parameter lambda. And you can show that you can actually also compute the gradient with respect to this entropy regularized objective. And the gradient will be given by this term here, which depends on kind of the state action value function Q at the current policy pi theta. And also it depends on this state visitation distribution here. So oftentimes in many of the literatures, people can come up with all kinds of ways to estimate or sample from this state visitation distribution, and then to estimate these Q functions. And then you'll be able to get unbiased or potentially biased estimators for this policy gradient. And then you just do run again policy gradient on this new objective. And again, although you add this regularization parameter here, this objective is still non-convex, right? And for entropy regularized the problems, you can, as I said, you can directly use policy gradient methods to, so instead of the original gradient here, you just take the gradient on the regularized objective. So there is also the family of natural policy gradient methods where you use this Fisher information matrix to do a preconditioning of your gradient. Or you can also view this as just applying natural gradient descent to this regularized problem. And this Fisher information matrix is given by this following definition here. And one can also show that this natural policy gradient, which is popularly used, is indeed nothing but just the soft policy iteration. This is also closely related to soft Q-learning algorithms as well. And it can also be viewed as a special case of a mere descent algorithm, which I will not go into details here. I think Bo will probably discuss more in details in the afternoon. And as I said, all of these problems are inherently non-convex, but there are many very interesting recent breakthroughs on understanding the convergence of policy gradient and natural policy gradient. And many of these results shows very intriguing and also exciting results about global convergence. And particularly, there were a recent line of work that shows that if you look at just the tabular setting, right, and if you do this softmax parameterization, and in fact, if you just do this policy gradient or natural policy gradient, they will converge to the global optimal solution, although your problem is non-convex in nature. And they show that for policy gradient, you can actually achieve this 1/t convergence rate. And this can be improved to a linear convergence rate if you use entropy regularization, okay? And similar results can be obtained in the function approximation settings. Particularly, it was shown that for natural policy gradient, if you use log linear policies, then you will get this 1/t convergence rate. If you use neural policies, you can also get this 1/t convergence rate, but you will need very massive overparameterization, say something like a t to the power of 6. And all of these are showing basically sublinear convergence when you use function approximation, unlike the linear convergence case, unlike the tabular setting. So there are a number of interesting open questions, like say, for instance, what are the sample complexities or the convergence rate should be if we don't have the exact gradient, if we can only estimate the gradient through some samples. Right, so there are some recent work on this, and more details will be discussed in the afternoon. And another question is, naturally, does entropy regularization help in the functional approximation setting? In the tabular setting, you get a faster boost in the convergence, right? You can boost the convergence from sublinear to linear. What about function approximation case? So recently we had some ongoing work that shows indeed you can also get linear convergence for policy gradient if you use even in the function approximation setting. And lastly, also, can we really improve this overparameterization bound that was in the existing literature, which is like t to the power of 6, right? Which seems to be overly pessimistic somehow. And some of the analysis we did earlier for the TD learning can be potentially useful here to get better overparameterization complexity. And I was going too fast. Okay, here. So I wanted to basically, lastly, want to briefly discuss this entropy regularization, right? What's the role of this entropy regularization? I think we have seen this used in many occasions, right? In the value-based methods, like soft Q learning algorithm, in Bellman residual minimization problems, like in our speed algorithms that we use this to smooth out the max operator as well. And in the linear programming based methods, we use this extensively to optimize over the simplex set or the probability distribution set to get a better convergence guarantees. And in policy gradient methods, this was also extensively used to achieve faster convergence. So there are many other algorithms that also use or explore the entropy regularization, but they are somewhat different in nature from what we have discussed here. And the question here is really that we have seen many different evidences of many different aspects of this entropy regularization, right? In some cases, this was basically used to avoid doing projection on the simplex. It helps you to stabilize training. It achieves better convergence. The folklore theory says that entropy regularization helps you with exploration. And so I would say there is a bit of each of those in different settings, and I would say this is definitely very powerful or useful technique for this type of optimization-based reinforcement learning algorithm. So lastly, I think I should really stop here, and I want to summarize that I discussed the two parts, right, in this talk. The first part is about the asymptotics of reinforcement learning, and through this close synthesis between control theory and reinforcement learning. Second part is more about reinforcement learning with nonlinear functional approximation, different algorithms, how can we get some theoretical guarantees when nonlinear functional approximation are used. And the key message here, as you can see, that regularization is super important, both in terms of the optimization aspects and also in terms of the generalization aspects of reinforcement learning. And with that, I guess I will conclude the lecture now, and happy to take any questions you might have. And I should also really thank all of the collaborators and students in the lab for this for all of the results we presented today. And this afternoon, Bo will be talking more about how to combine reinforcement learning with offline data and online exploration. Okay.
So there is still a couple of minutes to take a couple of questions, if there are questions from the audience. Otherwise, I do have a quick question for you, Niao.
Sure,
so
yeah.
Thanks. So you briefly discussed about primal dual methods, and there have been recently many works on primal dual methods for reinforcement learning, with also a lot of solid theory. But as you also mentioned, these methods rely on duality theory and strong duality, which implies then convexity. So so far, they are kind of limited to the linear architecture case, right?
Mm-hmm.
Do you believe this to be a major limitation of this class of methods, or do you believe that there are ways to extend those with more advanced theory tools to also handle the class of nonlinear function approximators? Because at the end, it's there that somehow we would like also to go, because of the all empirical evidence of the success stories of this reinforcement learning agent when used in combination with these powerful parametric approximations.
Right. I think that's a very good question indeed. And you see a lot of numerical evidence, not only in reinforcement learning settings, but also in, say, in other machine learning applications like training GAMs, generative adversarial machine learning, right? So of those, actually, you have to deal with these min-max problems using primal dual methods over like massive amounts of like large neural networks. And just surprisingly, for many of these applications, people do observe like global convergence, or oftentimes they are able to actually recover the optimal solutions, right? So I think first of all, it's still a very viable approach, although theoretically speaking, you might be losing the duality, strong duality there. But I think it will be interesting here to consider, like, when would you be able to establish strong duality, right? Like maybe with enough overparameterization. Say, for instance, something similar as what I discussed for the neural TD learning case. If you use two-layer neural networks for the primal and for the dual, and they are approximately going to be just a bilinear problem, which has some hidden convexity there, right? So that might be able to alleviate the issue with the lack of strong duality, or maybe you can show something there. So I think those are in general very interesting open questions, and they would be very perfectly suited for a PhD project, right? Uh-huh.
Yes. Many thanks.
So maybe I can also ask a question. So I have a question regarding the LP approach that you presented. So I do understand that it can be used to model the underlying MDP problem, right? And then it gives rise to different algorithms that have been presented using the LP formulation as a kind of starting point.
Mm-hmm.
However, also somehow it seems that the LP approach is quite fundamentally different in the sense that it's kind of a one-shot problem, right? So you don't solve something iteratively, you just have a, like a static optimization problem, you solve it, you get your optimal policy.
Mm-hmm.
So now what's your view on that kind of modeling framework? Like, is that, so when would you consider this as a useful kind of problem modeling? Because it seems like, so sometimes, like doing something iteratively, like the value iteration, policy iteration seems much more powerful instead of, like putting everything into one single optimization problem and solving that in one shot.
Right. So, so I think that's a very good question, first of all, and I would say, even in the tabular setting, in the very classic theory, we know that solving this LP formulation actually is much better than the value iteration or policy iteration. So first of all, you can show that because with a linear programming formulation, this is actually a tractable convex program, right? People can actually show that you get a strongly polynomial convergence, polynomial complexity for solving this LP. Whereas if you do value iteration, you get linear convergence, but those are not necessarily strongly polynomial algorithms, right? So solving LP should be much faster than the value iteration, policy iteration, if you know the underlying dynamics very well. And that is actually what people normally use in practice to solve small scale MDPs, right? The interesting question is then, like, is this amenable for function approximations? There are also lots of, I think, papers on approximate dynamic programming in the classical literature, right? I think it's not any worse than all the value-based methods like value iteration or policy iteration. And I think using this optimization or LP formulation, it really is it's kind of, because I think both of them are boils down to this Bellman equation, right? Both of them are derived from Bellman equations. So that's also is a very interesting question, is like, there are so many different ways of formulating Markov decision process, so many ways of formulating an optimization and objective to get the optimal solution. Then which one is better, right? What should be the right objective? What should be the right loss function? What should be the right optimization problem to start with? I think that's not very clear at the moment. What should be the best thing to do? I think there was also a recent work that I think I mentioned it in one of the slides that considered this logistic Q-learning, and they were basically proposing different loss functions, different objectives, rather than the mean squared Bellman error. They were using some logistic-based Bellman errors. So I think there is a large room of research, open questions there. Yeah.
Mm-hmm. Cool. Thank you so much.
Are there any other questions from the audience? Otherwise, well, we'd like to really thank you a lot, Niao, for the really nice and interesting lecture that you gave, and also for having endured all these hours of lecturing. Many thanks. And for further discussions, we will use the Slack channel. So we have a dedicated channel for Niao and all our lectures. And then we will continue this afternoon at 2 with Bo Dai and his lectures on offline reinforcement learning methods and more. Many thanks, and see you in the afternoon.
Thank you for having me, and I will try to also join the Slack channel and just see if there are any other questions. Feel free to ping me on Slack, and if you need any further references, just feel free to let me know. Okay, and thank you very much, and see you in the afternoon. And yeah.
Thank you. So 2 p.m. for the people who ask, 2 p.m. in the Europe time, Berlin. So thanks. Okay, welcome back everyone to the second sessions of this first day of summer school. As I told you this morning, this first day will be a really full immersion in reinforcement learning. It is my pleasure to introduce Bo Dai. Bo is a senior research scientist at Google Brain in Mountain View. He obtained his PhD from computational science and engineering at Georgia Tech under the supervision of Le Song. Bo Dai is currently very active in the machine learning community, as he is co-author of many publications in the major machine learning conferences. In the past 2 years, he also has been a guest lecturer and invited speaker in many different universities, conferences, and research centers, such as the SIAM Conference on Optimization, Facebook AI Research, DeepMind, and the University of California, LA. His research interests comprise learning to design algorithms, large-scale non-parametric machine learning, and reinforcement learning. We are really excited to have Bo Dai as a main speaker at this summer school, and we are very much looking forward to his lectures on reinforcement learning methods. In particular, he will focus on offline reinforcement learning and reinforcement learning with exploration. Many thanks, Dr. Dai, and the floor is yours.
Thank you. Thanks, Mathilde. It's my pleasure to give a talk here. Yeah, I'm Bo. I'm from Google Brain in Mountain View, and actually here right now it's 5 a.m. So you can think I'm just have a. You can consider I'm just have a very jet lag. Okay, so today I will give a brief talk about part 3 and part 4 of this mini course, which is offline reinforcement learning and optimization-based reinforcement learning and exploration. Actually, the similarity of these two parts is that all of these two, the content in all of the two parties most related to optimization. So we will see that how optimization can play a very important role for design reinforcement learning and help us to have better algorithm. So because this is, I know this is a control related emphasizes audience. So if you have any questions, just interrupt me, and I'm very happy to answer the questions. You know, this is a 4-hour courses, so it's a long time. So don't hesitate. Don't worry. Okay, let's see. The first part I will talk about offline reinforcement learning. And actually, here you will have we propose a very coherent framework, and you will see literally how optimization can help us to handle reinforcement learning. So I don't know when I should read the slides. I don't know whether I should read this part, but because Niao told me this is a control conference, so I think it's better I have something here. It's like a very, very basic introduction about linear programming and Lagrangian dual. Roughly speaking, we call the can you see my mouse? Okay, great. Roughly speaking, we call this part as primal LP, which is because it's a minimal problem, which basically we minimize the object function, which is linear, and also the constraint itself is linear. And we always assume the solution exists, which means the problem is feasible. So that means it corresponding has the dual. And the dual problem corresponds to maximize some linear optimization with respect to a linear constraint. And you can see that actually this B corresponding to object function B prime, B transpose, and this A corresponding to this A. And the reason why we have such kind of optimization is that we can get it from the Lagrangian dual perspective. Roughly speaking, we have this Lagrangian as min-max optimization, which could be written in either this form and this form. And because we assume this primal form is always have a feasible solutions, that means AX bigger or equal to B always satisfied, which means consider you are trying to minimize something. This is negative, this part. And if Y is smaller than 0, this part goes to, you see, infinite. So which means it cannot have any solution. So that means we need to restrict the Y bigger or equal to 0. That's why we have this constraint in dual LP. And similar, if we return into this formulation, we know that x must be bigger than 0, and we are trying to sorry, we are trying to, let me see, maximize y. So which means we cannot have this component to be positive, this component to be positive. Otherwise, it goes to infinite. So we should make this component smaller than equal to 0, and which corresponds to A transpose Y bigger than C. So this is how we derive this two constraint in dual problem corresponding to LP, primal LP from Lagrangian perspective. Yeah, this is basic linear programming and Lagrangian dual. I think what I will, most of the case in this lecture, we'll just use this simple cases. So if you have any questions or have any, about this part, so you can raise the questions now. Okay, great. I didn't see anything here. And let's pause here and come to a problem to say why we need offline reinforcement learning. Actually, Niao already introduced a lot of reinforcement learning, but in that style of reinforcement learning, it have interaction between the agent and the environment, which means every time you train an agent, you need to use the agent to interact with the environment to get data from there by executing your current policy, and then collect the data to train your agent. And this is this loop is iterated, so on and so forth. We noticed that this style of reinforcement learning actually have some limitation. For example, we notice, let's give a concrete example here. In the dialogue generation in chatbot, you want to train a chatbot, which means it will reply your questions or have a chit chat with a human. If you run this kind of, if you train such kind of thing interactively with human, you will see basically you need to hire a lot of people every day to interact with some agent which output randomly at the beginning, meaningless. So you see, this is insane, and it's hire a human could be very expensive in this case. And in another case, it's like a self-driving car. At the beginning, your driving policy can not guarantee there's maybe have some bugs. So if you just throw this kind of thing into the car and let it drive in the highway, you will see it's so dangerous to everyone. So basically, sometimes we really don't know, we really don't want to directly use our agent to interact with the true environment because it's maybe unaffordable, expensive, or maybe cause undesirable disaster. So in such kind of scenario, the good thing that motivates us to propose this kind of offline reinforcement learning. Let's see what is concretely offline reinforcement. I think this this above figure gives us a very concrete example and to distinguish the offline reinforcement learning to the online reinforcement learning. The first part actually is Euro reinforcement setting. You see, the agent every time is interact with the environment and then collect the data to update itself. And this is iterate, so on and so forth. As I mentioned, this is sometimes impractical. So what we propose called offline reinforcement learning is that some agent which you trust collect the data for you. And the agent itself is only not interact with the environment. It is invisible to the environment, but only interact with this kind of logged interaction or collect the data. So that's what we call the offline reinforcement learning. I hope this gives you quite significant difference between these two kind of reinforcement style. If actually when I present this kind of stuff to many people previously, people will raise questions about how to distinguish the off-policy reinforcement learning to the offline reinforcement learning. So that's why I list the 3 figures here. Maybe you heard about offline reinforcement learning. And let's see how it's distinguished to the offline reinforcement learning. Actually, in offline reinforcement learning, we didn't prohibit the agent to interact with the environment. In another way to put it, actually it can interact with the environment to collect the data with your agent, with your current agent. And it will collect the data into a pool, which sometimes we call experience replay buffer, and so on and so forth. And the data collected in this pool maybe not just collected by current policy. It can collect by, say, like 1,000 step previously data, such kind of thing. So that means this buffer not just include current policy, the data collected by current policy. It can also collect the data. It can also save the data, which collected by say like pi 0, pi 1, so on and so forth. And then you use this data buffer to train your policy. And this is called off policy because the data is not only collected by current policy. But you see, on the other hand, this is our offline reinforcement learning, which means there is some policy collected data, and your current policy, your policy to be trained cannot interact with the environment. It can only interact with the buffer collected by other policy. So this is the significant difference between the off policy and offline. Always remember, in offline reinforcement learning, you only have data. You don't have the chance to interact with the environment. So this is what we want to emphasize before we go through the technical detail and algorithm, how we solve this kind of problem. Okay, so I hope we are clear about the setting right now. Okay, great. Let's keep moving. Okay, so here's some here's some notation revisit. I think you already see the slides in Niao's lecture, and I just want to emphasize that we will still work on MDP. And you have, sorry, I noticed there's questions. I think it's better to interrupt me. Anyway, I will read it. So the question is like, if we update pi beta with the new pi in order to explore and drift to a better policy, it's not offline reinforcement anymore. Yes, that's true. Roughly speaking, in our previous slides, this pi b or pi beta actually is not visible to you. Let's give me another concrete example. For example, sometimes when you only have data, and sometimes who collect data it's not known to the learner. A very concrete example is like in recommendation system, there is a policy collecting data for you, and sometimes it's just a human or just a human rule, such that encodes the prior knowledge about this kind of recommendation knowledge. And you never can explicitly written down the mathematical formulation for that. So this is one way to say you don't know the pi beta. Or even worse, sometimes in the scenario, you only have data. You even don't know who collected that for you. Another example is like in chatbot. What you observe is a bunch of the dialogue interaction, and you don't know who is interacting with who. You don't know which one is agent. It could be both human. Okay, so I think we are clear about this setting. Okay, another question is the difference between online and offline. Okay, so online is like it never have this replay buffer. Every time you currently have your policy and you interact with the environment, you collect the data, and with this data collected from this pi k, you update your pi_k to pi_k plus 1. And after that, the data collected during this procedure is thrown away. And you do this iteratively again and again, update your policy. Remember, you never save the data. After you use the data to collect your, to update your policy, it is abandoned. And that's the significant difference between the on-policy or online reinforcement learning with the offline reinforcement learning. Okay. Okay, finally we will reach the notation side. I don't think I will read every notation here, but remember we keep the same focus on discounted infinite horizon setting. And yeah, this is the procedure of the MDP. Every time you have the state and you execute a policy, which A0 from some sample from a distribution, conditional distribution given as it will give the A0. And then the environment give you a reward R0 based on current state and action. And then your state will move to another next state by this state transition distribution. And this procedure iterates, so on and so forth. It could be goes to infinite long. And also this slide is also very familiar with you. This is what I copied from Niao's slides. When Niao trying to solve the reinforcement learning, she just transferred the problem. Actually, the two core problem in reinforcement, one is called policy evaluation, the other one is policy optimization, to solving Bellman equation or Bellman optimality equation. Okay, that's a traditional way to solve reinforcement learning. Today, in this lecture, we will go through another way to view the reinforcement learning. It's not directly goes to the Bellman recursive equation, but look at this, what we call the policy value. Roughly speaking, it is expectation of the accumulated reward. So like this goes to infinite long, and you have R0, R1, and this gamma, as if you remember the notation, it is a scalar to do the discount. So this summation from T0 to infinite, gamma T RT, basically it's the cumulative reward for one trajectory. And this expectation is saying, because there are so many random things here, say like this initial distribution and the action and also random reward and random next state, so on and so forth. So there are so many random things here. So definitely one trajectory is not enough. We take expectation for that. And because this is executing this pi by sample action from there, so we call this as the policy value. So then we can see that the policy evaluation is just trying to evaluate this quantity, and the policy optimization is trying to say, okay, I have this policy quantity. I want to find the policy pi such that maximize this quantity. That's what I wrote here. Let's see, this is two core problem. And in the setting of the offline reinforcement learning, as I mentioned, we don't have the environment, we only have data. Okay, the data is read as a lot of trajectory from I to M, and each one is the trajectory from S0 goes to S. It goes to infinite, but the S prime R is random variable from the distribution, and A is executed by a behavior policy. And I would like to emphasize that, as I mentioned, in some scenario, we don't know who collect data for you. So in that setting, we call it, we don't know pi0, so we call it behavior agnostic offline reinforcement learning. And in this scenario, the offline policy evaluation will be, say, like, give the data set, and you want to find an estimator we had, such that it can approximate based on this data and also the knowledge of your policy. You want to make this quantity as a good approximator for the policy value, which is defined in previous slide here. Okay. And so the policy optimization is, as I mentioned, say like you want to justify the maximal policy, which we call optimal policy. Okay, actually, I want to emphasize why it is difficult, because look at the difficulty actually comes from you cannot access to the environment but only the data. If you say you want to do the policy evaluation and you can access the environment, actually this estimating this quantity is like a Monte Carlo approximation, right? You execute this policy along the MDP and collect the trajectory, and do say like n times sample and do average, you will get a quite good approximation for this one. But this is offline reinforcement learning. So you don't know who collected the data for you, and you have no access to the environment. So that kind of idea is not executable here. It's not applicable. So that's basically the major difficulty in offline reinforcement learning. And beyond these two core problem in reinforcement learning, actually there's some other kind of side problem, which is like offline imitation learning. It's imitation learning. It seems like you don't want to do any thing related to reward, but there is an expert behavior policy. And you just want to make sure you learn a policy such that the behavior of your policy matches the expert. So this is what we call imitation learning in offline setting. So same, you don't access to the environment, but only data, but you still want to finish this task. That's what we call the offline imitation learning. And sometimes you don't want, as you notice here in policy evaluation, it's only a number, right? And you know, as the definition there's so many random things. So in some cases, only an expectation value is not enough. So sometimes we want to estimate a confidence interval for this quantity. So that's what we call the policy confidence interval estimation. And in this setting, we call it offline. Yeah, I noticed please go ahead.
Yes, so I had one question. So the reward function, is that you assume that this is known, or you only have sample access?
Yeah, I only have sample accesses to it. As I mentioned here, it's a distribution. It can sample from it, but I don't know the detailed number.
So the exact reward function is also not known? Huh?
Yes.
Okay. Thanks a lot.
No problem. Yeah. So you see there are so many problems, and in this talk, I think I will give a brief introduction to what we have done in past 2 years. We propose a framework which can solve all this problem in a quite consistent way. And I will use the policy evaluation as a building block and a case study to give a brief idea how this kind of thing derived, and also introduce the rest of them. So, okay, so if we don't have questions, we will move to next slides. Okay, great. So as I mentioned, in the offline setting, it is really difficult because you cannot execute the policy. So in 20 years ago, people think we can introduce the important sampling to do it. Right, that's a good idea, because you see, you don't know sample from here, but you don't know sample from here. So what you do is you just reweight them and do the important Monte Carlo approximation. The duration of this one is quite straightforward, but actually there are two major problems. One is because it's restricted to a setting where you know the behavior policy, which means you know who sampled it, and this must be known. And also, this must be a probability policy. Otherwise, if this is deterministic, you see, this is not doable. Okay. And the second part is the most terrible part. Actually, the variance of this estimator actually increase exponentially with respect to the horizon. In another way, if h goes to like 100, you basically cannot trust your estimator because the variance is so huge. Okay, the reason why it is so huge, actually intuitively you can thinking this is multiplication, a sequence of product. Okay, and we written it as exponential summation log ratio. And if you assume this part is bounded, it directly gives the exponential h times c. So that's the quantity of the variance. So it will kill you right here. So people notice this kind of phenomenon, and there are several efforts trying to combat with this kind of difficulty. So for example, the doubly robust estimator, which is very known technique. I introduced some baseline to do variance reduction. Yeah, it's very popular and proposed by Miro Dudik and Nanjiang Li Hongli. But in worst cases, the curse of horizon, we call it curse of horizon, is still not eliminated. Okay, this is the vanilla method before what we propose. Are we clear about this classic method? Great. Okay, next, from this slide we will introduce what we propose. So before we dive into the detail, let me first define some quantity. Bear with me, it's not too many. Okay, what we are interested in actually is this quantity. It is expectation. And so we define a quantity known as stationary state action occupancy, which is, you can roughly understand this as you execute your policy on this MDP and you count every step, every t time step, you count the distribution along the margin distribution, and then you do a discounted average, and it gives the distribution. Roughly speaking, that's a stationary distribution when you execute this policy on this MDP. And if you run long enough, it will give you it will stop on some distribution. So that's stationary state action distribution. And if you know this quantity, you can represent the policy value by expectation with this distribution with respect to the reward function. It's only one step, and you don't need to accumulate anymore because accumulation is already done here. Okay, so this is what we noticed. It actually is very important in later our algorithm derivation. So we transfer from expectation of accumulation to expectation with respect to a single stationary distribution. Okay, now let's see what happened later. And okay, there's actually by definition of the stationary distribution, we can have a similar Bellman recursion here. Let me derive it for you. So we know this is the definition of the stationary data action distribution. And we do one step expanded. Okay, so it's from 0 to t equals to 1. Okay, and then we expand this part. Okay, we expand this part. It will gives you because this t equals to 1, so we say okay, t from 0 and give me next state. So this component will comes out, and that rest part will be t equals to 1. And remember, by our definition, this component will be stationary distribution. Okay, so it gives you this characteristic recursion about the stationary distribution. Okay, it's quite similar to the Bellman equation, but if you look at the Bellman equation here, you will see this is integrate out of the past, but in the Bellman equation, it's integrate of the future. So it's like you will see it's actually primordial to each other. You will see later. Okay, okay, we are clear about these slides. Now we have our major component to derive the linear programming reformulation of policy value. So as I mentioned, we can have, if the D is the station distribution, which means if D satisfies this condition, we can represent the policy value as expectation of the expectation of reward with respect to this distribution. Okay, so when we solve this optimization, it gives us the policy value. Okay. Remember, as we introduced in the first slide, this is linear programming, and its maximal can be understood as dual LP. So we definitely have the primal LP part. Okay, this is the primal LP corresponding to this LP. You'll notice, if you look in carefully, you notice something very, very familiar with everyone. So what's this? This basically is the Bellman equation. Okay, but slightly different here is I don't need to find a solution which is exactly equivalent. I just find something bigger than that. It's enough because the object function will push my Q to make sure Q equals to the right hand side. You see, the object function is minimized. So it's pushed this thing to the smallest Q value to satisfy this condition. So that will say Q equals to this right hand side. So you see, indeed, this Bellman equation and the recursion relationship to this station distribution is primordial to each other. Okay, now we have our basic tool for solving this offline policy evaluation from here. Definitely you can not directly solve this optimization because 2 points. First one, this expectation is with respect to distribution of the current policy. You don't have data for it. That's one reason. And second one actually is this is for arbitrary state action. There are too many constraints. Say like if your state is continual, which is very common, and this constraint is infinite many. So definitely cannot solve it. So how we deal with that? Actually, we introduce the Lagrangian part. Okay, by Lagrangian, you eventually represent the constraint into expectation part, this part. Okay, but still, there's one more step because this is expectation with respect to the on-policy sample because this D. We don't have any sample from there. Remember, keep it. So we only have the offline sample. But don't worry. Actually, IPS gives us a very good idea, which is use important sampling. So we use important sampling, but we don't use important sampling with respect to the policy itself. We use important sampling with respect to the station distribution. Okay, this DD is the basically you can think this part is offline data. Okay, and this is what we want. And then with this kind of stuff, we have this object function. You see, from here to here, I just do a important sampling. I've replaced this D to this DD, but introduce the reweighting part. Now we have every component, every expectation is approximatable by current data set. And so from here, I can use stochastic gradient or stochastic approximate stochastic average approximation to solve this kind of optimization and get the solution. Okay, I noticed the questions. What is zeta? Or maybe you can raise the question directly because I need to switch.
Sure. Yeah, I wanted to ask exactly what is this zeta because I didn't understand.
Yeah, the zeta is like the in important sampling. If you sample from a base distribution, but you want to approximate to another distribution, you need to do a reweighting, right? That is my zeta, which is the distribution ratio.
Okay, is it chosen by the user?
Sorry?
So is it chosen by the user?
Oh, I see your point. Actually, it will be optimized this part. There's a typo. It's not maximize D anymore. It's maximize the zeta.
Ah, okay. I see. Okay. Right. Thanks.
No problem. So we call, actually based on this relationship, we developed several methods which we all name as sum dice. We call it dice family because it's short for the stationary distribution correction estimator. Okay. For this paper, its original, it's derived first dice, but actually it's not deriving this way. If you look at this paper, it's very tedious. The derivation is so, although eventually you came this formulation, but the derivation is so complicated, you will miss somewhere. And later, this one generalized the method to the discounted, from discounted to undiscounted method. And finally, this paper actually is for, eventually we understand from the linear programming, it's much, much easier. So that's how we eventually come out this framework. Okay. Oh, I forgot to mention something here. In this formulation, actually, there are, as I mentioned, the first thing is it's applicable by SGD based on current data set. And also another benefit is that it's naturally compatible with the neural network because you can parameterize the, sorry, it's not D anymore, it's zeta and Q by any neural network you prefer. Okay, it's not changing the estimator. It's naturally incorporated because it's optimized. You just do min, max, min with respect to the parameter of the neural network. That's good enough. And another benefit, actually, although it's not very significant, but you will see later it's very important in some application, which is you are estimating the ratio. While a lot of methods focus on estimating the Q function. Actually, the ratio itself is independent with respect to the reward function, which means you can, this method naturally applicable to the sparse reward MDP. But the Q-based estimation, for example, LSTDQ, which is very famous before DICE, is backing up the reward. And let's give a very, very extreme cases. You only have one state, which is 1, and the other state are all 0. Basically, it's not doable in the Q-based function because it's the reward is too sparse. Every location is 0, almost, right? So, but that's not a problem in here because for example, in this relationship, there's never corresponding to the reward. Reward only eventually comes out when you use this estimated ratio to do policy evaluation. So in your backup, actually in your estimation of the D or ratio here, you don't need to worry about the reward is sparse or dense. It doesn't matter. You will see an application later when this is important. Okay, so I think I mainly finished the major component of the dice, but we will see something here. Anyway, before I go through here, any questions?
So I would have a question actually. So in this box that is actually now on the second box on this slide, right? So you have the expectation on the second line, right? So this is the second expectation. This is with respect to the transition kernel, which you don't know. So will this expectation? So you assume that you can kind of approximate this expectation with.
I see. I get your point. Remember, we have a sample like S prime, A prime from here. Yes. This part is never changed, right? If I sample from here, this is data, and then maybe I should go back to what the data looks like. Okay, here. Right, the data is given you as, you can thinking S0, A0, and also S1, A1, S2, A2, and so on and so forth. Okay, you basically have the average, like, you can think this is cutting to tuple, say like S, A, R, S prime. Okay, so you have sample from S prime. Now come back to the estimator here. Although I wrote it into expectation, but you have sample SA reward function, SA reward S prime. And this A prime is from your policy, trying to estimate it. So you have another A prime from your target policy. So roughly speaking, this is linear, so you can extract this part outside, and every expectation can be approximated by samples.
Mm-hmm.
So that's a benefit. That's what I mean. Each term is approximatable by data.
Mm-hmm. Mm-hmm.
Okay, great.
And that's why. So that's basically the punchline. Why you don't need to know the transition kernel, right?
Exactly. I don't need to know. I don't even need to interact. I don't need to even sample from it because I have already a lot of data from there.
Mm-hmm. Thank you.
Okay. So we have 10 more minutes. I hope I can finish the first component. Okay, so actually, we, based on that kind of basic knowledge, we introduced several components for regularizing. For example, this component, it's regularize the Q function. Okay, because this is statistic. So we know from statistical machine learning theory, when you just do the unregularized, it's not good enough. So we need to introduce some regularizer here. So this is regularized for the Q function. This is regularized for the ratio. Okay, and we even notice that because, as I mentioned, D is not depends on R. So sometimes you can eliminate it. Say set alpha R to 0. It doesn't matter actually. You will see this from this table later. And also this lambda is we're trying to emphasize that, trying to enforce the ratio to be a valid ratio, which means the expectation D, sorry, the expectation DD with respect to the ratio equals to 1. So if you incorporate such kind of constraint by the Lagrangian, it will automatically have this lambda here. Although I didn't mention in the derivation. So this is how we have this kind of regularized here. And from this table, we carefully profile every combination of different setting of this for regularizer. When we bold it as unbiased, which basically it's not unbiased because space is not enough. Actually, it is asymptotic consistent, which means if I have infinite amount of data, the solution will be unbiased. So but the biased part is not. We mainly focus on the unbiased part. Biased part is not good enough. So, which means even you have the regularizer, you still can choose some setting in some combination in this table to make sure your solution is good enough. I mean, unbiased, asymptotic unbiased. And we also notice that after you obtain the Q and obtain the ratio, there are several ways to do the policy estimator. One is we call it deal estimator, which is at the beginning we just do reweighted expectation with respect to reward. Another one is like a vanilla thing. You do the expectation with the Q function. And because these two are all unbiased, you can combine the two together. And also remember the Lagrangian itself is unbiased estimator. The Lagrangian itself, after you solve it, actually the solution itself is equals to the solution to primal and dual. So it is another estimator. So that's how this three estimator came out here. Are we clear about this part? Okay, so you can find this table and how we derive it in this paper. It's not showing here, but you will see in the reference. Okay. Yeah, here.
Sorry, might I ask a question?
Sure.
So the first question is, what exactly is this F1 and F2 functions?
Oh, F1, F2 are just two convex function. Roughly speaking, for example, the L2 norm is a good example. It's convex, so that's we sometimes use for regularizing. It's not, some norm is not good, large.
And the second question would be like on the previous slide you had for the Lagrangian, the first expectation was with respect to S0 and A0. So why is that exactly? Because before it's not with it's with respect to.
I see. Let's see how we derive that. So actually, it's come from here. Okay. When you're in the Lagrangian, you time this one with Q function here and Q function here, right? So you see this component will automatically give you that you need to take expected back to the initial state.
Okay.
Okay.
But then in the regularized version, it's. Yeah,
regularized version is not. It's not. Actually, it doesn't matter. Actually, to be honest, not that matter. But we didn't regularize it with respect to initial. We regularize it to a whole collected data.
Okay. Thank you.
Okay. Good. So here, I don't want to go to this one. This is saying with this understanding, we can formulate a lot of existing methods by setting different by different regularized combination. And actually, this is what we proposed, and this is proposed by Nanjiang and his student. And this is very famous LSTDQ proposal, which is actually a standard state-of-the-art method before our method. And this is what we empirically found performs the best, which we call the best dice. Okay, I think that's how this slides. What's this slide trying to say? Now, let's see the real performance. Actually, we have more experiments in the paper, but let's just look at this simple case, which is richer in the module setting. Module is the current benchmark for reinforcement learning. So we want to do a policy evaluation. And this module, this richer is saying like the policies control this arm, and eventually you want to have this green dot end of this arm to reach the target. And as I mentioned, it's offline. So we compose the policy like this. This pi b is some policy. And this pi is what we want, the target policy, which we want to estimate the policy, which we want to estimate its value. So the alpha is like you tell how much is similar to your target policy. So here is alpha 0, alpha from small to bigger. So it makes this sampling policy becomes more and more similar to your target policy. Okay, we compare our method with some TD method, and also important sampling, which is basically in IPS method, as I mentioned before. And this red dot line is the true value. As you can see, when we increase the number of samples, the proposed method, actually, no matter alpha from 0 to alpha becomes alpha bigger, which means the policies, the behavior policies become more and more similar to the target policy. The method performs, our method performs very close eventually to the true value, but the other one basically failed. It's just because the variance is too large. You cannot control it in this case. Okay, this is empirical study. Okay, now I think I'm on time to finish my first component. Yeah, any questions? Good. Okay, then in next session, I will discuss a little bit about the property of this dice family, especially answer the questions whether it still border from the curse of dimension or not. And also, I will introduce how this method could be applied, how this method could be applied to a real problem, which is have the sparse reward. Actually, Mathilde, I was wondering, I'm not sure. should we stop
Yes.
here, or we can keep going and eventually have a 20 minutes pause?
As you prefer, we could either have a shorter pause now or continue and have a longer pause later.
I don't know how the students think which one's better. I'm fine. I'm fine with it.
Generally, they like more shorter pauses, but it's yeah.
Okay, then we can stop here. Yeah.
Then okay, then let's make a pause now and reconvene in 10 minutes. Okay.
Yeah, great.
Okay, great. So let's see each other at 3.
Mm-hmm. Sure, sounds good. Let's.
Awesome.
Okay, so since we don't have any questions about my major algorithmic part, let's go to the major questions we want to answer. Whether this method breaks the curse of horizon or not. Actually, that means besides the empirical super performance compared to the IPS method, theoretically, whether we solve the curse of horizon problem. In another way to put it is whether the variance of the certainty, whether the variance of the estimator is polynomial with respect to the horizon. And actually, the answer is yes, and it's even better. Let's look at this theorem. And theorem, if the total, if the total reward is bounded. Actually, here's a little bit subtle. If you just think the reward function is bounded, then eventually the bound will depend on the horizon. Okay, but in another way to put it, if we say the value of the policy is bounded, it means it's independent of h. Then we can cancel 1h from the results. So let's assume just the value function of value itself is bounded independent of h, which is very common in practice. That's what we call total bounded reward. And another assumption is a little bit, actually it's something what we are doing right now, but let me explain that to you. Another assumption is called data coverage, which means for every state action pair. I know this is a little bit restricted, but anyway, for any state and action pairs, you need to make sure it is visited at once. It is visited. So in another way to put it is, at least your data covers all the support of your distribution of state and action pairs. So we prove this theory in a tabular case, but I think in our paper we extend this one to the linear mixture MDP. But anyway, let's come back to the tabular case. So in this case, under this two assumption, we can show that the estimator, which is denoted as V hat, compared to true value, actually eventually absolute value is in the ratio, in the rate of 1 over square root of KDM. So K is the number of episode. In this case, for simplicity, we didn't consider the infinite horizon. We only consider the finite horizon. But I think there's a relationship between the finite horizon and the discounted MDP by changing factor of the horizon h to 1 over 1 minus gamma. But anyway, let's in this particular setting, it's fixed finite horizon with h, and then you can see this bound. It's not depends on h. It's a little bit weird, but if we throw away the assumption, say it's the total reward bounded, it's gone, but you only bound the reward, and then there will be a h in front of this. There will be a h here. So, but anyway, in either case, we say it's not exponential with respect to h, it's polynomial. So in this case, you can trust the estimator or not? No. Okay, this is the theoretical part of showing that indeed our estimator is it's better compared to the IPS. Okay, I will next we will have several slides trying to introduce how we prove this kind of stuff. I mean, proof sketch, but make sure the high level idea is carefully bound the variance and also utilize the recursion structure in the V function, in the value function, when you bound this kind of policy value here. And and what I want to emphasize is that this algorithm also achieves the lower bound of our policy evaluation. And this is quite new result in our paper on archive. In there, we both proved we have detail for this theorem and also the lower bound proof. In this talk, I will not talk about how to prove the lower bound, but only this upper bound proof here. Let's start. First of all, we prove, actually this is known to many people, but we formally say that in this tabular case, the algorithm from the dice family actually is equivalent to a plugin model-based estimator, but it's only valid for the tabular case. So that gives us benefits that we can estimate the plugin estimator instead of complicated optimization. Okay. Here, in another way to put it, is we have a closed form of the solution. So you don't need to worry about optimization anymore. And then another important lemma is that value difference lemma. So which means I give you a policy and the true value of your policy compared to minus the estimated value by this plugin estimator could be written in this formulation. Here, C hat actually is the station distribution estimator. In other words, compared to my previous slides, it could be understood as D hat. And this I hat is estimator of the reward function, and this P hat is estimate of the conditional distribution or transition distribution based on the data. And the proof of this one actually is quite simple but tedious. How we get here is by definition of this V and definition of the V hat and expand it and also use recursion. I think I will not introduce how we exactly get here, but remember this is some important lemma we want to from. Based on this lemma, we change the original object function to this part, and then we can bound each term in this thing and eventually get the solution. That's the basic idea. Okay, how? Let's see the first component, which is very simple. It's one step. You don't need to consider this VH thing. It's just one step. So in here, we call it error from the reward estimation. And it's easy. We utilize the Bernstein inequality. Okay, before I proceed, do I need to introduce the Bernstein inequality? Okay, fine. I just briefly introduce it. It's like a probability inequality, which trying to distinguish the estimation of your expectation from data and true value with respect to the finite number of your samples. Roughly speaking, that's called. There are so many such kind of probability inequality, but we utilize Bernstein inequality here to get this bound. Okay, this is one component, and the difficult part actually came from the second part. Second part actually is super tedious. We denote this part as delta 1. We throw this away. So this component is delta 1. This is what we call total variance. And we try to bound this term. If you just simply apply the probability inequality here, you will not get the optimal dependence to H. It's just because this is summation of h. So if you simply bound this term, definitely there's some h here, right? So that's not good enough. And remember, so that's why we go to another strategy, which we first rewrite this using a Cauchy-Schwarz inequality. So we have this term, variance term. And then we apply the Bernstein. So we eventually get this part. And now what we need to do next is we bound this term instead of here. The reason we bound this term instead of here is because we have some recursion for this v function, for this variance function. So that's the magic thing here. We didn't use, so remember, we didn't do here. We changed to a upper bound of this quantity. The reason we can bound this upper bound with some quantity optimal with respect to the h is because we utilize its recursion again in the variance bound. Yeah, I know this is tedious. Actually, it is tedious when we prove it. So you can see here, we denote v1 equals to this one. You see, this is exactly the thing here. Okay, and then if we I equals to say 0, it is exactly this term. Okay, but we want v1 0, but we notice there's a recursion relationship like this. v1 I smaller equal to square root of some constant here, and v1 I plus 1. So that's what we call the recursion structure in the variance term. And with respect to this constant recursion, we can solve this recursion and eventually gives you v1 0 is in this order. Okay, I know this is tedious, and before I move to next slide, any questions about this part? Okay, it seems like silence, but I really want to emphasize that if we want to achieve the optimal dependence with respect to h, you cannot simply go from here. You cannot do that. You need to utilize still Markov recursion structure in your variance term, and eventually it gives you what you want. Okay. And from with this and plug back into the original term, you eventually get the delta smaller than square root of kd. This eta actually is some log term. Actually, you can basically throw away and becomes O tilde O square root of kd plus 1 over kdm. Okay, so we have this term bounded and also previous term bounded. Now we have this two component, and this combine these two results, we get what we want, and we finish the proof. Yeah, I know this is tedious, and I only give you a brief introduction, a brief sketch of the proof. So, any questions about the sketch, proof sketch? Okay, so then let's move to a real application of our method. In this application, we really want to do a policy evaluation, dialogue evaluation, which means you want to evaluate some agent which really solve a problem. Let's make a very concrete example here. the agent itself is having it's a air ticket booking agent. Basically, it's interact with the customer, and the customer is trying to communicate with this agent to book a ticket, and then during this conversation, you can see the agent expressed his intent, and the customer expressed its intent, and the agent looking to the database to eventually fulfill this order. And if this task is completed, we say the reward is 1 because it's a successful booked. And if it's not, we set this reward is 0. And you see this is indeed a sparse reward, because during this whole procedure, there's no reward assigned. Eventually give a 1. Okay, you can think during this whole procedure until you reach here, it's all 0. And particularly concretely in this setting, we formulate into MDP first. And basically that means we want to match action state and transition. Action state transition from here for this particular application. Let's see what's it. What's wrong with my laptop? Okay, so in this particular application, we said action A is just the agent response, and the state is the conversation history. And as I mentioned, the reward is just a finished task or not. It's very sparse. And the transition is given current conversation history and the feedback from the agent. The human will have some reaction. Okay, this gives you the basic component of the MDP. And by this construction, we reformulate the dialogue evaluation to policy evaluation. Okay, great. So we are clear about the problem setting and how this one is transformed to the policy evaluation problem. Okay, so let's see why it's difficult. As I mentioned, in this setting, the reward is super sparse. And because you only obtain the reward at the end of the dialogue. During the whole procedure, you'll never have any guidance. And another difficulty actually is because the conversation actually have varying horizon, finite horizon, which means you cannot directly use the dice or whatever algorithm for infinite horizon MDP, because in this setting, you don't know where it ends, when it ends. It maybe ends in 3 or 5 conversation or even longer. So the data set is quite different. And also another quite difficult part is that the state action space is computationally large, because we have humans have very large vocabulary size. And each sentence is combinatory from this state, combinatorily picking from the vocabulary to compose the sentence. And then in our setting, the state is the history of the whole conversation. So you'll see it's combinatory. So eventually, actually, the state space is already large enough, right? And the action is composed sentence is also large, which means in this setting, no matter how many data are collected, it seems impossible to satisfy the data coverage assumption in our theory and method derivation. So this is 3 major difficulty in applying the policy evaluation to evaluate dialogue. So, okay, so let's see how we beat each of them one by one. First of all is that, as I mentioned, that's estimator is independent with respect to reward. You don't need to worry about the sparse reward anymore, because when you're estimating the density ratio, it's independent with respect to reward. And the reward eventually only used for compose with the ratio to get to the policy value. So it doesn't matter to estimating the ratio. But the Q-based method, for example, STDQ, which is the state of the art before, it's highly sensitive to this setting. Okay. And the second one, we say the conversation is finite horizon. Don't worry, we propose some method to do that. Basically, we call it pseudo-state padding. You will see what's that later, very soon. And when we want to handle the complete large state, we introduce some function approximator. Basically, it is robotize the language model. I'm not sure because I know this is a control-based community, so you guys know about language model, right? Okay, I will have several sentences to explain what it is. You may be heard about a lot recently about BERT or GPT-3 or so on and so forth. This model trying to, you can thinking that this model is like first to extract a feature representation of the sentence, and then use this feature representation to predict next words to generate the whole sentence for sentence generation. In here, we use one model, one particular language model, but we throw with the language generation part. We just use the feature extract from this model as our function approximation part. I hope my explanation is clear to you guys. Or in another way to put it, just neural network extract the good feature. Is this clear? Good, good. I think this is quite some side words. I think this part, this language model is recently very exciting progress of machine learning for NLP. And if you are interested, you can read a little bit about this one. Okay, so let's see one by one how we deal with it. First, we'll discuss about the pseudo-state padding. Okay, this, as I mentioned, in this application, we really don't know how long it is. For each conversation, the T could be varying a lot. So for example, in this case, it's finished after this big T step. And then we said, okay, we will not stop here. We will add more pseudo state from T+1 goes to eventually T max. Okay, so by this padding, we eventually make sure every conversation eventually have the same length, but it's still finite. And then we say after we reach this T max, we sample from we goes to beginning and sample from the initial distribution and do it again. So this goes to iterate and many times. So basically, this one goes to infinite long. Okay, so by this pseudo-state padding, we eventually get a augmented MDP. It's different from the original MDP because now in this augmented MDP, it is infinite horizon. Okay, and but then actually after this padding, the very natural idea is that very natural question is that whether this padding is valid, which means after this padding, whether our dice is applicable. That's one question. Another one is whether this value or policy value on this augmented MDP still can generate original. Let me rephrase the sentence. I'm a little bit sleepy. Whether the original policy value on the varying horizon MDP can be recovered from your execute the policy valuation on this augmented MDP. That's the second question. Actually, we provide the confirmative answer to both of them. First one, we prove that you can see this definitely this augmented MDP is not ergodic because it's periodic. This is cycling, right? But even that will show that there's a unique stationary state action distribution, which means we can utilize the dice estimation now. the proof of this part actually is quite simple. We just construct, we just find it in our paper. We just find it and verify it is the station distribution. And secondly, we show that the policy value in this augmented MDP is rescaling. Sorry, here's typo. It's not recalling, it's rescaling the original value by Tmax. So that means after you estimate the policy on this augmented MDP, you just divide the value with Tmax. That's good enough. That's the best. That's the original policy value in the original MDP. And then in the coding part, actually, we didn't do this padding. Oh, we didn't do this padding. This is only do it conceptually. Okay, so it's not introduce any actual computational cost. That's what I want to emphasize. Okay, I think this is pseudo-state padding. Because you guys don't know, quite familiar with language model, so I will not go to the detail here. Just remember, the language model is used here for feature extractor. You can think this part as a very, very large neural network to extract the feature from this state, this combinatory state action, which means the sentence. You use neural network from sentence to extract a feature. And this feature will say like, for example, either go to a linear model or go to neural network to eventually parameterize your zeta and the Q function. So here's not V, it's the Q function. That's, remember, in our dice, so in our dice, it's it goes too fast. In our dice, it's this two component, this zeta and the Q function. And we utilize a very good feature so that you don't need to worry about, you literally cover every state action. You are in the feature space right now. Okay, so let's see. We already finished the major technique to combat the difficulty in applying the outpolicy evaluation for this dialogue evaluation. Let's see how it performs. Okay, before we go to the real comparison, we just do ablation study to see the effect of sparse reward. And here we call this method INGMA with we replug the LSTDQ, replace the dice. So you see, because it's sparse, the performance now is far away from the true value. And these are two agents, and the dollar is their true policy value. And this is what LSTDQ gets. And now here is we use dice, and you can see the we converge to the true value very quickly. Okay, so that gives intuition. Also give a very straightforward illustration that this sparse reward indeed affect a lot in different algorithm. Okay, so next is a very boring table. You don't need to read the detail number here, but remember, we compare to the state-of-art policy, dialogue evaluation method. And for this air ticket booking agent evaluation task. And this is correlation number. The larger is better. And you see our method achieve the state-of-the-art compared to model-based one. The cell play is model-based evaluation, which first evaluate a human. First, actually, here, environment is a human. So you need to first model the human and execute your policy with respect to the human. So you see, that is not very good because human is very difficult, very complicated to model. So our method don't need to model the human. So it achieve much better performance with respect to current state of the art. No matter Pearson correlation or Spearman rank correlation. Oh, here is another illustration. Say, we we visualize the correlation between the solution and the true value. And this slope is 1, the closer to 1, the better. And also the data point here close to this horizontal 1 is the better. Oops. And compared to our method in the first row and the model-based one, you see the variance is very huge. And also this line is more close to the line with slope 1. So that means the dice family actually performs quite well compared to the model-based one. Okay, I think I just finished how we particularly apply this method to a very difficult real-world policy evaluation problem. Okay, we'll stop here and any questions?
Yeah, excuse me.
Yeah, sure.
Can you hear me? Yeah, it's okay.
Yeah, I can hear you.
I have a question about the data coverage, and especially when we have a policy that do not explore the environments very well. So meaning that we have states that are not covered. So when we evaluate a policy that is not the same policy as the behavior policy, so if this policy go towards states that are not visited, that means that our offline policy evaluation will give bad results, right?
Yes, yes. Yeah, that's actually the thing I'm trying to, I'm not trying to bypass, but trying to mitigate by utilize the language model to extract a feature. Actually, your worry is very valid. Actually, that's also our worry, concern at the beginning when we initiate this kind of project. We know what we collect the data is not sufficient enough. So there will definitely a lot of state and action, which here is a lot of conversation we never observed. So we utilize the language model to extract a feature such that as long as the feature is similar, we sort of have some ability to mitigate such kind of difficulty. But your worry is definitely valid. I would say even with this kind of language model to extract feature, there's still some difficulty to generate some policy which is too far away, in the sense that their station ratio is too large. It's still very difficult. I totally agree with you. Yeah.
Okay. So when you use your offline policy evaluation to find out a new policy, you use some optimization process to find out?
No, actually here we only finish the policy evaluation, which means the policy is fixed. We're never trying to improve it. We just want to have, say like, give a quantitative score to each policy so that we can compare to which one's better. We never say we want to improve that policy along this offline data.
Okay, I got it. Thank you.
But actually, you raised very good questions. I will cover later, which is the offline policy optimization. Yeah. Any questions about this part? Okay, so then let's see next part. I think here, as I mentioned, we propose a very consistent, very unified framework to not only handle the offline policy evaluation, it also can be generalized for other kind of task with this kind of perspective, with this kind of optimization perspective. So in later this session, I will talk about how we can use that dice family do the offline policy optimization. And later, maybe in next session, I will also talk about how this method could be applied to other tasks like offline imitation learning and offline confidence interval estimation. Yeah, I put offline confidence interval to last because it's quite difficult. Actually, we'll consider that problem for a while. But anyway, let's first focus on how we can utilize this method for offline policy optimization. Okay, actually, this kind of extension is not that difficult. Recall, the policy optimization task is that we want to eventually maximize the policy value, right? Now we already have good estimator for the policy value, as I mentioned, as the dice family, which is this term, right? If you still remember, this is Lagrangian form, and if you solve it, it just gave me the policy value. And what do you need to do? Actually, it's quite straightforward. Maximize it, right? So this is intuition and also the idea to do it, but there's some difficulty if you just straightforward do such kind of stuff, because this is offline data, and you really don't want to say like direct optimize this one, because sometimes if your data is not good enough, for example, some support is not covered sufficiently, then what you optimize here actually will not trustable outside of the data domain. So we introduce something here. Oops. So we introduce regularizer here. This minus alpha expectation df zeta. This f actually is a convex function, as I mentioned. And let's proceed. And let's see what this regular indeed trying to do. Okay, ignore this two box. Actually, this regularizer is equivalent to a F divergence between your stationary distribution and the data you collected. This is not too difficult to derive because this is the ratio. And let's see if this is negative log. And if this is ratio, so you plug the ratio d pi over dd here, and it is negative expectation dd with respect to log d pi over dd. So obvious, it is the KL divergence. So that this effect of the this regularizer is indeed trying to restrict your stationary distribution, not go far away from your stationary distribution. Actually, this is what we want, because as I mentioned, if your data is not very covered, it's not covered everywhere, you really don't want to go that far. And actually, this philosophy is not only applied here. Recently, there's a lot of batch or batch reinforcement learning paper which just introduce a different regularizer, but still follow the same spirit. Constrain your policy, not go far away from your data. For example, the BAC and a lot of recent paper just trying to do this. Some paper use the KL divergence. Some paper use MMD, maximum mean discrepancy, and so on and so forth. But naturally, this can be very efficient, convenient to incorporate into this stats framework. So you just introduce this regularizer. You don't vary too much, and also maximize this pi. Okay, this is if you want to look into the detail, just refer to this paper. Okay, I think until now, I think I finished the object function for offline policy optimization. And let's look at the property of this object function. Actually, before we achieve the conclusion, I will make a claim that the gradient of this object function with respect to policy is a policy gradient. So in another way to put it is that even your data is not executed, it's not on policy, it's not executed by yourself, it's collected by other behavior policy. You optimize that object function, what you get is an unbiased estimator for your policy gradient. Let's see how we achieve that. We take a gradient with respect to pi, and let's see where pi shows up. Actually, it shows up in this box and also in this box, because this A0 sample from pi, and this A prime is also sample from pi. And the rest of the component in this object function is independent with respect to current to pi. It depends on d and zeta, but it's independent of the pi. Okay. And after we solve the optimal for this max and the min, there's a theorem, or there's a lemma called Danskin lemma. So which means you don't need to worry about the dependence with the d and the q with respect to pi. You can treat it as the optimal part is independent with respect to this pi. So when you calculate the gradient, you only calculate the gradient for this two terms. The rest of the term is, you don't need to worry about that. Is this clear to anyone, to everyone? Okay, and then let's proceed step by step. And remember this zeta, after you solve it, actually it's d pi over dd, and then you plug this part into your expectation. This is what you get. Okay, so here's mu pi and here's d pi. And I reorder this term and extract the partial derivative outside of everything and recall this relationship. Eventually, what you get is like this. Okay, and here you can see I do one more step, log trick. Okay, I will introduce log trick later, but believe me, this is what eventually the gradient. Okay, I will introduce the log trick in the policy gradient family. It's in section 4. And here, believe me, this is eventually what you get. And we call it policy gradient. And it is indeed what we want. So this is quite interesting. You just use the offline data, but eventually you still get unbiased estimator for the policy gradient with respect to unpolicy sample.
So sorry, wouldn't this mean that we can do policy gradient, which typically is online, via instead offline data, so in an offline fashion? Yes,
exactly. But I hide something here.
Okay.
The thing I hide actually is you already noticed that in the proof condition, in the assumption of the theorem 1, which is saying I really need the data coverage. See, I can handle the distribution shift only by the mass shift. But if your data say like just restrict to some domain and the other domain is not observed, I can do nothing. I think this is not only restricted to this method. Actually, this is also the problem of the statistical machine learning. In the vanilla statistical machine learning, the best you can do is just predict over the support of a distribution, right? You can never do out of distribution prediction. But we do here we say by this important sampling, we can handle a little bit about the distribution shift, but still not go beyond the support.
Thanks.
Okay. Any questions about this part?
So basically, if I try to translate it again to understand, so the behavioral kind of data that you have, like this D to the script D, right? So this needs to visit all potential state action pairs.
That's true.
That's kind of a hidden assumption, and otherwise you could not say anything about the xi function there.
Exactly.
Okay.
So essential. This is about, let's say, in the important sampling. If your proposal is very bad, it not cover the whole support, your estimation is very bad. So this is the thing. This is the problem of this important sampling. Okay, I think we are clear about this optimization part. Actually, here's some similar results for policy optimization. We still under the assumption that total value is bounded, not reward is bounded. I mean, total value is bounded, and also data coverage. We can still have the difference between your optimal policy value. I mean, the policy you obtain from data compared to that value with optimal value is still in this rate. It's similar rate. The high value actually is quite similar, and you just need one more step to decouple the error. And this is difference from here. And we introduce the stepstone. This is V hat, which means you estimate your optimal policy on the data. And compare this two components, definitely this one is smaller than this one. Otherwise, you will pick pi star instead of pi hat star. Okay, remember you are doing maximal policy evaluation, maximal policy optimization. So this term is smaller than 1. So these two terms are the left. And this first term, we call it error on fixed policy because it is policy evaluation of the true optimal one. So with theorem 1, we can bound it, right? Remember theorem 1, this is do a policy evaluation basically. But this term is actually, it's a little bit tedious. I don't want to look into detail, but remember why it's tedious. I just explain why it's tedious because both pi hat and the v hat are dependent on your data. You need to carefully handle the dependence in this two terms. But here it's not because you see the policy is given. It's never related to your data. So it's just a policy evaluation, but here it's not. So we need some actual effort to make it eventually bounded by this term. But good thing is this term in terms of the sample is not the leading term. So it's a high order term. Don't worry about that. But it have some dependence with the state. So anyway, it just looks like this. Yeah, I think this also gives you a illustration. This kind of method actually performs quite well in terms of the horizon. Definitely under the assumption, theoretically. And now let's see, we really do some empirical study to verify our method performs quite well. This one is a famous 4-room synthetic data. So this is starting point, and this is target point. This is I don't remember which. It's actually t from 0 to some number, but I don't remember the concrete number of t equals to which one. But you can think this just we execute our algorithm iteratively again and again. We just pick 4 of them to give an illustration of the whole algorithm procedure. This arrows is say the policy, represents the policy. And this shadow part represents the Bellman arrow. So eventually, the Bellman you can think that this basically guides you which what's the optimal policy you get, and eventually you can see here that's quite a good policy already visually. And also, we definitely compare with some state-of-the-art model-free algorithm like soft actor critique and TD3 and DDPG on the module code. We just pick 2 examples here. One is called worker 2D, the other one is humanoid. And the blue line is ours, and the rest line corresponds to our competitor. You can see the corresponding here. We don't say we beat all of them, but we are comparable with them. Yeah. So yeah, this is the empirical study. Okay. Any questions? I think still on time. Yeah. Any questions?
So I have a question if nobody else has a question, which is like where is the size of your state and action space entering your kind of error bound on the previous, like before your empirical study, you had like this kind of, approximation errors on the cost evaluation, right? So yeah. This DM, I guess, like this depends on the size of the state and action size.
Yes.
Pairs. So because I'm wondering, like later, if you can use like this method to do kind of a policy optimization, right? So I'm wondering where the curse of dimensionality will pop up. Yeah?
Good questions. Actually, in this setting, we didn't observe that. It's linear with respect to state and action. And if you say curse of dimension, we can think that the state is a discretization of say like RD. And this S will represent as exponential with respect to the curse of dimension.
Okay.
Because this is tabular, and here S represents number of state. So I think this term shows up.
Yeah.
But with careful analysis, average dependent, I think almost this is optimal. But I don't know whether this is optimal or not. But in terms of leading term, in our case, it's achieved the lower bound already.
Yeah.
Yeah.
Excuse me.
Sure.
I don't understand. How do you get your results with Mojoko and the empirical results? What kind of policy do you use for get your data?
Oh, for this one?
Yeah.
Good questions. Actually, in this paper, we're still executing the off policy thing. We still, but it's a little bit different. We say like we still, after we train for a while, we still use this one to collect the data and use that. You can think of this as our policy, but we didn't collect data that frequently. We describe the detail in our papers.
Okay.
If you want to ask particularly for current moment, people use what kind of behavior policy, or what kind of behavior policy to collect data? I think, let me tell you, they just execute some algorithm for a while and then use that algorithm, freeze that algorithm, collect data, and use the data set to train the rest of the algorithm. This is particularly, I think there's a benchmark collected by Sergey Lavin, and this is what they're doing. Okay. Any other questions? Okay, good. I think I will stop here. And the next session, it's a little bit hybrid. I will introduce, still apply our method, apply our framework to imitation learning and confidence interval estimation, and also give a summarization. And if time permit, I will start the policy gradient convergence proof. And there we will see what is the log trick. Okay, cool. And let's start 10 minutes later, which is, let's see.
It will be 4:04 for us.
Okay, it will be 7:05.
Okay, good.
Yeah. I'm really sorry, I'm a little bit sleepy. So when I have some misspelling or miss thing, just remind me. Okay.
No, don't worry, it was perfect. See you.
Yeah.
Okay, but if you are also ready, we are ready to restart.
Yeah. I just come back. I just find the unmute button. Okay. So let's see what's next. Okay. Oops, where is it? Okay. Now, next, still, oh, wait a second. Before I start, I just want to make sure. So this session is still like 15 minutes. So it ended up like, yeah, so anyway, let's start. So in this session, I will still keep going to apply our framework for other kind of offline imitation learning. So other kind of offline reinforcement learning task, like here, we just apply this framework for offline imitation learning. So as I mentioned, usually imitation learning is that you are given a lot of expert behavior policy, and you want to make sure eventually you find a policy such that the policy performs similar to the expert behavior policy. So simple, like still this constraint. Basically, you want to find a stationary distribution of the current policy, but you change the objective function into, say, like minimize the d pi with respect to dd. dd you can think now is expert behavior policy. Roughly speaking, this is ensure that your policy will behave similar in terms of stationary distribution to the expert. So quite simple, right? Still with everything similar, Lagrangian formulation, important sampling, and eventually it came out like this formulation. Quite straightforward, right? So yeah, nothing too much after you understand what we have experienced before, this optimization and policy evaluation. So quite simple. Yeah, okay, let's see next. Okay, here I don't want to show the empirical study, but if you're interested, please refer to this paper. Okay, next is a little bit difficult one, which is offline confidence interval estimation. As I mentioned, previous estimator, for example, the offline policy evaluation estimator, only give you a point estimator, which means every time you have a single scalar to approximate expectation. But sometimes we know the confidence is important. For example, a lot of people in offline policy optimization, they don't maximize the point estimator. They maximize the lower bound estimation of the point estimator of the policy value due to some justification reasons. For example, robustness and so on and so forth. But anyway, I just give an example that where the confidence interval estimation is useful. So then it raises the questions, how can we estimate such kind of confidence interval with offline data? One straightforward idea actually from statistics, very simple. I give you a data set, and you construct data set by resampling from the original data set to construct a lot of sub data set, say like DI. And for each of them, you run the dice estimator on this data set to obtain one point estimator. So remember, you run that m times, so you will have m different estimators. And now you just compute the variance based on this estimator, which and you can plus them and minus them to perform as both upper and lower bound for the confidence interval estimation. This is called bootstrap. But major problem this one is it's sometimes too expensive. You know, every time you need to solve a min-max problem, and it's m different set, so you need to run m times. So it's not very good. So the nature question is, could we have a better way to do the policy offline policy confidence interval estimation, which is more computational preferable in a more efficient way in terms of competition? The answer definitely is yes. That's what I will represent here. But before we go there, let's first check versional representation of the lower bound. I first explain some notation here. So this C is some scalar, and this Sn square is the variance of your estimator. This Z is some random number, and it is taking expectation with respect to sample. So this part is the empirical sample estimator, and the S are just the variance of this estimator. Okay, this is just a saying with you solve this optimization, and this can be represented as lower bound because you see you move this side here, it's bigger or equal to expectation minus this square root of variance. And also you move this to here, it's upper bounded by expectation, your empirical variable, your empirical estimator minus some quantity which is related to your square root of variance. Roughly speaking, when you solve this one, it gives you quite a good estimation for expectation plus its square root of variance. So actually this quantity is used a lot in distribution robust optimization. Okay, and also it's highly connected to estimator called empirical likelihood. But I'm not going to that detail, but remember this is just a special, this optimization, it's just a special representation of expectation, empirical expectation minus square root of its variance minus standard deviation. I provided some proof sketch here. So let's denote U as 1 over n minus W. So I can rewrite this object function in this formulation. So instead of optimization W, which belongs to a simplex, I focus on its 1 minus n minus W. I do a variable change of variable. And particularly, this df, f divergence, is utilized the chi-square, which f belongs to, f is x minus 1 square. So with this plugs into this optimization, I eventually get this optimization. And then we can see we achieve the maximum over this part by Cauchy-Schwarz inequality, which gives you this optimization, this upper bound. And it's achieved this upper bound if and only if we know it's unified distributed like this formulation, like this. Okay, and then we need to make sure it belongs to the feasible set. So yeah, this part is ensure we have U belongs to 1 over n. So this together gives us the right-hand side of the upper bound. I just plug this in back into here, and eventually, yeah, expectation minus what you have here with this quantity is smaller than or equal to square root of the variance, basically standard deviation. I think this lemma is used quite a lot in the distributed robust optimization. Okay, and for the right-hand side, it's also not difficult to prove because we assume they belongs to Z is bounded, and previous conclusion is come from the condition that this one always satisfied, which means we always have square square of s bigger and equal to this quantity. But if it's not, we immediately have this count. If it's not, it's saying, okay, if it's not, this part is 0. So definitely you minimize W in this simplex, which means you pick the smallest one among this Z, and it's definitely smaller than your expectation, empirical expectation. So this gives you the left-hand side inequality. And now this basically gives you the variational representation of the lower bound. And similarly, we can also have a similar formulation for the variational representation of upper bound. Instead of maximize weights in the simplex, you just do maximization instead of minimization here, which gives you the expectation, which approximate the empirical expectation plus the standard deviation. And actually that is what we want, right? Which means if you have some estimator and you don't do this empirical estimation, but you find some weights in the simplex while it's not far away from the uniform distribution on this data set. And then it will give you a variational, it will give approximation for both lower bound and upper bound by either do minimization over this section or maximization over this section. So based on that understanding, we have this quantize for offline confidence interval estimation. How we deal with that? Remember, we have L, which is the basically considered as Z in the representation here, this Z. And then you introduce this minimization over the reweighting part. Instead of use uniform sample, you do minimization in this simplex. It will give you lower bound. Vice versa. Oops. Here's the typo. It's not minimization. This should be upper bound, and this should be maximization. What I have done. Okay. This basically gives you both lower bound and upper bound by switching in this reweighting on the observed data set. Okay, until now, are we clear about the quantize formulation? Yeah, any questions about this one? Okay, good. And then we basically, actually this proof is quite straightforward if you understand that, okay, what we observe, what we optimization actually is approximation of this expectation plus or minus this square root of variance. And then you utilize some probability inequality, for example, this one from the Marot and Portil 2009, and it directly gives you this confidence with high probability. And you don't need to worry too much about what else. So I think this is quite straightforward. If you have that kind of you understand that optimization actually is a variational representation of lower bound and upper bound. It's not difficult. It's quite straightforward. Okay, until now, I think I finished the how we can use this kind of dice family for offline confidence interval estimation. and also provide a theoretical guarantee. And next, I will definitely to show the empirical performance of that algorithm. Before I start here, any questions about this part? Method and also the theoretical guarantee. Okay, silence. It seems like we don't have questions here. Oh, everyone is totally lost. I don't know which one. But anyway, I assume we are on a good track. And now let's see the performance. Okay, so we compare to some existing method, which is bootstrapping. And there's also existing method you directly Bernstein with IPS. IPS, remember the inverse propensity score method, which is basically doing important sampling with some Bernstein correction for the upper and lower bound, and also student T, which is a asymptotic method, still based on IPS. Let me explain a little bit here. The figure is not clear, but let me explain it. So we tested on two environments. One is called frozen lake, also from the OpenAI G for reinforcement learning, and the other one is taxi, which is a simulator quite applied, which is quite popular. The upper row actually is trying to evaluate the quality of the confidence interval, which this black dot line actually is expected how many times the estimator should cover, how many times your confidence interval should cover the ground truth. The closer your curve is to this dot line, the better it is. You see the confidence and the x-axis actually is the 1 minus alpha percentile. So the larger it is, you will feel more confidence about it. But correspondingly, this bottom line is the width of the confidence interval. So the larger it is, the wider it is. So that's understandable. And you see, our method is much closer than competitor to this black dot line, which means the confidence interval get from coin dice is better in terms of the coverage rate. And later, the bottom line is actually the log width of the estimator, which means the smaller, the better it is. And compared to the rest of the competitor, our method achieves the smallest confidence interval, which means our estimator is both tighter and accurate. Yeah, that's how to interpret this empirical study. Okay, so if we don't have any questions about this off-policy imitation learning and off-policy confidence interval estimation, we will go to a summarization of this offline reinforcement learning design method according to this primal dual framework. Actually, we already see many problems can be recast as an optimization and then utilize the regularized form and the important sampling ratio formulation. We can solve it only according to the offline data. So here this part shows algorithm, which means we have several papers along policy evaluation, policy optimization, policy imitation learning, and offline confidence interval estimation. And this side is several papers for theoretical guarantee for these algorithms. Yeah, for particular paper, actually it's listed in the reference in the end of this slides. Until now, I think we finished the section 2, and here comes the summarization of the section 3. As we already observed, the optimization, especially the linear programming reformulation, actually provide a unified framework for offline reinforcement learning. And meanwhile, it helps us to establish better statistic and optimization property. And also, you can see based on this framework, we can design a lot of principal data efficient reinforcement learning algorithm. Meanwhile, it's very easy to compatible with the neural network on other kind of nonlinear parameterization generalization into the algorithm. But still, there are some open questions. If you notice what I introduced, I never mentioned how I solve the min-max problem when listed. It's just because if it's convex concave, we know everything. And if it's neural network parameterized, well, I'm not saying we don't know anything, but we know very little. So that means we need a relatively look into how we can solve such kind of stochastic approximation problem in the form of a min-max optimization. This is quite difficult. I know Niao, Professor Niao is an expert in this area. So yeah, but still a lot of problem is still open. Yeah, the second part is still related to this one, especially when we use neural network into the min-max formulation. We know statistical property for that, for the optimal solution, but we don't know how to achieve that. It's a little bit awkward. Okay, finally is something I'm personally not very satisfied, which is the data coverage assumption. As we already noticed, in all the theory approved and all the theoretical guarantee, we always need such kind of assumption because we are restricted in the, we are utilize the tools from the statistical machine learning theory, which can only gives you the generalization on the same support. Although there could be some distribution shift, but the distribution shift is limited to the scenario where the support is the same. But in this setting, it's naturally that you may collect the data not sufficient to cover everything. What can we say beyond this data assumption, data coverage assumption? Potential way to deal with such kind of stuff is we can explore some causal inference method, relies on your model, relies on your assumption. And I think this is, although it's not very satisfiable, but it's still reasonable. Why? Let's give a very, very hand-wavy argument. You know, human, and Newton is the top scientist among humans. And he discovered the Newton's dynamics only based on part of the observation. But it can generalize a lot of scenario which much beyond the observation he observed. The only reason is that the model is good. The model is perfect, almost perfect. I think same thing here. You cannot require too much beyond the, say, you cannot require too much for the algorithm beyond the, you don't have any assumption about the model, right? So I think potentially we still can incorporate some prior knowledge into this setting, say even the data coverage not enough, but you still have a good model, you can still say something. That's, I think, something could be interesting, especially for the real world application people. To be honest, recently we are suffered from such kind of assumption. We don't, in practice. Okay, I think roughly that's part 3. And before I go to part 4, any questions here?
So just to be sure I understood, in the algorithms you discussed, you use a min-max formulation, right? But in the empirical part, you always use neural networks as parametric approximator. And indeed, I mean, wouldn't that break, as you just said in the last open?
Yes.
Break the whole framework somehow. So it works good empirically, but is for now is a bit of a brute force from the theory side, right?
Yes.
Okay.
That's what I mean. It's still open.
Yeah.
To be honest here, you can definitely utilize the kernel and or linear model, and everything still, I'm not saying fully covered by theorem, but still covered a lot by theorem. I'm guaranteed a lot by theorem. And the feature, I mean, linear model, the feature part, actually you can extract, I mean, you can split this into two stages. One stage is you extract the feature, okay? And then you use this feature for parameterization. And so eventually in your model, in your optimization, in max formulation, it's still linear parameterized and convex and K. Everything's perfect and everyone is happy. That's one way to, that's a lazy way to avoid such kind of problem. Another one, as you mentioned, is definitely we really want to incorporate the neural network into the parameterization and learn it end to end. We not just train the final layer, but we still train the feature extractor simultaneously. This indeed is something very difficult. We only achieve empirical success by mimic again. We actually borrow a lot trick from how people train again.
But in the application that you saw, I was thinking about the one with the extraction of these words embedding these language models, right? There it seems that indeed these neural networks prove to achieve superior performance thanks to this, right? So having somehow to avoid that probably we would need to pay a big price empirically, so to say, in terms of the performance, maybe.
Yes, actually, I skipped that part. If you go back to my slide there, it's like a combination of pre-train and end-to-end training. Actually, the language model is not just say you random initialize it and then plug into the parameterization. It's done. It's not in that way. We to get a reasonable representation here, we first pre-train the language model on Wikipedia wiki is, I don't remember the number, Wikipedia dataset. I think it's Wikipedia 18K to get a quite good initialization for feature representation. And then last layer is like a linear W transpose this phi as A.
Okay.
And then when I train it, I'm not just train the W here, as also train this representation. So it's like a hybrid. It's not to say I totally fix this part on the linear, nor I use them randomly here. It's like I could have good initialization, which is pre-trained, and then end-to-end train both the final layer and this part.
So you use a sort of warm starting, but since you keep training the nonlinear component, you have a non-convex kind of element in your optimization, which makes it, which still brings us to the issue that you were discussing.
Exactly.
Okay.
That's exactly how I did it in the experiments. But I think you raise a perfect questions. This questions is, I don't think it's easy. I mean, when you introduce the neural network, what can I say about it? What can I say about optimization? Although I didn't mention anything here, but it's still open.
But from your plot, it seems that this, I mean, if one is able to use the proper theoretical tools and fix this kind of open question, things seems to work nicely, actually, right?
Yeah. It's like empirical work, but theoretical we don't know.
Imitation learning. I mean, it's clear to me already by the cost function that you minimize, right? Since you take like the F divergence, right? You have this absolute continuity assumption. This immediately like gives rise to this data coverage issue. But so how about one would change this objective function to something that doesn't suffer from this absolute continuity thing, like a Wasserstein distance between, you know, like the behavioral kind of policy and the one that you optimize over. Could this be a way to kind of relax this data coverage assumption?
I don't think so. And I know your intuition, because the versus and distance basically give you a transport between data to data, right? So
yes.
your intuition like this will give the better way to avoid the ratio here. But I'm thinking that even that, I still think that we cannot say too much about beyond you don't have the data coverage. The reason is because eventually, we need the data to approximate the expectation in my constraint.
Mm-hmm.
So I don't know if it's totally beyond. I really don't know. See how this expectation. You mean? I mean, so as I mentioned, in important sampling, if your proposal is bad, so yeah.
Yeah. Okay, so it's really kind of there must be some additional prior knowledge you can build in to say something beyond like the data points you covered. Yeah.
Exactly.
And this is not so clear. What would that prior assumption look like or be?
Exactly. Recently, we really want to look into this data coverage in the aspect saying, if we want to achieve such kind of, if we want to collect data to guarantee satisfy this kind of assumption, how many data we need?
Mm-hmm.
The result is quite interesting. I didn't cover here because we just submitted to NeurIPS, and it depends on how you sample.
Mm-hmm.
Let's say we distinguish sampling method into two different styles. One is, say, you can basically you have the generative model. You can do restart, which means you can sample from anywhere. You can acquire sample from, say, I want to have sample SA, and what's next, so on and so forth. This is what we call it path independent, because it's just what I want it to do, right? In this setting, it's not that many. You just need a polynomial with respect to data and action pair. But if you use really execute a policy on particular MDP, and even the policy is universal. I mean, sorry, not universal, uniform for every action on every state. The number of samples is terrible. It's like exponential with respect to the horizon. It's straightforward because let's give a very concrete one. You have a chain, and each chain there is one separate state. So if you want to cover everything, definitely it's 2 to the h, right?
Mm-hmm.
So intuitively, that's the scenario. So what can we say? So that's why I'm thinking potentially one way to avoid such kind of assumption is we go to the representation part.
Mm-hmm.
That seems like lying in between of you require a particular accurate model and the data coverage.
Mm-hmm.
So you have a representation, and in the representation, everything is covered. You're fine. You don't in this setting, you don't need to worry about your model is accurate. No, it doesn't matter, right? You don't need to do that, but you still have a good representation. I think this might be a promising direction. And recently, my colleague actually tried this empirically. He didn't learn a model, just try to learn a feature. And in that setting, actually, eventually, the performance of the offline method is even you use very naive one, say like the behavior cloning for imitation learning. We know theoretically it's debate, it's unbounded. I mean, the guarantee is there's no guarantee for that. If in traditional setting, but even you use that with a good representation, you still have pretty super performance empirically. So this makes me think that learning a good representation might be a good direction to avoid such kind of data coverage.
Mm-hmm.
This is what I'm thinking about this assumption. And it's echo what Mathilde mentioned. Oops. Where we can potentially separate this into two stages. And the first is it's just seeking for the good representation. After that, linear model is enough.
Good. Yeah, thanks a lot. Thanks a lot for sharing.
Okay, we almost done with part 3. And I think we still have 1 hour and roughly 1 hour, 50 minutes and 10 more minutes here. I don't want to state the detail of part 4, but let's give a high level what I'm trying to explain in part 4. Part 4 actually is I will explain major component of part 4 is I will explain a recent result we obtained for global convergence of policy gradient method with softmax representation of the policy, while with here's a little bit awkward with full gradient, with exactly gradient. So that's what I will cover mainly in part 4 about optimization based IL. And also I will cover a little bit about online exploration. That part is a little bit deviate from the major theme of my research, which is utilizing the optimization for reinforcement learning. But recently, after we want to extend this kind of policy gradient from full gradient, from full using exact gradient to stochastic gradient, we eventually it seems like it's not avoidable. And I think that's the 2 components I will introduce in part 4. Okay, let's start a little bit just to make sure we can finish on time. You're definitely also familiar with this slides. I copied from Niao's lecture. She gave a very good categorization of the policy gradient. So this is object function. And with different setting, either it's tabular MDP with non-parametric parameterization, or with function approximation for the policy. I would argue a little bit here. Actually, this is direct parameterization, but and also this is softmax parameterization. But I would say both of them are non-parametric. And this softmax parameterization is still unparametric because for every state action, you still need 1 parameter. The only thing it's eliminated from this parameterization is you don't need to restrict this parameterization to a simplex. Itself is a valid distribution. So in the following, we will think that we will introduce some recent advanced results for using policy gradient with, exactly policy gradient with softmax parameterization in tabular case. And here's something I want to emphasize. After we introduce this kind of softmax parameterization here, and back to this object function, I would say it is highly non-convex with respect to theta. It's not convex. So we cannot use the off-the-shelf results to achieve the global convergence. So that's something I want to emphasize at the beginning of this section 4. Okay, and actually this is proved formally in this paper. Okay, let's begin the journey. Before we start everything, let's first derive what is policy gradient. you definitely know this theorem. This is very classic theorem proved by Sutton in 2000. I think it's a NeurIPS paper. I will give a brief proof here, and hope we can go this quickly before this. We still have 10 minutes. I think we definitely can finish this part. Okay. First, let's ignore this proof, and believe me, this is the gradient, policy gradient with respect to theta. And then we can use the gradient to update the theta. So this is called policy gradient method. Basically, every time you calculate this component, this bigger component, this includes the expectation. And every time you use the step eta to update your current parameter and go on, so on and so forth. This is what we call the policy gradient method. And in practice, we need to do some expectation estimation. So that's practical how, based on different way to estimate this expectation, that will generate a lot of different family of policy gradient variance, but we ignored that here at this moment. We just use this full expectation in this algorithm. Okay, so we are clear about the gradient, policy gradient and the policy gradient ascent method. Now let's see how we prove this equation 8. Okay, from this first step, it's based on the definition of VPath. Okay, and then this is linear nebula gradient operator is linear, so we switch this expectation or summation with and this nebula, and this is by first part and gradient for first part and gradient for second part. So this part is easy. We don't need to change it. For the second part, we still, based on the definition of Q pi, we expand it here. And then use the linear property of gradient operator and make it inside. And R is independent, reward function is independent of the pi. So eventually we get to this quantity. And look, this is almost the same as this one. So recursion again. You see, in my slides, in the duration, there's the recursion is very important. We use that again and again. So I changed this part remember, I changed this part to 5. I don't want to write it. I'm a little bit. So for here, and for this part is like after step 1 from the distribution starting from state S to okay, this quantity is like for after step 1 and starting from S, the distribution of S prime. So that's basically this quantity. And this part we do expansion again. And similarly, this is rolling out again and again. Eventually, it looks like this term. And by the definition of this one, and also the definition of state and the definition of stationary state and action distribution, this quantity is eventually here. So we prove equation 8. It's not difficult, just tedious. It's not difficult, just tedious. Every time when you apply the basic calculus rule, remember, do the rolling out, and remember every definition of the quantity, you will get there. Okay, after this slide, do we have any questions about policy gradient and the algorithm and also the derivation? Okay, so I think I will stop here, and let's start the final session 10 minutes later. And okay, in the final session, I will discuss different variants of the policy gradient and also their global convergence and their rate. If time permit, I will talk a little bit about the exploration, because this is a reinforcement learning introduction course. I think we cannot avoid the major component in reinforcement, which is exploration versus exploitation. Okay. See you in minutes.
Yes, so we will reconvene at 5. Okay, but when you are ready, we are ready to restart.
Hi, hi everyone. Okay, let's finish the final session, and everyone will be released. Okay, now we finished the policy gradient, and also the proof for how we calculate the policy gradient, and also we gave an illustration of how the policy gradient with full gradient executed in this algorithm box. And next we show some variants of the policy gradient. One of them is actually very famous. It's called natural policy gradient, which means after you calculate the policy gradient, instead of directly utilize that for update your parameters, here's theta, you can use either the Fisher matrix to inverse of Fisher matrix to do a sort of preconditioning to update the policy, or equivalently, you can update the policy in this form directly to the theta. So although I read into the policy here, but equivalently, if we use the soft max representation learning, soft max parameterization, this here is theta SA. So it's equivalent to theta t plus 1 equals to theta t plus eta q SA. Okay, that's the this equivalent formulation for that. So this is natural policy gradient. And also we have another variant, which is called normalized policy gradient. Basically, instead of doing this, we do this. Simple. We don't use policy. We don't use the gradient directly. We use a normalized gradient. We call it normalized policy gradient. This algorithm actually is published in our recent work. Okay, here is some variants. Okay, I shouldn't address questions here. And also another big class of variants is like, instead of our ranged object function, you introduce the entropy regularization into the object function, and then you can have entropy regularized policy gradient family. Okay, after you introduce that, actually the rest of the derivation is almost the same. Instead of you have actual component for the which is come from the regularizer. Okay, and then with this you can have the entropy regularized policy gradient, entropy regularized the natural policy gradient, and so on and so forth. Until now, I think I covered most of the representative algorithm in policy gradient. So you see this slide is familiar, but I separate this part into, we here give a very brief review of existing method, existing guarantee for what I introduced. Say like policy gradient with softmax. Actually, natural policy gradient without entropy regularized is improved recently to exponential. But 1/t rate is still unimprovable for softmax parameterized policy gradient. And also, I think I made some mistake here. It's not 1/t, it's exponential. It's linear rate for entropy regularized PG. I should correct this later. Sorry about that. And no matter whether with or without entropy regularizer for natural policy gradient, people prove that it's exponential, it's linear. And we also show that normalized policy gradient is also linear. The benefit of a normalized policy gradient is that in practice, you don't need to calculate the Fisher matrix anymore, just do very naively do the normalization and use that to update your policy. That's good enough. Remember, this is saying softmax parameterization, but still non-parametric and exactly gradient. I think any part to extend beyond the non-parametric parameterization, say like introduce any function approximation and utilize stochastic gradient is not trivial. I would say there's some method trying to introduce stochastic gradient instead of exactly gradient, but they require very, very restrict assumption for the stochastic gradient estimator. And actually, we observed, and also people observed, which they have published paper saying this assumption normally is not satisfied in practice. But even that, sometimes your gradient, even that, sometimes your stochastic policy gradient still converge. And that's the paper published recently by Marlos and Nicholas from Google Brain, and it's published in SML this year. So that makes this things a little bit weird. If it's not saying we can directly apply current result in stochastic gradient to stochastic policy gradient, because even the variance is unbounded is in stochastic policy gradient, sometimes still converge. Weird, right? But anyway, that's a little bit out of scope of this talk. Today I will just say recent progress in table case, softmax non-parametric, and exactly gradient. Remember, exactly gradient. Okay, so next I will give a very concrete example to show what's the major component to prove the global convergence. Actually, it's not difficult, but the proof actually is quite routine right now. But in this first paper, it's not that routine. But anyway, let's go back to the case study here. So it's softmax non-parametric plus vanilla policy gradient. Actually, this results with star minus VT is in root 1/t. It's proved in May 2020 SML. The proof idea is utilize a smoothness assumption of this part and non-uniform lowest width condition with value suboptimality. So this will become routine. You will see how we can connect every component here to give this results. It becomes quite routine right now. So every different variance, just to check this three condition, you're good enough. You're fine. Okay, now let's first see the proof sketch. Particularly for this policy gradient, particular softmax non-parametric policy gradient, we can show that the value the policy value itself is smooth. I mean, Lyapunov smooth. And also this condition can be proved by checking the spectral norm, the Hessian matrix of the gradient. As I mentioned, this is not difficult, it's just tedious, The next condition is very important, which is known as non-uniform lowest width condition. The reason we call it non-uniform is because this is never a constant. Okay, this is never a constant. It's dependent on actually the theta. Okay, it depends on your current, the gradient of the current parameterization, current step parameterization. So this is also not difficult, chat. You just check the bound of the norm. And finally, it's also not difficult. Actually, we use many times. This is this condition actually can be obtained by expand the definition of this V function, and you do some and also some definition of the d pi and the q. You will get there. These are all quite straightforward. Now let's see how we can connect these three components into our results, into the finite convergence rate.
Okay, step one. We first switch from the station distribution to a uniform distribution value, policy value. So in this one, we know that expectation is with respect to the station distribution, but here we change that from station distribution to initial distribution. So you see there's some change, but you have some constant here, and we assume in our assumption this is not zero. This is not zero, which another which you'll notice that this is also equivalent to in your initial distribution, your state and action pairs are visit everywhere. Okay, this is quite similar to the data coverage assumption. And then step two, we based on this one, we switch our object function from pi rho to pi mu, and then we can use the smoothness lemma to get this condition, which is saying the progress basically is upper bound by this null. Why is progress? Because you see, v star mu is never changed, so it's minus v star and minus v star, and it's cancelled. So basically, this is progress, and it's bounded by bounded by the gradient null. This is come from the smoothness lemma, and then we know there's NL inequality, or in another way, non-uniform lower switch condition. So switch from here to here. Quite simple, huh? Now notice what's this? Basically, this is difference between the current solution to the optimal one. And it's also appear here. Remember, I just canceled the V star. Actually, this step is a little bit tricky. Let me tell you what it is. This, as I mentioned, this is non-uniform, which means it depends on current solution, right? So that I upper bound it with the smallest constant along your trajectory. So this is just because your condition is non-uniform. So you need to handle this non-uniformity by some constant instead of every step you have different constant. Now, actually, after obtain this one, first assume this is not zero. And after this one, actually, you already have the recursion to quantify the progress on each step. And basically from here, if you assume this one is not zero, you can already achieve this 1 over t with a lot of constant in front of it. But final step, you need to check this condition is indeed satisfied, which means this part is not zero. Again, this is still tedious. Let me tell the high-level idea. You need to utilize non-asymptotic analysis to show that this algorithm indeed converge everywhere in your simplex, except the boundary. Okay, except the boundary. That means as long as your starting point is not have zero probability for each arm, for each action, you're good enough to converge global optimal. You're good enough to guarantee it never goes to zero during your optimization. And then because it's asymptotic, you can show that it never goes to zero. So this part is not zero. So combine this step 1, step 2, step 3, eventually you will have the conclusion. Okay, so come back to the high level idea. Three things. Actually, we use it in a different order. We first use this one to change the object function, and then we use the smoothness to let the progress is bounded by this quantity, and then use this one to map it back into the progress. Done. This is quite a standard recently, become a routine algorithm already, a routine proof method already. So the only thing different is like with different algorithm, you will have different smoothness constant and smoothness condition and the different NL conditions. So it will form eventually different recursion that will give the different rate. I think this is why different algorithms behave differently. And difficult part, actually, I think the most special part is you need to check this part instead of have a constant bounded. You need to really check, because you use the non-uniform Loyas width, you really need to check this constant is not zero. Otherwise, if this is zero, you can say nothing, right? So that means your progress is zero. So no, what can I say? Okay, this is basic. We use we gave a high-level proof scratch for softmax with non-parametric parameterization for policy gradient. So we really do some empirical verification for our results. This is quite a simple MDP. It's only one state, and you have different, say like 20 actions. Roughly speaking, you can think of this as a bandit. And we just do policy gradient, and we check the rate. So this is log t, and this is indeed the log t rate. You see, this is 1 over log t. We take, sorry, this is 1 over t and take log. This is curve, so match quite similar. And also, we know the best one is 1, so it's indeed converge to 1. So basically, we empirically verify our claim in a very simple case, which is manageable. Okay, so until now, I think I basically introduced the recent progress on global convergence on policy gradient family, and gave a case study of how we prove it in very basic algorithm. Any questions here? Okay, if we don't have questions, let's proceed. Okay, here's another case study, but I didn't complete the whole proof. I just show that even if you introduce entropy regularization, entropy itself is smooth, linear proof smooth with this constant. So plug this one with the original object function, it's still Lyapunov ellipsis constant, ellipsis smooth, and then introduce entropy regularization will change the non-uniform Loyas width condition. The basic thing here is it's no longer 1, it's 1 over 2. So that's why it will accelerate the convergence. And the rest of it is quite similar. Because this basically echoes what I'm saying. Now it's become the routine. Okay, so this is a summarization of not part 4, only a part of the part 4, which is the recent progress on if you use softmax non-parametric parameterization and exact gradient, how to prove these kind of results. Remember, smoothness condition, non-uniform Lyapunov, non-uniform Loyas width condition, and value suboptimality lemma. 3 things. This is most important component to prove the results. There's some tedious thing, and it's tricky. It's just you need to check, because the non-uniformity, you need to check the constant is never 0. And combine everything together, we'll get the solution. I mean, get the conclusion. Okay, I think this is what I want to cover about the recent results. Okay, definitely have some open questions, as I mentioned. All these results are using exact gradient. And I think there's one exception, which came from recently particle mirror gradient from George Lang. But in his paper, actually, he have a quite strong assumption about the estimation of the gradient, which saying the estimation of the gradient is almost the same as exactly gradient. So there's some noise, but no, it doesn't play too much effect. But as I mentioned, recently we noticed that this assumption is really rarely can be satisfied in practice. The variance can be unbounded. How we can, even the variance is unbounded, sometimes the algorithm is still converged, quite weird. How we can check, how we can provide some theoretical guarantee for that is still unclear to me. It's not answered yet. We have some initial thoughts, but we didn't finish the whole thing. We didn't close the problem yet. So this is one thing. And another one I think is quite interesting is if you introduce function approximation for the not Q function, not in the way that, not in this way, not in, sorry. Let's go to the first slide. Not in this way. Not in this way. Not in, say, exponential phi transpose theta. This exponential family way, because sometimes your action will be continuous. So summation over the continuous space is sometimes intractable. What if I say just a Gaussian distribution for this action, a parameterization? That's actually another difficulty. I didn't see any results on that yet. But that one actually is used a lot in practice. So I think there's still some gap between practice and theoretical results along this line. It's just the beginning. I would say, although the tabular case with exactly gradient and non-parametric parameterization almost finished, it seems many people came recently, but how to make it closer to practice setting is still don't know. Yeah, if anyone interesting, I think this is very good direction. Okay, so until now, I think I finished half of my section 4. And about the recent very hot topic about global convergence on using policy gradient for policy optimization. Any questions?
So you mentioned that when the gradient is not computed exactly, but rather we have an estimate of the gradient, so to say. So a stochastic gradient policy optimization, the variance could be unbounded, right? So there are some methods in the actor-critic fashion that use, for instance, estimate of the Q function or value function to somehow try to bound the variance. Could you comment on that, on the empirical? Yes.
Definitely. So
thanks.
That's still the case. It doesn't. It just pushes difficulty into policy evaluation, and that task is not completable in practice. The reason why is because, you see, let me give you a very intuitive or hand-wavy way to explain it. Even in on-policy setting, let's say the polytech, you need to make sure the QS is estimated very well, right? But in your current policy, maybe it's doesn't visit. It's not that flat. It's very sharp. Okay, so in that setting, you will only estimate some SA, not all of them. So that means your QSA for a different SNA, the variance will be huge.
difference of the variance will be huge. Some of them estimate very well, some of them are not. So in this case, it's really difficult to satisfy the assumption saying the Q function is estimated good, even you have on policy setting. So this is why I'm thinking that we should distinguish of the sampling policy and the optimal policy. The sampling policy should relatively, as we always observe here, have good coverage to make sure your estimator is good.
Mm-hmm.
But your control policy should be make it sharp, which means you need to go to the particular corner, which is best compared to other actions. So roughly speaking, this is already, you already see some shadows that there should be an exploration versus exploitation trade-off if you want to introduce the statistics, stochasticity in the estimation.
Yes.
This is my comment about this assumption about Q. It's not solving the problem, it just push some difficulty to assumption.
Mm-hmm. Thanks a lot. Thank you.
Yeah, if we don't have any questions along this part, I think I still have 20 minutes to give a brief introduction about exploitation and exploration. This is always a huge topic in reinforcement learning. I think I can make a claim that in Bandit, people understand this quite clear right now. But in MDP, it's still not sure. Still not sure. Oh, I shouldn't make such kind of claim because even in Bandit, if it's beyond the linear Bandit, I don't think any satisfiable result is satisfiable. So this is still a very active research area. Let's see, what is exploration versus exploitation? Actually, this is, as we discussed just it is induced by the stochastic nature because you never have the full information about everything. So you need to separate your effort, and part of them is trying to gather more information to know about your environment so that you have good estimation, better estimation. That's what we call exploration. But simultaneously, because you don't have, you want to still to achieve the best. You don't want to waste too much to estimate very well for some useless information. So that's what we call the exploitation. We want to make a better decision instead of estimate everything, right? So here I gave a quite a comic illustration. Say this robot want to pick a restaurant, and sometimes he goes to, as usual, he goes to this restaurant, but sometimes this new restaurant is opening. So if that's the case, whether he should go to there, and if he goes to there, that's called exploitation. That this robot use the chance to make a better estimation about the goodness of this restaurant. And if he goes to here, this is called exploitation because he already have very good estimation for the Euro place. And when we, in general, when we want to balance this trade-off between exploitation and the exploitation, the basic principle is be optimistic. Still, following this example, let me give an intuition why we want to be optimistic. If it's, say, it's not optimistic, so every time it goes to the best based on current estimation, because this is never visited, so this is, say, like starting from 0, and this is positive, so he never have the chance to visit here. But if you use upper bound estimation, so because you never visit here, the variance of this could be very high and much larger than this one. So he will utilize some chance to visit here, and based on that visitation, he will shrink the covariance while eventually have a good estimation of the mean. So if this upper bound eventually is smaller than the Euro place, he will never go through here, which means he already located the best one. So you don't need to visit here anymore. So be optimistic means you need to give chance to other places. And vice versa, if that places is better than this one, you will never miss the chance. So that's the reason why we want to be optimistic, why we want to always curious about new chance, new challenge. I hope this gives the intuition why we need to be optimistic. Okay, mathematically, how that optimistic eventually initialized or eventually concretized into algorithm. It's still like multi-arm-bandit, which is most simple MDP. Here you have two arms, and there's no state here. It's always you play this arm and you have a reward. There's no state change, so you always stay in that state. And the target of this multi-arm bandit is that eventually you pick the arm that's such that the reward is maximized. So in these cases, there's a famous algorithm called upper confidence bound algorithm, which is shorted as UCB. So the optimistic principle shows here is that every time you don't estimate the mean, but you estimate the upper bound. So which means instead of you just use the current empirical average to select, you also plus, which we call this bonus. And eventually this part gives you the optimistic part because here. So in this case, arm one is visit less. So shows in here is this part is small. So this bonus will be large. So he will visit this part. After visit that, he will have better estimation for the mean and also shrink the variance. And if the variance, if eventually the mean is smaller than this one, and also variance is shrink to below here, he will go to here. And this one will, this algorithm iteratively keep going and going. Eventually, we have guaranteed that this algorithm eventually will select the best one. And also, even better, we can control the regret, which means after you execute the algorithm n step, the best thing compared to what you get, the best reward, the maximal reward, the oracle reward, compared to the algorithm, the reward achieved by this algorithm is upper bounded by square root of kn. And if you divide by n, which is average reward, it's, you see, square root of k over n, which means it's shrinking. Okay. So I will skip the proof here. But this one, okay, I will skip the proof here. It's a little bit tricky, but remember, this part is saying by optimistic, you estimate the upper bound so that you can bound the regret at every state by current estimation minus true one plus bonus. And this part is controllable so that you eventually, when you accumulate this part, eventually your regret is in this rate. I hope this one gives you a rough understanding of what is UCB and what is implementation of the optimistic principle. Are we clear about this part? Great. If no questions, let's move to how this can inspire us about how we can move this kind of intuition to reinforcement learning. Okay, intuition. remember what we did in UCB for Bandit. We use the collected data to estimate model plus some bonus. And this bonus just trying to make you be optimistic. And then you pick the best action from this optimistic model. That's what we do in UCB, in Bandit. Similar thing happens in MDP. You can use the data to estimate the model plus the bonus. Meanwhile, when the only thing different here is that when you do the optimal action selection, it's not that easy to say max over all actions, max over all estimation plus bonus. It becomes a planning problem. So we use the value iteration to do that. And this gives you the algorithm called UCBVI, UCB value iteration. And I will give a algorithm box here. It's very simple. This part is counting. So it's tabular case. I will just focus on tabular case. This part is doing counting. And then the model can be estimated by this ratio from your empirical data. And the tricky part is here. It is giving you some bonus estimation. This part actually is doing the first component, which is doing the model estimation plus bonus estimation. And then, as I said, we can, because this is MDP, when you want to choose the optimal action from this optimistic model, it's not simple. So you need to do a policy evaluation. Sorry, not policy. You need to do a value iteration to select to do the planning and select the policy from it. Oops. And this one gives you the pi-t, and you execute the pi-t to collect data and do the iteration and so on and so forth. This is what we call it UCBVI. And still, you can bound regret in a sublinear rate. And still the key step is when you bound regret, you switch it to your upper bound. And this part is controllable. It's intuitively it is an extension of UCB, but because from Bandit to the MDP, it's a little bit tricky because you have so many recursions. So when the proof it shows that a lot of recursion you need to handle in bounding this term. I'm not going to detail, but remember this philosophy. And hope if you are interested, you can read the paper, and hope my explanation will give you a high-level idea of how they prove it. Okay, now I think I finished all the materials, and I think Niao covered a lot of other part. I only covered how we can use offline data, and also how we can use optimization to do with offline data to do the reinforcement learning. And here's my collaborator. And today I introduced a lot of work from a paper I co-authored with those guys. Dale from Google Brain, and Li Hong used to be in Google Brain, but now he moved to Amazon. And Jing Chen, Chaba, Wei Simon, Sherry, Ophir, definitely Niao, and Tor in Georgia Tech, and Inlam in Google. And thanks. And here's the reference I mentioned I talked today. And thanks everyone. Listen to my 4 hours, such a long time mini course. I know it's not easy for everyone.
Many thanks to you.
Any questions? Any questions about either what I talked today, or we still have time, so we still have 10 minutes. So any questions about either what I talked today, or you can ask any questions about I didn't talk today.
I have some question, which, okay, is probably again vague, but since like this is a control kind of workshop, right? Maybe it's a valid question to be asked. So, so the methods that you presented, most of them like relied on a discrete action and state space. And so is there some hope of, let's say, some of the the techniques presented or some of the tools to be lifted to give some answers to the problems where you have like, you know, like a continuous state and action space?
Definitely. I show it here just because it's simple and it's clean to give us intuition how we prove it. But actually, recently there's some effort to generate such kind of thing to continuous state and action model, which is called linear MDP and linear mixture MDP. So although it's simple, but actually it's one good direction and to generalize what we did here to continuous state and action. Definitely, things beyond linear is completely messy. We don't know yet, but I think this some recently popular model to do some generalization.
I'm asking because, like for example, you know, like you use like in the first part of your talk, right? So you use like the LP structure of MDPs quite a lot, and there is some, you know, like early work of Benjamin Fenroy and so on, where they have, you know, like LP structure for continuous space MDPs, and then they do constraint samplings, right? Because you still have like this for all state action pair constraint, which is infinitely many constraints. Yes. But you could think of then, you know, like applying approximation techniques there, such as, you know, like sampling, etc. So I'm wondering whether there's already like research activities on your offline MDP setting in this kind of general setup.
I would make some comment about the connection and difference about this thing. A connection is definitely we both eventually make the infinite many thing to finite, and we use the stochastic sample to do the expectation, and they actually do a particular sample random projection. Actually, to be honest, these two are equivalent. But in my case, I make it into all policy setting and also make it behavior agnostic, which means I don't know who sample it. But in their case, I think they need to know the phi structure. Right? So that's some connection and the difference. And what I want to say. Yeah, I think that's the connection and difference. Both of us, we do some thing here, but still have some difference. Yeah.
Okay, cool. Thanks a lot for the great talk. Yeah.
Thank you.
Or lecture. Yeah.
Thank you for your questions. Yeah, it's actually just to pin the major drawback of this kind of method. But I don't know any other kind of method can go beyond this. It's still a very still quite open problem. Yeah.
No.
Are there any other questions from the audience?
Oh, sorry. Go ahead.
Okay. Thank you. I have a question that's a little bit related to what's the last question? What is your point of view? What is your opinion about model-based reinforcement learning method in the application of offline reinforcement learning tasks?
Okay, what kind of method?
Model-based, like MOPO, model line plan.
Oh, model-based. Yeah, model-based.
Yeah, because I think they are more.
Yeah. I agree. I didn't mention this, but actually, if you look into offline setting, what I did is I do an empirical estimation first. You can always think I first do empirical estimation with data, and then what I'm doing there actually is doing planning with the empirical model. So that's why in my proof I said in the tabular case they are equivalent. Okay, and then come back to your questions whether which one I should use, either model-based or model-free. I think it depends. Some of the time, if you know everything about model, model-based, and that is not reinforced learning. That is called planning. So we should utilize model if we know it. But sometimes if we don't know it, I think we should avoid introduce any bias, which means model-based might be good in terms of approximation error. So I'm not saying which one is dominant the other one. I think it's case by case. Is this answer your questions?
Yeah, thank you.
Yeah, thanks also on my side for the course. And thanks for the effort of waking up so early in California. So my question was about the last part of the talk on the trade-off exploration exploitation, and particularly it seems to me that the UCB strategy works well asymptotically, and that's also what the regret analysis shows. But that also points out that in finite time you keep always accumulating regret because you need to then try all the possible upper bounds. So whenever you have uncertainty, you run the risk that you will go for something suboptimal. So yes. I was wondering if, in your opinion, it makes sense to formulate this trade-off more on a finite horizon problem where you have finite time and you have maybe some budget and you maybe accept some level of uncertainty to stay, let's say, with some level of uncertainty, but at some point you would like to stop being optimistic and just be greedy, because otherwise I mean, yeah, on one hand, I agree that you are solving the trade-off, but on the other hand, let's say you are doing it asymptotically. So it's kind of obvious that in the long run, you will visit everything. But I was wondering if it's possible to formulate strategies which are more finite time. And, you know, then you really have to play well because...
Yeah, I understand your questions. I think we should divide this into two problems. First one is UCB in infinite many time and versus finite time. I think in bandit, if I remember correctly, UCB already achieved lower bound, which means even in finite case, it's still the optimal. But when you say you want you don't want to observe everyone, you don't want to observe every arm. Let's go back to the data coverage setting. Let's go back to the data coverage setting. I think that's a good topic to work on. But we need to a little bit cautious that the stochastic machine learning theory is not working for that regime. So you need to definitely trust your assumption. You definitely need to trust your model. So I was thinking that only your model is good enough, or your representation is good enough, such that you do that either relies on your model, relies on your representation. You don't need to observe other things. Otherwise, it is require too much to enforce your need to achieve the optimal.
Yeah, so I guess that's a right way to maybe reformulate the problem. Is there a level of uncertainty in your system that you can tolerate? Hence, you can stop exploring as soon as you get there. And so you
Exactly.
Okay, I'm happy with that. Like going back to your analogy, I tried so many restaurants that no matter how good can be the end one that is opening tomorrow, I'm happy with what I already know and I will go to the best one so far.
Exactly.
Because, yeah, I can be suboptimal, but yeah, I can tolerate that error, right?
Exactly. So it depends on your assumption, your model, problem model, and your eventually evaluation criteria, right? So definitely there's still many things to do. Yeah.
No, thanks.
Any other question?
Any other questions? Yeah, I'm happy to answer them. Okay, seems like everyone is happy. So thanks everyone to attend this long course, and hope you enjoy your day.
Thanks a lot to you, Bodai, for having joined the summer school and for having endured all these long hours of lecturing, and also despite your time shift. And many thanks to all of you in the audience for having taken part in this first day of the summer school. So tomorrow, just to remind you, we have Nikolai Matini and Stephen Tu as main speakers. And since they're going to join us from the west coast of US, the sessions will be taking place in the afternoon from 2 to 11 p.m. And Bo, I don't know if you are aware of that. I believe yes, that there is a Slack channel of the summer school, and there is a channel inside Slack dedicated to your lecture. So if you like, you can join our Slack channel of the summer school and interact with the people, and they will, I imagine they will have many questions or many thoughts to share with you.
Definitely.
Thanks a lot. So then, and see you all tomorrow. Have a good evening.
Bye.